Mic check. 1 2 1 2. Check 1 2. Check 1 2. Yeah, it's coming through. You're just not hearing it. Mic check. Mic check. 1 2.
I think we can slowly begin while we're setting up the presentation. Hello everyone, good morning. Welcome to the second day of the Quantum Science Center Quantum Summer School. My name is Alex Senishev. I am postdoc here at Purdue University and I will preside over the morning session. We will have very exciting talks and speakers and I really look forward to it. And we will begin with the first talk from Professor Susan Yellen. So Professor Susan Yellen, she's a vice director of Max.
No, external.
No, that's outdated information. But then I will tell about the Professor Yellen's group studies on theoretical quantum optics and quantum information science. So the current research directions include quantum control of ultra-cold polar molecules, investigation of novel coherent-based optical elements, single-photon nonlinear optics using dipolar systems, coherent metamaterials, and negative refractivity, coherent control in condensed matter system, as well as super radiance. And today we will hear about quantum chemistry on a quantum computer. Let's welcome Professor Susan Yellen.
Okay, let's see whether it works. Okay. Good morning. Sorry for the technical difficulty. This is somehow still, I'm still not happy with that, but I guess. Okay, is that better? Okay. All right. The goal is to, I still get somehow a feedback here somewhere. Let me try here. Can you still hear me here? Yeah, still. Okay. What we want to, sorry, can we switch this a little bit less loud? This is kind of, sorry, I'm kind of getting freaked out by this right now. The goal here is to try to show some utility of a quantum computer. Sorry, I need some timer here. I'm sorry. Don't know where I put my phone. Can you give me some kind of 10 minutes or so? Okay, good. The idea is to try to find an application for a quantum computer where we can actually get something useful out, basically today. So today is not quite happening yet because everything which I'm showing you is actually not yet run on a quantum computer. It's all still simulations. But I can tell you, in case I forget to say this later, that in terms of simulations of the quantum computer, we are definitely at the limit now. So everything which goes bigger will have to run on a quantum computer, and our problem is set up such that we can run it as soon as the quantum computer becomes available. This is all, and I'm sorry that this is cut off on the bottom. So this is all based on our recent paper, Programmable Simulations of Molecules and Materials with Reconfigurable Quantum Processes. And here is all of the authors on that. And in particular, I would like to highlight Nishat and Stefan, who really have done most of the work. But also, I would like to show with pride Anna Krylov and Martin Head-Gordon, who are actually quantum chemists. So we really went with this problem to the chemists and asked, okay, so what could be useful? Okay, so quantum chemistry means solving an electronic structure problem for a configuration of electrons and nuclei. And this is a hard problem. In order to do this and in order to get a quantitative prediction, we need in principle the full Coulomb Hamiltonian. And this is a priori a hard problem, and in particular if we have strong correlations. And so we are really zooming in here on problems with strong correlations for which a quantum computer could potentially be helpful. Okay, let's just go back a little bit to this Microsoft paper from by now, I mean, 1.5 years ago. And let's look how, if we do quantum chemistry with a perfect universal quantum computer that is error corrected and has gates that run somewhere between a microsecond and a nanosecond per gate, and which has already physical qubits that have an error rate of somewhere between 10 to the minus 3 and 10 to the minus 4. How can we do with quantum chemistry? So as you can see, quantum chemistry is unfortunately somewhere up here in the right corner. So that means we need of the order of a couple of million qubits. And if once we know how to run our system, a single run can take somewhere between a month and a century. So that doesn't look so promising right now. So why is that? Why does that actually look so bad? So the first problem is that the mapping of the target Hamiltonian to the quantum hardware is very non-trivial, so one needs to do a lot of kind of translation. The algorithms are kind of universal, but it's strongly based on quantum phase estimation and similar, and this is relatively expensive. And there's, of course, this overhead for quantum error correction. So what we want to do, we want to simulate the relevant quantum dynamics. So we want to translate that into a quantum dynamics problem and run that on present-day hardware. Okay, so there are basically 3 aspects that we want to that are important for our approach. The first is that we take into account the classical quantum chemistry computational algorithms very heavily into account. Second, we are building this on programmable quantum simulators, and I'm going to tell you very briefly how this works, but you will hear more about that afterwards. And we will do this hardware efficient. And again, what we are looking at are problems with strong correlations. So there are three elements again that we use. The one is we really need some classical computation because, as I say, we kind of take into account what the quantum chemists do, and they run their computations on high-performance computers. The second is the so-called model Hamiltonian. So you can imagine that kind of for the chemists to take all the knowledge that they have, for example, for particular functional groups of a molecule or something like that, and kind of coarse graining already about everything that is known already, such that the Hamiltonian that actually needs to be solved looks already much simpler than the full kind of electronic electrons plus nuclei. And this is something which the quantum chemists also are very good at. And so we basically take their model Hamiltonian. So up to now, we are not building our own. And so the third part only is the actual use of the quantum computer. And of course, we kind of let them all 3 work together. Okay, so this is the model that we are looking at. And in particular, the target that we have is strong correlations due to spins that are large, and in particular larger than 1/2. So, and I will show you in a second an example of such a thing here. And I'm sorry that this became so small. Here is a spin Hamiltonian. Single spin terms, 2 spin terms, 3 spin terms, 4 spin terms, etc. And we are not limiting ourselves to any kind of particular symmetries like Heisenberg or anything like that. So here is a molecule that kind of fits this model very well, because this has localized valence electrons, and I explain that in a second. this is a problem that is difficult to solve, but easy to obtain a model Hamiltonian for. And this also gives a relatively natural mapping to our quantum hardware. So we are basically taking advantage of everything that we can get right now. So this is where we got this from. So this particular molecule is a catalyst, and this is involved in a so-called oxygen-involving complex for photosynthesis. And so why is this an interesting molecule? So here's the periodic table of elements. And as you can see, this catalyst has 4 manganese atoms in it. And manganese is a transition metal that sits here. And in particular, it has 7 valence electrons. Of those 7 valence electrons, you see these numbers here, 4 and 3. This is the so-called oxidation state. And the oxidation state just tells you how many of these electrons are actually already used up for bonds, for these covalent bonds that are basically shown here as lines. So in the case of an oxidation state of 4, that means 4 of those valence electrons are already used up. That leaves 3. And these 3 electrons, they act in unison as like a spin 3 half particle. So they are not kind of 3 independent electrons, they are really a spin 3 half electron, the spin 3 half particle. And this is basically where we get our high spin value come from. And here again, I'm sorry that this got hidden by Zoom here. So there are 3 types of interaction. The one is the Coulomb interaction. This basically localizes the electrons and has been taken into account already by the model Hamiltonian. So we can take that first part as solved. But then there are, due to the spins, there is exchange interaction and super exchange interaction. And the exchange interaction is ferromagnetic and the super exchange interaction is antiferromagnetic. So we have at the same time both basically repulsive and attractive interactions, and that makes for a complicated kind of frustrated system. And if one asks computational chemists how they see these molecules, this is what we get. So here are our 4 spins, and this F and AF stands for ferromagnetic and antiferromagnetic. And what one gets in this case, so I say there's a Hilbert space scaling, which basically goes with the total 2s, where s is the total spin, plus 1 to the n, where n is the number of spins. But please do note that this is a multiplicative factor on top of all of the other kind of electronics that are in there already. And please do note that even for this very simple problem with these kind of spin 3 half and spin 2 manganese atoms, this is already basically 2 orders of magnitude. Okay, so how do we do that? There are 3 problems that we have to solve. First of all, we have to represent the high spins. The second is we have to have them interact with each other, and for this we also need non-local connectivity because they are all interacting with all. And then the last is how can we read out quantities that are actually relevant for chemists, which means we are not happy with just finding the ground state. And this here we do some heavy quantum classical co-processing, and I will explain this. Okay, so here is basically the same program again, but with some pictures. And I will start with this non-local connectivity, because that's a problem that's basically solved already before we even start kind of thinking about this problem. By the fact that in the Rydberg atom arrays, the atoms can be moved during the calculation. I should say at this point that, for example, if you take ion trap quantum computers, they have a priori all-to-all interaction, and also by now can do multi-qubit gates, so this can be relatively simply translated into ion trap quantum computers. But for now, I assume we have a Rydberg array. So let me tell you very briefly, Misha will tell you afterwards a lot more about these Rydberg arrays. So the idea of the Rydberg quantum computer is you have atoms in an array that can be sorted at will by having every atom in its own little tweezer, and these tweezers can be moved around independently. And the nonlinear interaction is due to the Rydberg blockade. So the idea here is that you have, for atoms in the Rydberg state, they interact very, very strongly. It's 1/6, but with a very strong prefactor. Whereas atoms in the ground state basically don't interact. So what does that mean? That means that if, so here on the x-axis, we see the distance between two atoms. So if we are somehow very far away, the atoms are independent, and if you send one photon in, we get one atom excited into the, so R and G stands for Rydberg and ground state. We get one atom excited into the Rydberg state. If we send two in, we get two atoms, and if we have more than that, we kind of get this ladder. However, if they are very close together, this interaction kicks in, and the first excitation happens very nicely, but the second one and all the subsequent ones is out of resonance. So no matter how much light you send into such an ensemble of very close by atoms, only one ever gets excited. And this is nonlinear, and this can be built into a gate, and here's a very nice paper which shows how to do that with very high fidelity. The nice thing is it's also a very robust interaction because it's enough that they are close together. It doesn't matter whether you are somewhere here or somewhere here, you get the same interaction in both cases. Here is a small movie that, of the reconfigurable kind of array. This is a real movie, but it's not absolutely real time. This goes really faster in reality. There's the high fidelity gates, and then this moving and having the gates gives an analog digital hybrid control, so that at the end we have a high degree of programmability. The interactions are manipulated just by geometry of the proximity of the atoms, and then we have pulses that are global over the whole thing. So we cannot address single atoms. We can only address all atoms at the same time. But that one gives us the non-local connectivity. So the next question is, how do we do high spins? So there are actually quite a number of really good proposals how to program high spins. So you can take, for example, the plethora of internal kind of atomic or even molecular states, which I'm not going to talk about, and which is nice, but right now there is no good solution on how to do that without a really huge amount of extra lasers. And so the way how we actually do this is we just say that a spin S variable is encoded in 2s qubits. So for example, a spin 3/2 is encoded into 3 spin 1/2 particles. These are already here kind of suggestively drawn as being within one Rydberg blockade radius. So close together. I will call this clusters from now on. And I should also say that the level scheme is a little bit more complicated than what I showed on the previous slide. Namely, we have now 3 states. We still have the Rydberg state and the ground state, but the ground state is now, we use two parts of the ground states as the 1 and the 0, and use the excitation in the Rydberg state just for the nonlinear interaction. And we do that with 2 fields that both can be detuned and have a kind of changeable Rabi frequency, and these are time dependent. And both of these fields act on all of the atoms, but the fields are independent of each other. So now if we do this encoding, we have to make sure that the particular kind of 3-qubit state is actually a valid spin state. So here this is the kind of all over kind of spin relation that we know from quantum mechanics. And not every, and in particular, only the symmetric subspace of a 3 qubit state is actually a valid 3/2 state. And so that means that we have to make sure that we stay within this substate. So what we do is engineer 2 field pulses with these 2 fields here. And we can, in principle, implement any 2s qubit gate with that. And here I just give 2 examples. One is the all-to-all interaction, which goes with s squared. And the other one is the projection back into the symmetric subspace, which for obvious reason is very important. And the way how we do this is we just use time-optimized multi-qubit gates and use a method that's already very well tested, GRAPE or gradient ascent pulse engineering, which gives us pulses that look something like that. Okay, this is around since about 20 years, and the 3 last citations here are use cases, so people who have used these in practical things. So this is a very well known and commonly used method. And here I would like to just show you how well that actually works if we do that. So on the left side, we have these multi-qubit gates. In this case, for the 3 that I showed you, this is a 3-qubit gate, where we do these global pulses. And here are these two operations, the Heisenberg one and the projection into the symmetric subspace that I showed you before. And here on the x-axis is the number of qubits inside one cluster, and here is the gate time. And here we see, sorry, there are 2 sets. Just look at the lower sets. The upper one is if we optimize the pulses separately, and here is if we optimize them at the same time. And what we see, surprisingly, is that the time gate takes nearly doesn't go up with the number of qubits. There is no analytical proof or anything like that for that. This is purely heuristic. We just tried this out, and this is what comes out. But now we compare that with the same situation if we just take universal computation 2-qubit operations. Please do note that both have an error that's about the error that the experiment has right now. So we are really trying to compare apples to apples. And here you can see that the number of gates that you need for up to 8 qubit goes up basically exponentially. So at this point, we already have an orders of magnitude speed up by just kind of implementing this great pulses for 3 spins at the same time. Okay, so here I show you a little bit how this works. So we had to, of course, in order to show how this works, we had to take a particular Hamiltonian. So here we just take a 2-qubit Hamiltonian, but we are kind of taking here into account. So this Jij means that there can be really different interaction in principle for each pair of Ij. We have here just an example where we, for example, can take a symmetric part and an anti-symmetric Jalochinsky-Moria part. So the way how this goes is, sorry, I should go back once more. So here are all our clusters. So we basically, on this picture, would have a spin 3/2 state, a spin 2 state, spin 3/2, spin 1, etc. So if we have this, how do we do this? So we start by reconfiguring. So we take 1 qubit out of each cluster such that we basically get all the interactions that we need for our target Hamiltonian. We run a gate here, which is now just a 2-qubit gate for all of these interactions, which is the same as the target Hamiltonian, except that these are now, of course, single qubit spins and not these full 3/2 spins or spin S spins that we want. This is nice. We can get all of the Hamiltonians that way. We have this long-range connectivity because we can move these together from anywhere to anywhere. But it does violate this large spin encoding. Okay, so we have to go back into this large spin state. So we move them back and run this projection into the symmetric space. And now we just do this as a kind of a floquet sequence. So we here this HC is the intra and the HI is the inter cluster Hamiltonian. And the nice thing is, a priori, both of these theta and the tau are small, but it turns out this actually not necessary. This theta can be big, the tau unfortunately not. And with this floquet sequence, we realize the target Hamiltonian on average. The nice thing about this floquet is that we, of course, can now optimize the floquet in order to also get rid of higher order errors. Or when we want these higher orders, we can control them also. So we have some examples of that as well, but I'm not going to show that to you today. Okay, so we can do all that. And the only thing that is left now is, okay, we can do all our calculations. So now what? So for this, we kind of use the ability that we have this efficient time evolution on the Rydberg simulator. This is the generic kind of, we can do simulation, can do time evolution on a quantum computer. But the second is that we have the ability to perform snapshot measurements. What does that mean? The way how this in this system measurements are done is you basically take a camera, take a picture of all of the atoms in the array, and that tells you whether in the Z basis you have a 0 or a 1. So what you get is something that looks basically like this here, where you just get with one single shot, you get the solution of all of the atoms that you have, but only for one time, obviously, and only in one basis. And then we can do that for several times, and that gives us quite a lot of information. So the remaining question is just, how do we use this information best, okay? And for this, we defined a quantity which we call operator resolved density of states. And this is basically a spectrum, okay? So this can be done for arbitrary operators A. And let's just for now assume that A is unity, then obviously this first term here is 1, and then we just have the spectrum. Okay, but this A can also be something else, so in such as to basically weigh these different peaks of the spectrum differently. And so this first term gives us the properties of the eigenstates, the second one gives us the spectrum, and the big question is, why is that useful and how do we get it from our quantum computer? So here is basically the idea. And I spare you the exact mass, but the important thing is that this quantity can be written as an sum or average over many evolution times, over many state samples, and over different observables. And inside this kind of averaging, we have two correlation functions. The first one is a time evolution of a known reference state, which we can't just put into whatever, for example, tensor network methods or so, and can be done classically very efficiently. The second, however, is the time evolution of an unknown superposition state, and that cannot be done classically efficiently. And so that is the part that we put on the quantum computer, and that's basically the evolution that I showed you before with this kind of moving atoms around. Here is a little bit more details, which I spare you today. But the nice thing is, I told you that these operators A, and I tell you a little bit more about them, are kind of crucial into how to read the spectrum. And the nice thing is that with the same set of samples, we can find this operator resolved density of states for any A that we want without taking new measurements. Okay, let me show you how this works as an example. So we can show this whole evolution and like that type of quantum circuit. We start with some kind of, let's say, everything in a zero in an up state or so. Then we transform that into a known reference state. So S is a simple operator that we can just run. And then we sample over all kind of basically disturbances of our systems R. So R is one of the things that we average over. And this one is used in a control R operation on a plus state. So we have superposition of the undisturbed and the disturbed states. And then we run our time evolution, and then we take the sample measurements. N qubits give the parallel measurement of 2n observables. If you want to know why that is, you can ask me later. And here is an example of what we get. This is a very simple example to just show the idea. This is just a Heisenberg Hamiltonian of two interacting spins we have. That's also a nice example because that's obviously something which we easily can perfectly calculate. For example, we can do a direct diagonalization and look where our eigenstates are. These are these gray lines that we see here. And now we can see that we have actually five different lines in this picture. The one is this black, the black broken line, where we use as this operator A, just the unit. So this is just the spectrum. And there you already see immediately what the problem is here. Namely that if the lines have any widths, and in our case, the width comes from the errors in the quantum computer, that, I mean, as I say, this is all simulated, but we simulate the errors as well. Okay. For this black spectrum, this lowest energy eigenvalue gets totally swallowed up. Okay. Also, if we just look at that, we know the spectrum, but we don't know anything about the physics or the chemistry that lies behind the spectrum. So now we take the same sample and take as this operator A the projectors into the zero total spin manifold, into the one total spin manifold, etc., for all the spin manifolds, and see each of them gives us the spectrum that only comes from this particular spin manifold. So you see, for example, that this zero spin manifold gives us now this lowest lying line. So we know, first of all, we see that this line is there. And as you can see, this one is actually now very exact. But we also see that this lowest energy state comes from the zero spin manifold. And so on for the higher ones. Please do note, just for completeness, this is something that is done over 20,000 samples. And this is something that is kind of, that can be done relatively fast. So 20,000 samples is low. Okay, what we also can do is, for example, find the temperature dependent of the susceptibility. For this, we use for this operator A, just the sigma z, and take all the results that we get from that into a Boltzmann distribution. And this gives us this distribution. The black one is the exact solution. The blue and the pink one are if we average over 10K and 50K samples and make an error bar for that. So this is actually, I mean, it comes out pretty nice. But as I say, this is still kind of a two-spin Heisenberg Hamiltonian. So let's see. Let's go back to our nice kind of catalyst. If we do the same thing with A equals 2 unit, namely just look at the spectrum of that, we get something like this. And this is not the whole spectrum. This is only kind of the lower part of it. And here we see in some of these eigenvalues that are calculated. These are these lines. Not all of them are in because there are a lot of them in this case. And then we zoom out just this low-lying part. and do basically the same thing. So we look at the full spectrum, this is the black one, and we do this projection into these different spin manifolds. And here we see that we get already a lot of extra resolution. For example, between this yellow 5½ and the red 7½, they are obviously very close together, and turns out this is 0.3 wave numbers. And we can now resolve that and basically decide the physics of it. So here is just an example where the nice thing is the so-called spin ladders is something that can be calculated, measured experimentally. There are two similar configuration of this molecule. This is the same molecule here, which has these names, doesn't matter, which is if you know just the spectrum, it's basically impossible to tell the difference between the two. But since we have the spin resolved now, we can compare what we get from our resolution with the actual experimental detail and see that this first configuration is probably the right one. And with that, I'm basically out of time. So one can actually also use that for solid state materials. So here we do a little bit of band structure calculation where we do the single particle Green's function. I'm not going into detail with that. The next step is to actually expand this operator resolved density of states. And we have started with that already. Include error correction, which is non-trivial. The dynamics of chemical reactions in here, it's a little bit of a red herring, because once you know the low energy spectrum, you can actually just calculate the dynamics. You don't need to do anything extra with a quantum computer or so, at least a priori. And finally, the biggie is to actually really simulate fermions rather than spins. And I would just like to show you that we already have started to do that. We can now, for example, calculate potential surfaces. That is H2. This is not very exciting. But we can do a full fermionic kind of simulation of lithium hydride, where we use as an initial state or as this kind of reference state the Hartree fork. And what you see is a spectrum that is already very much non-trivial anymore. And with that, I would like to show my summary, and thank you.
Thank you, Professor Yellen. Excellent talk. We have time for one short question. Yes, please.
I heard several talks recently by chemists that are looking at the big problems in chemistry. What you presented is a very interesting problem in physics. But the question is the following. One of the challenges of the quantum computer in chemistry is to do drug design, to design particular drugs. Now, are you saying that, and the problem there, if I go to a bit deeper, is that the ability of computational chemistry today to predict the resonance, any resonance of a system that has biological molecules like proteins and so forth, is the error margins are plus minus 20%.
Well,
so do these actually include correlations of electrons or not? In other words, this is really in chemistry a problem. What you did is beautiful physics.
So our small molecule here, and I mean, for physics, that is an impossibly large molecule. But for chemists, this is a really, really small molecule. This actually, yes, it does take correlations into account. And we have started actually talking to these drug design people and thinking of where we can come in there. Drug design by now is done by basically looking at the surface distribution of electromagnetic forces of both the kind of the docking molecule and the drug, which is from our point of view, and even from the quantum chemists that I cite here point of view, very, very crude, but that's what they can do. So we are right now looking into where one can actually kind of look into that, and there are a couple of interesting problems. But we are very much in the beginning. That's not the talk that I'm willing to give yet. But yes, you are right. We can do full correlations, but at the end, the same as the classical calculations, you always have to weigh kind of the accuracy against the size of the problem, because at the end, even with a quantum computer, we have only finite resources. Right?
All right, let's thank Professor Yellen again. We have a change in our program, so the talk from Professor Chris Monroe will be in the afternoon, and now we will have next talk by Professor Mikhail Lukin. And while we're setting up the presentation, I will introduce our speaker. Professor Mikhail Lukin is a professor in Harvard University, and his group focuses both on the theoretical and experimental studies in quantum optics, atomic physics, and quantum information science. So the emphasis is on studies of quantum systems consisting of strongly interacting photons, atoms, molecules, and electrons. They're developing new techniques for controlling quantum dynamics and studying the relevant fundamental physics phenomena. So let's welcome our speaker, Professor Mikhail Lukin.
Risers. So what, it's okay? How about this, some things? Yeah, no? Better? Okay. So for invitation, it's always a great pleasure to be here. It's almost like an annual event now. So actually, pertinent to the previous discussion, I think, you know, these quantum computers and quantum simulators are, of course, very important for, or potentially could be very important for problems with strong correlations. And so in real kind of world chemistry and materials, you know, in quantum materials, there are many problems with strong correlations. In chemistry, actually, problems involving strong correlations are not as frequent, but there are some important ones, you know. So, you know, for example, you know, well, actually, I slept through my chemistry classes, so I shouldn't call it, but, you know, there are some, you know, like, okay, maybe I shouldn't say that. Yeah, some important, you know, if you party too hard, you know, the next morning, you know, how quickly you recover, you know, apparently this, you know, involves strong correlations, you know, believe it or not, you know. So, anyway, so quantum computers might play a role in this. So, okay, so my talk today will be about building quantum computers. And I would start out by kind of just identifying one key challenge, and the thing which limits our ability to execute quantum algorithms at scale is basically our ability to keep these, quantum computers and quantum processors quantum mechanical. And the way how operationally it comes up is that if you do, for example, quantum computation, you have to do logic gates, and the errors in logic operations somehow. Is there? Oh, I need. Is there a connector to? Yeah, but I need a. Do you have like this USB? This little. Sorry. Yes. Just. Yeah. It's yeah. Somehow. Usually I'm much better organized. So. It's okay. It's because we don't have quantum computers. That's it. But I will tell you how to fix this. So thank you so much. Okay, great. That's good. Thank you. It's perfect. It's okay. It's okay. Thank you. Thank you. All right. So basically, yeah. So okay. So kind of in the process of building quantum computers, there is now several systems which actually where the qubit count, is in hundreds and basically reaching thousands, and can do many steps of computation. But the real issue is that when you do quantum logic, you basically make errors, and these error rates now are hovering at a fraction of the percent. And basically, what it really means is that if you make a sufficient number of logic gates, eventually you'll have an error, and basically these errors kind of completely destroy the power of quantum computers. It basically makes them classical. So somehow it's not for some reason. Okay, I'll just use it. So basically, this is a challenge, and so the reason why it's challenging that most known useful algorithms in practice require many billions of operations, and there is a huge gap. So this challenge has been realized many years ago at a point where people started seriously thinking about building quantum computers, and for this reason, actually, for some time, some people thought that quantum computers could never be built. This still may or may not be true, but at least conceptually, this motivated the development of the idea of quantum error correction, which actually is a solution to that. So what quantum error correction is basically very similar to classical error correction, where you use redundancy. So you basically encode, for example, one bit of information, like in 3 bits, and then you can use things like majority vote to correct the error. So in quantum mechanics, it's actually not so easy, because in quantum mechanics, there's no cloning theorem. You cannot duplicate quantum information. Also, typically, this finding out if you have an error or not involves a measurement. And typically, when you measure the quantum state, you destroy it. But it turns out these seemingly, very fundamental obstacles could be surpassed. And the idea is essentially to use entanglement to delocalize quantum information. So it turns out that some, relatively small modifications, but important modifications to classical error correcting codes allow us to basically use this idea of redundancy to correct quantum errors. And so what you do in this error correcting protocols, you typically use many physical qubits to encode one so-called logical qubit or few logical qubits. And then you measure some things which are called stabilizers, some special operators, which allow you to basically figure out if the error occurred or not. And basically, by being delocalized, these logical qubit degrees of freedom become hard to manipulate accidentally, and that's the basis for this kind of protection of the quantum information. Just one example by now is perhaps the most famous example is a so-called surface authoric code. It's due to Alexei Kitaev, which is basically kind of a product of the two classical repetition codes. One corrects for bit flips and another one corrects for phase flips, because in quantum mechanics you can have both types of errors. And in practice, it involves measuring this kind of stabilizers, which are basically a products of these, four operators, Z operators or X operators. And the way how it works is, for example, if you have a qubit which had, for example, an error, for example, a bit flip. So the pair of these stabilizers light up. You see that now they should be 1, but instead they're -1, and you, by that measure, can kind of identify that error occurred and correct it. And the fundamental idea is that if we make a lattice bigger, so there are more checks, but there are also more opportunities for errors. And it turns out that, there is something which is called a threshold. So basically, if the error probability is sufficiently small, by making the lattice bigger, you can basically suppress it to very high degree. And this suppression is determined by a code distance, basically by linear size of this lattice. And as such, this offers realistic route towards extremely small errors. So I should say that it was really this theoretical breakthrough of quantum error correction, which was extremely non-trivial, which really caused this field of quantum computing to take off. And it's basically commonly agreed in the field that eventually we'll need to transition from performing algorithms with physical qubit to actually doing it with logical qubits. But already you see this kind of redundancy, and all of these kind of sophisticated interactions introduce quite a bit of overhead. And basically, as a result, the kind of so the current challenge is that, basically these logical qubits are very hard to build and control. In fact, most of the current demonstrations are limited to 1 or 2 kind of very small qubits, maybe doing at most 1 gate. And there is some very nice work have been done, in Innsbruck, Duke, Quantinum, also Google Group, and Yale, ETH, etc. So we will try to address this challenge by using quantum processors based on cold neutral atoms. And so the key advantage of these processors is that atoms have, to begin with, excellent coherence properties, and we can actually create large samples of atoms. But atoms do not interact very strongly typically, and it's also kind of have been hard, at least until recently, to control atoms individually in large numbers. So the approach we will be using involves the so-called optical tweezers. So we'll basically use focal beams of light, to trap individual atoms, and we will focus this laser beam so tightly that each tweezer will host at most 1 atom. So what we'll do in practice is not just use 1 tweezer, but we'll use, thousands of tweezers now, and try to trap atoms in all of them. And actually in practice, what will happen is that you trap atoms in some tweezers and, not in others. So the system has now classical entropy. So to get rid of this classical entropy, so what we'll need to do, we'll need which traps are full and which are not, which are empty. And then using this information, we can then move atoms around. For example, we can remove some traps and move some other traps in such a way to actually create a desired array. So with that, we'll end up with systems where atoms are separated by a few micrometers. They are kind of easily optically resolvable, but then the atoms at this point are completely non-interacting. And so what we'll do is to basically make them interact. We excite them into the Rydberg states, and basically by doing so, we effectively increase the atom size, and we will dramatically, increase the interaction strength. So this is actually our kind of joint project with Vladan Vuletic and Markus Greiner that actually we started now nearly 10 years ago, and I think this actually has been a lot of fun. It's still a lot of fun. So just kind of maybe give a little bit of more feeling for what is Rydberg excitations really mean. So if you take, for example, the atom excited into principal number n equals 100, the van der Waal interaction between two such atoms will be 14 orders of magnitude stronger than the van der Waal interaction between two ground state atoms. 14 orders is a large number. We can use it, make it to good use. And also, Rydberg atoms live relatively, have relatively long lifetimes. They live typically something like 100 or a couple of hundred of microseconds. So to make use of this interaction, we utilize something which is called Rydberg blockade. So Susanna already introduced it. Let me just briefly go over it. So basically, what we'll try to do, we'll try to simultaneously excite both of these atoms resonantly into the Rydberg states. But actually, when the atoms come close together at some point, this van der Waal interaction will take off. And then basically at this point, this doubly excited state will be shifted far away from resonance. We will be able to excite one atom or another, but never both. And it turns out that it's actually a very good, very robust mechanism to entangle atoms, because in particular, it's insensitive to things like exact position of the atoms and motion as well. So in kind of combination, what we will do is we will basically assemble the arrays of atoms, then encode qubits in the internal state, manipulate these internal states individually or through this Rydberg excitation, do quantum logic, and then eventually we will read out the atoms in a state-dependent way. So this is our kind of cycle. Experimental cycle. So this is actually an exploding field. There are, actually a few hundred experiments are built around the world. Actually, many of them in academia, but there are now already actually at least 8 companies are pursuing it, and I think the number is actually growing. And there is a wide variety of kind of different directions. So, for example, you can think about choosing different types of atoms. In what follows, we'll use rubidium atoms, but which is alkali atom, but you can also use alkaline earth atoms. You can use molecules, and some of these systems become really exotic. So this is a kind of a double species array from Hannes Bernian group, and actually this is an array of I think over 5,000 trap atoms from cesium atoms from Manuel Ender's group at Caltech. So this is actually a lot of fun field. I'm so sorry this thing is cut off. So. It's exciting frontier from many body physics to metrology, and it bridges things also to other areas combined with optical lattices and things like this. Okay, so the workforce of many of these experiments is a computer generated hologram, which is very similar to the device which is used in this projector to project the slides. So it's so-called special light modulator. And basically using the special light modulator, by basically programming it with the computer, we can control the deflection angle. And we can, for example, create the pattern which will actually generate, 2-dimensional arrays of the tweezers when basically projected into the vacuum chamber is what we can use to trap the atoms. So this special light modulator, and as I already mentioned, you can actually now create, tens of thousands of these tweezers. One drawback of the special light modulator is that it's actually relatively slow. The update rate is very slow. We need to actually move the atoms faster, and to do that, we actually use these devices called acousto-optic deflectors. So basically, which use sound wave to deflect the laser beam. In fact, we typically use pairs of them, which allow us to basically move rows and columns independently. In fact, in our experiment now we have 3 sets of these crossed acousto-optic deflectors, which we use both to move atoms, but also to single qubit manipulation. And it's all computer control. So basically, this is our 3rd generation of the apparatus, and the key is now that we can control larger systems. We have higher fidelity and we have much more advanced control. So basically, I can now routinely trap over 1,000 atoms, and we can make defect-free arrays, which actually also, approaching 1,000. So, and with this kind of approach, it has been a lot of fun the last couple of years. So I think I talked about some of these things In prior editions of the school, we explore many-body physics, explore dynamics, also thinking about how to use it to accelerate classical combinatorial optimization problems. So this thing here is cut off. So there is actually a machine of the time which I just described, now available online. And actually Pedro later today will talk about the Square Aquila processor. There's actually another Quera processor coming up online soon. And what I'll talk today is about kind of an approach. So most of these things, can be viewed as a kind of analog systems. So I will focus today on this digital approach involving, in particular, error correction. So the key idea of this digital approach is something which we call reconfigurable architecture. And the idea is the following. So we'll encode qubit in a long-lived states of the atoms, the so-called spin states, so hyperfine states. It turns out that once qubits are encoded in the states, they can live for a very long time, so coherent times routinely as seconds. But not only qubit can just sit in one place, we can also take a tweezer and move this qubit around, while preserving coherence. And what this really means is that, this kind of, and so basically in this approach, the qubits are completely protected. And so only if we want to do the gates, we will excite them into a Rydberg state and use this blockade. So basically in this approach, what happens is that this connectivity of processor can be kind of like a living organism, right? So it's actually very different from what usually, how you build the processors, right? Usually what you do, you basically design it, then it goes to optical lithography, you actually use very similar tools to write directly, transistors, but then the connectivity is fixed at the design stage. Here, connectivity can change during the quantum evolution itself. So this quantum processor is kind of like a living organism, basically. So there are a couple of important unique features. One is that it allows us to couple qubits non-locally because we can just move one qubit to another, across the chip. And it also allows for something which is very important for efficient parallel classical control. So with this system, there is another set of, a lot of fun things to do. And I think Susanna already one direction, so we can sort of have new tool to study many-body physics. We're thinking about some quantum chemistry. We're thinking about topological matter and lattice gauge theories. And in fact, one could actually even kind of simulate quantum gravity or some kind of small models of quantum gravity. So the only thing which kind of, prevents us to have more and more fun with that is actually errors. So basically, so the key challenge in all of these things is to control the gate errors. So this would limit, for example, the circuit depths, which we can execute. And this is what I want to focus on next. So returning to this idea which I introduced of Kitaev's toric code. So here is an example of the error correcting code, which contains the so-called data qubits, which are black dots, and these ancilla qubits, which are red dots, which actually are used to make this kind of checks. And it turns out that if you put it on a torus, you have this additional kind of topological, protection. So basically, you have to, make errors going all the way around the torus to destroy your qubit. So, but implementing this thing, the torus in our 2D system seems hard. Actually, it turns out it's possible, and this is something that we already have done a couple of years ago. So here is a system where we have, some stationary data qubits, and there are these ancilla qubits which actually do this stabilizer measurements. So they do these local checks first with nearby atoms, as you see here. So red is the gate, And what you will see is that basically after they do these local checks, the final round of the checks, you basically move these qubits all the way around. So this is so to complete, basically to complete this torus. And so basically without going into the details, what is amazing about this approach is that this circuit can be programmed by just 2 voltages, which kind of move this ancilla atoms up and down and left and right. And this, efficient control allows us in this case to actually encode 2 logical qubits, one going across one way direction of torus and another one going across the other direction of torus, but just with basically two control nodes. So this efficient control will be a central feature of this talk. Okay, so since this work, which was 2 years ago, we actually were quite busy. And in fact, last year we've done a number of technical upgrades. So first off, we improved our gate fidelities, which are now basically, pretty much at the state of the art. So we can have error rates about 0.5, 0.4% per 2-qubit operations. We have also kind of individual addressing. In fact, we can in parallel address basically arbitrary patterns of these qubits, and these fidelities are also actually quite high. So local addressing has 3 nines, global is actually 4 nines. And also using this reconfigurable architecture, we can also now read out qubits during the computation process itself. So the way how we do it is we basically have some zones, where we can actually plug some qubits and move it to a separate zone where we actually can image, basically these qubits, detect their state, without disturbing, what's happening in this other, entangling on storage. So combined together, this is kind of like resulted in a kind of, I would call it first logical quantum processor. So, and if you think a little bit about it, so this logical processor has different zones is already indicated. One will be used to store qubits, one to store fresh ancillas. The third zone will be used to do entangling operations, and then there will be this readout zone. So actually, it kind of now starts looking like, a real quantum computer. And in fact, it has kind of a lot of analogies with something which is kind of very early on was called von Neumann, and actually the modification is one called Harvard classical CPU architecture. So, okay, but the idea here is that basically you want to have an efficient control over logical rather than physical qubits. So to illustrate it, let's consider this kind of primitive involving basically doing a logic gates between two, like a 2-qubit gate between 2 encoded logical qubit. So and as already indicated, the key here is that quantum information is delocalized, so it makes it very stable. But it also, this delocalization makes it also very hard, to basically make a gate operation between 2 of such encoded entities. So basically, in some way, each of the qubits in the right logical qubit should kind of feel the presence of the of each of the qubit in the physical qubit in the left logical qubit. So basically, in a technical, so I guess yesterday there was some talks about anyons. What you kind of, one way to think about it is you need to basically take an excitation anyon and kind of drag it all the way around this kind of, this second, the other logical qubit. So, and this typically is quite challenging. And in fact, to do it fault tolerantly requires many rounds of error correction. But there is another approach, and this has been known already since actually basically Peter Shor, is something which is called transversal gate operations. And so the idea here is that you can basically take this logical qubit, bring it on the top of the other one, and then kind of execute gate operations on pairs, in parallel, on pairs of physical qubits. So it turns out this approach actually implements, in this case, for example, logical C0 or logical 2-qubit. And this approach is actually very effective. The reason is that, in doing this, you don't actually allow the errors to spread. So in fact, in general, D rounds of error correction is not required. In addition, you have this long direct connectivity between logical qubits. But most importantly, is that, basically we can now think about this encoded logical qubit as like one macro atom, so we can think about controlling not just individual physical qubits which are inside it, but controlling this entire thing all together. So we can grab, move it, and do this, all of these things in parallel. So, okay, so let's see how it works in practice. So this here, what we'll do is will basically uses two surface codes and prepare one of them in a plus state, one 0, and then basically try to apply this transversal gate. So the way how it works is that you can basically, so the smallest kind of interesting one is here 9 physical qubits. So we'll measure basically, Z stabilizers on one of them to prepare, and then X stabilizers on the other. And then what we'll do is basically we'll bring them together and do this transversal synod, and then put them apart and basically measure them. So, and then what we'll try to do is we'll try to increase the code size by just putting, encoding in more atoms and even more atoms, and see whether our operation improves. So here is the result. So first off, you can just by measuring in 2 different bases, this in this case of this D equals 7 code, you see that these 2 qubits actually are 2 logical qubits are entangled. And most importantly, this error indeed decreases with the code distance. This is a hallmark of the quantum error correction. So there are a wide variety of caveats and details here, which are actually important. So first off, it was important in these experiments to actually decode these qubits jointly, not individually, so to account for this kind of correlated errors which emerge from these transversal gates. One other thing which actually is important is that here we just did 1 round of entangling and immediate kind of error correction. So in practice, you need to do, of course, multiple rounds. Also, in this case, for this high distance code, our state preparation was not fault tolerant. So that's why in this case, correlated decoding was very, very important. But, basically this already simple example shows that it's really exciting frontier at the kind of interface of science and engineering. So there are many possibilities which one can explore. So here is another example. In this case, we use a color code. So the color code is also topological code, kind of similar as a surface code, but it's a little bit different. So in this case, what we do is we basically prepare this initial state fault tolerantly by first preparing 2 copies of this color code, both in the 0 state. And then what we do is we do a gate between them, basically to check, whether an error occurred in preparation. And so basically, this is a kind of like, if you want, logical Ramsey experiment. So in this case, if you do conditional operation on one of these qubits and then kind of measure measure its state, if this qubit is in 0, then the other one must have been 0. So this is how you make this preparation fault tolerant. And indeed, here what we see is basically we see that we can now prepare logical qubit much better than we can prepare physical qubits. So our error decreases both to non-fault tolerant state preparation and actually physical atomic operation. So I'm sorry. So there are actually, this is not the first experiment of this type. There is, in particular, some very nice work in Continuum. So these references are cut off, but maybe you'll get my slides. You will see them. But the big difference is that in all of these previous experiments, people will just do these things on just 2 qubits at a time. So in our case, we can do it on multiple qubits. In fact, so in this specific result was average over basically 4 pairs. And once we prepared 4 of these qubits, of course, what we can do, we can start, making circuits out of them. And so, in fact, what we've done in this case, we made actually a logical GG state from these 4 qubits which we have prepared. And what it means is basically first you prepare them fault tolerantly, and then you basically do entangling operation. And again, what we see is that, depending on exactly what we do, if we don't do fault tolerant preparation, our fidelity is actually quite low. If we do fault tolerant preparation, fidelity improves. And if we do some kind of fault tolerant preparation and additional kind of error detection, so basically we can push fidelity to essentially to unity. So there are also some very interesting features. So usually when you prepare GHG state, you look for like fringes, you try to change phase, for example, continuously. Here, with logical qubits, you cannot do that. So the logical qubits are really discrete, they're digital. So you cannot do kind of conventional, things to detect their presence, but actually for that, for example, what you can do basically a tomography, measure, all possible logical Pauli strings, and basically that's how you can extract fidelity. So basically, that really shows that there is kind of like exciting opportunities now to start exploring error-corrected, quantum algorithms with logical qubits. So I don't know how much time I have, so a few minutes, okay. So maybe just one last example to kind of illustrate this point is that basically we're now entering this kind of era of what I would call early fault tolerance, where we can already utilize at least some degree of this, protection. And in this era, what's very important is this idea of co-design, where you basically, think about the task you want to address, find the good algorithm, and then kind of try to match the algorithm with error-correcting code, with appropriate decoder and appropriate compiler, and then you try to basically map it to a native hardware capabilities. So the example which I will give here is this example of non-Clifford operations. So, and basically it turns out that, with these 2D codes which I've showed so far, all kind of fault-tolerant operations you can do correspond to the so-called Clifford gates. So basically, Clifford gates is a subgroup of Paulis involving, for example, X, Z, Hadamard, C0. And this subgroup can be implemented very efficiently, but the problem is that, it does not allow you to do universal quantum computation. In fact, with this, Clifford gates, you can, the result of this Clifford computation, even though if you can create highly entangled states, you can actually predict by just tracking the Pauli strings. So to do something trivial, you need non-Clifford operations. And usually this is actually one of the big challenges in quantum error correction, so how to actually do it efficiently. So there are all sorts of techniques involving code switching, the so-called magic T factory. So the question is, can we do this, in some other way to kind of utilize our, transversal gate capabilities? So it turns out the answer is yes, and you can do it using the so-called 3D codes by going away from 2 dimensions. So in fact, the simplest 3D code is this so-called 832 code, where qubits are basically placed, forming this this cube. So you can define the error correcting code by looking at different types of, surfaces, stabilizers, and etc. And because this code is 3-dimensional, so you can now do transversal non-Clifford operations. So in particular, by just rotating phases of individual qubits, physical qubits in this cube, you can actually perform the so-called CCZ gate, so which is non-Clifford, which is like a topology gate, So, okay, so and basically by combining it with entangling gate between different, blocks, we can now build quite non-trivial circuits. So in fact, what we'll do here, we'll prepare qubits in logical state plus, perform some interblock CZs and CCZs, and then perform C0s between the blocks, and then repeat this procedure. And actually, what it turns out, in practice, what we'll do, we'll actually, from these cubes, we'll start building, hypercubes. So it's actually kind of fun, but it's also a nice way to think about it. So like the target logical connectivity will be something like that, but actually the physical connectivity would be actually, in this case, high-dimensional hypercubed, up to 7-dimensional hypercubed. So basically, the question is, what sort of computation does it do? So it turns out that this computation implements something which is called instantaneous quantum polynomial circuit. This is actually a kind of a sampling algorithm, very similar to, for example, what Google has done with this kind of random circuit sampling. So just a different sampling algorithm, and it's actually a kind of known to be a circuit which is hard to simulate classically. So it's one of the examples of quantum supremacy circuit. So, okay, so how does it work? So we'll just run this algorithm and then measure these logical qubits. And basically what there is output of this circuit will be kind of like a speckle pattern. So it's basically speckle of random strings. And so for small number of qubits, for 12 qubits, we can still plot and simulate and plot these predictions of what probabilities of the string should be. So this theoretically is this gray curve. So if you don't do, if you just run it and don't do any kind of error correction, what you will see is that you see some circuit here. Maybe the highest string has some resemblance, but it's very hard to connect these two. So if you now increase the degree of error correction, so in this case, actually it's error detection, what you see is that basically a shadow of this perfect ideal classical distribution emerges. And you can quantify it by various kind of metrics, for example, like cross entropy benchmark. So one is a perfect circuit. So what you see now in the circuit is cross entropy benchmark is not perfect, but kind of relatively high, over 70%. And what we can do now, we can basically scale it up. We went and scaled the circuit up to 48 logical qubits. So this is our circuit, at a logical level, which we actually implement. And this is a physical connectivity, and we still see that for these circuits, the error correction really helps, and we basically achieve this cross entropy benchmark for the circuits about 10%, which actually is quite a bit higher than, is actually much higher, at least two orders of magnitude higher than we could possibly achieve with physical qubits, and it's also at least an order of magnitude higher than any other kind of demonstrations with physical qubits today. So this is actually a movie which shows this circuit. So what you see here is that basically we entangle things hierarchically. So we entangle smaller ones and bigger ones, and then at some point we run out of space in the entangling zone, then bring from storage, entangle more, and more, and even more, and even more, and then in the final step, what we'll do is we'll basically entangle all of them together. So I think it's by many measures the most advanced digital circuit has ever been executed on a quantum computer. So I'm running out of time. So but it's just the time to start having fun. So one of the other things we've done is we try to basically measure entanglement entropy, and it's actually turns out to be not very hard, because what you can do here, you just create two copies of this state and then basically do so-called Bell measurement. This all can be done with a logical qubit. So what basically this measurement shows is that the circuit we implement is a so-called fast scrambling circuit. So it's basically scrambling, creating entanglement at the fastest possible rate. So it actually has some analogies to some kind of black holes physics. But most importantly, what this really shows is that logical qubits really can be useful for proving physics of entangled complex quantum systems. And this is actually really an exciting scientific kind of frontier to try to use these things. So I want to wrap up here. So this is the kind of things which we kind of as a community are now thinking about. So it's very clear to us that these techniques can be directly scaled to tens of thousands of physical qubits. So we are already working to reduce error rates to at least 0.1% level. And there are many different directions. There are unique opportunities like involving erasure errors, bias, and altogether all of these things when combined, we see quite direct path to at least 100 logical qubits, 10 to the minus 6 error rate. But I don't think the progress will stop there. In fact, there are already new ideas which kind of, for example, novel encoding, things relate to so-called quantum DPC codes, novel ways to trap and kind of, atoms and utilize power more efficiently. So, all of that really lays down the foundation to the approaches with, thousands of logical qubit systems. So, but what I want to point out is I think this experiment really marked a little bit of a transition. So this is a picture from our lab. It's basically done by students and postdocs. And this is a picture involving generation of the GHZ state. This is now drawn for logical rather than physical qubits. So it's really a different way of thinking. So we are now thinking how to do operations with logical protected qubits. And I think this really is a very cool. I think it's probably one of the most exciting fields at the interface of science and engineering and applications. So I think I used up my time. So I just want to finish by thanking you for your attention and thanking also these people whose blood and sweat resulted in this work. Thank you.
Thank you, Professor Lukin. We have time for a couple of questions.
Thanks for the talk. Just a few words about the compatibility between the LDPC code and the transversal gates. Is it going to be a lot harder to implement the LDPC on this system?
Yeah, so the question is, so these LDPC codes, which I mentioned in the previous slide, so this is basically, so like, okay, the kind of foundation, the background here is the following. So something like a surface code is very well understood, but it has very low encoding rate. So basically you just grow the system size, you can still encode only 1 qubit. So, and in classical error correction, the codes like this are not used anymore. So for example, if you use, if you want to communicate with a spacecraft which is somewhere, around Mars, you use codes which have higher encoding density. And one of the state-of-the-art codes is so-called LDPC code. In fact, this is a code which is used, this is a kind of family of codes which is used in our cell phones right now. So what you do there, you encode, multiple logical qubits, in a kind of array of physical qubits. And it turns out that actually these kind of codes require non-local connectivity, and actually they can be relatively easily implemented in our system. In fact, there is a paper in Nature Physics this week, describing how to do it. The problem, and the question is how to actually do logic gates between this kind of, encode. It's like a mishmash, it's like a soup of, So this seems very challenging, and this is a frontier of the modern research, but some progress is being made. Stay tuned. So in fact, a lot of these gates can be made transversely, it turns out. But it's really a cutting edge frontier. Yeah.
Do we have more questions? If not, let's thank the speaker again. We'll have a short break. Let's reconvene at 10:40 for the next talks. Thank you. All right, I think we can now continue our morning session. I hope you had a good break and nice discussions about the talks you heard first day and in the morning session, and now we will continue with more exciting talks. All right, I'm glad to introduce our next speaker. Our next speaker is Shanik Chakrabarty. He is a quantum algorithm researcher at the Global Technology Applied Research Center at JP Morgan Chase. His primary research interest in the theory of quantum algorithms and characterization of quantum speedups for problems of classical interest with a focus on optimization, numerical analysis, machine learning, and stochastic modeling. So prior joining JP Morgan Chase in 2022, he obtained his PhD in computer science at the Joint Center for Quantum Information and Computer Science at the University of Maryland, College Park, where he worked on various aspects of quantum algorithms for optimization and machine learning. So let's welcome our speaker.
Can you hear me? Thank you for the very kind introduction. Very happy to be here and to follow two very excellent talks, although of course that is always a rather onerous task as well. And as you were just told, I'm at the Global Technology Applied Research Center at JP Morgan Chase. And we are a team of research scientists with our headquarters in New York City, although we have researchers in a number of other places scattered across the world. And our purpose is to design and conduct research across multiple frontier technologies in order to enable novel discoveries and inventions. And a list of these technologies at the bottom. So a few areas of focus are quantum computing, which is what I'm going to talk about, but also quantum communication, spatial computing, Internet of Things, fairness in computer vision and machine learning, cloud computing, blockchain, and this list is evolving. And the vision for the entire group is to take a long-term view towards research and to make a holistic investigation of these new platforms as they emerge in order to gain a good understanding whether these can be one day applied in the financial industry. And of course, in all these areas, we are very hopeful that they will have applications, but our view is not to say that these must be useful, but rather to come to sound scientific conclusions. And like I mentioned, I will be talking about the quantum computing efforts, and I'm moving a little bit away from the physics that we've encountered in the last two talks, and I'll talk more about algorithms. The purpose of our group is primarily to find out whether quantum algorithms are useful in the financial industry, which is rather broad. But to make it more specific, you could say our focus is that once we get to the era of early fault tolerance that Professor Lukin referred to a few minutes ago, do we have useful algorithms for industrial problems that we can run on these systems? And the typical areas in which you focus in the financial industry are things such as stochastic modeling, time forecasting using, say, Monte Carlo methods, optimization, and machine learning. And today, I will focus mostly on quantum optimization. Now, I'm aware that optimization perhaps is not the first application that comes to your mind when you hear quantum and finance. However, you'll be surprised to see how many applications in the financial industry essentially reduce to optimization. And optimization, due to its close links to other fields of science, also presents a very broad range of techniques that you can look at. And while there's interesting work to be done for machine learning and stochastic modeling, the techniques there so far are more limited. However, if this is your primary interest, please find me afterwards or write me an email. I'd be happy to talk about it. Now, on optimization, we focus on three main areas, and here they are labeled by algorithm, but let me label them by category of algorithm, right? So first, we have essentially quantum dynamics. And an example of this is adiabatic quantum optimization. Our goal here is to identify opportunities for quantum speedups with near-term devices, as well as to use insights from physics and quantum information to design new mechanisms for quantum algorithms. The second is evaluation of quantum heuristics. right? So here the classic example is what's called QAOA, or the quantum approximate optimization algorithm. And QAOA has been painted in many different ways. Like some people view it as an algorithm that really is meant for near term. We view it more as a meta-heuristic framework for discovering quantum algorithms, right? So we see it more as being analogous to, say, simulated annealing or parallel tempering in physics, and a heuristic that gives you a recipe for coming up with a method that you try an optimization problem. The thing that makes it a heuristic is that, say, global optimality or performance is not guaranteed. However, there is mounting evidence that the best way to use QAOA is not necessarily on a NISQ machine, but that it is a viable candidate for fault tolerance. And I will dive into this more later. And here we have both theoretical goals, such as understanding the speedup offered by QAOA and to understand the mechanism that leads to these speedups, as well as goals that are closely connected to implementation, which is to push the limits of QAOA on hardware and to make a plan for what QAOA algorithms implemented on early fault-tolerant quantum computers will look like. And then finally, we refer here to quantum mixed integer programming, but this is the area of provable speedups. So this is traditional computer science. Can you take a problem, derive a quantum algorithm, and prove a theorem that guarantees the performance of the quantum algorithm, and another theorem that shows a separation from the best you can do classically? So this is the traditional research you would find at a computer science conference. Now, this is a little bit far away from early fault tolerance. However, we find like these as a useful starting point for what problems even make sense to look at. And we want to reduce the risk of our effort by exploring multiple algorithmic approaches. Our team, as some of you know, is quite large. And given that we have a number of researchers, we have the bandwidth to explore a number of approaches. And we would not like to miss anything, even if we think that's not the most useful thing in the short term. Now, it would be nice if quantum algorithms in finance was just about studying a lot about quantum algorithms and then studying a bit about finance and then figuring out how to use the quantum algorithm for finance. However, there are significant limitations. And I think if you ask most people who work on quantum algorithms, that if for a long time the story was that we have great quantum algorithms, but the hardware is not good enough. But the quantum hardware industry has been doing what to a computer scientist seems essentially like magic, and hardware gets better and better every year. And it is not immediately clear that given a system that now is on many public roadmaps, say by 2030, and that gives you some degree of early fault tolerance, is there an industrially useful problem you can solve with it, say outside of chemistry? The answer to this is not obvious, and I'll present you 3 challenges, and this informs the perspective we take towards algorithmic research. So challenge 1 is that provable speedups are small, right? So if you look at provable speedups for optimization, you get a lot of them by applying a standard routine known as amplitude amplification, often in very clever ways, to particular components of classical algorithms. And because amplitude amplification itself gives you a quadratic speedup, no matter how clever you get with this paradigm, you can only construct a quadratic speedup. And in fact, there are many settings where you construct smaller than quadratic speedups. Some super polynomial proven speedups exist, right? So for example, factoring and discrete log, but it's difficult to find, say, an industrial optimization problem that's actually just a factoring problem in disguise. And existing provable low degree speedups are often demonstrated over the worst case instance of a problem. And this is another massive limitation. Because once you look at industrial optimization, you realize that the worst case bound you can put on a problem, say, my favorite example here is the maximum independent set problem. The maximum independent set problem, even for a random graph, no one knows how to get a better than half approximation ratio in polynomial time. So it's an extremely difficult problem, right? You should not be able to do anything, even if you draw just a random graph. However, there are examples of size like millions and millions that are currently solved by classical solvers. And those classical solvers perhaps use a lot of tricks. But there are integer optimizers that are available to all of us that you can run on your computer, and that will solve an independent set size problem of size, say, 500 way before I finish this talk. So we really need to focus on the real instance of a problem. So one trust that we've taken, even when looking at provable speedups, is can we prove what we call universal or every case speedups rather than worst case speedups? Like, is it possible to design an algorithm where you're guaranteed that you're always faster than the classical algorithm rather than only faster in the worst case? But the bigger problem is that the high overhead of error correction makes low degree speedups very hard to realize. And there's a famous paper out of Google Quantum, I think from early 2020, that sort of makes this concrete, where they say that with error correction as it was at the time, and error correction, of course, is an evolving field, if you have only a quadratic speedup, then to really see the quantum algorithm winning over the classical algorithm with error correction, the classical algorithm would have to run for a year. There are no classical algorithms that run for a year in practice. So this is not acceptable. However, if you can make the polynomial speedups bigger, say order 4, then you can see speedups over algorithms that run for an hour, and this is much more realistic. Well, challenge 2 is one could say, well, provable speedups are clearly too much to hope for, right? And the issue is with proof rather than with speedup. So why don't you try variational algorithms, right? So take a quantum ansatz and use gradient descent, a paradigm we know works very well in machine learning, optimize parameters of said ansatz, and then this ansatz is going to do all kinds of useful things. So one global limitation is that we don't have clear examples of what kind of useful things these ansatz will do if you optimize them. But there are more fundamental algorithmic limitations as well. Challenge 1 is that the cost of obtaining the gradient of a quantum circuit ansatz scales superlinearly with the number of parameters. This is in contrast to the situation in deep learning, where because of automatic differentiation or backpropagation, you can compute the gradient of a function in the same time that it takes to evaluate the function. But because of the quantum no-cloning theorem, you cannot do something like this with a quantum circuit. You're unable to store intermediate information. So if you want to use a million, like say 10 to the 6 quantum parameters, it's 10 to the 12 cost to evaluate the gradients. So this is a massive overhead over a million classical parameters with just a million cost to compute the gradient. There's the well-known barren plateau issue, which is that randomly initialized quantum circuits often have gradient norms that are decaying with the dimension of the Hilbert space in which they live. And there's been a lot of theoretical research over the last 3 years or so, and it sort of culminated in this paper by our group, where we showed that it's not quite as bad as all that. It decays not with the dimension of the Hilbert space in which the state lives, but with the dimension of the Lie algebra induced by the operators you use in your ansatz. The problem is that if the dimension of the Lie algebra induced by the operators in your ansatz is very small, then you can probably simulate the circuit. And this is a pattern that we've seen again and again, which is that the techniques that we have to show that an issue with a variable algorithm is not really an issue can also be used to lead to classical simulation. So finding something that can't be classically simulated, doesn't have barren plateaus, still an open question, and some people conjecture that there is no such system. And then finally, there are lots of spurious local optima, and we can avoid these provably, but we can only provably avoid them in the heavily overparameterized case. And by heavily overparameterized case, I mean number of parameters that is asymptotically the same as the dimension of the Hilbert space, which is again too much. So I'm not saying that variational algorithms cannot be used to do useful things, but if you have a construction, right, here are some theoretical obstructions you would have to get around. And then finally, maybe the most famous quantum optimization method is quantum annealing. And this is sort of very concrete, very clean. And if it works, I think gives us like interesting results immediately. However, large quantum annealing devices are yet to yield concrete speedups. I think the closest we have is a demonstration coming out of Harvard and QEra, where there was a speedup demonstrated over simulated annealing for the maximum independent set problem using neutral atom arrays. However, these speedups do not always persist against the best classical solver. So if your goal is to have a quantum algorithm be the champion for a combinatorial optimization problem, that is yet to be met. And finally, typically quantum annealing gets a lot of its power from the fact that you're doing something very natural, right? You're using a quantum system to do the thing that the system does. But this means if you want any sort of flexibility, then you need to come up with complicated embedding schemes, and these add overheads, which are often difficult to analyze. So your actual performance for any flexible problem family might be much worse asymptotically than you think at first. Okay, so what do we do about this? Right, so I'm going to quickly go over like 6 areas that we think are a focus, perhaps that help get around some of these obstructions. The first, and I think like this is something I try to convince almost every computer scientist I meet, is that we should focus beyond polynomial time algorithms. So in computer science, this is the paradigm we live in. There are problems in P, which are polynomial time. There are problems in NP, which if they're NP hard, then you cannot solve them because they're exponential time. So what we must do is come up with polynomial time approximation algorithms, right? For example, for an NP hard problem like vertex cover, there's a well-known approximation algorithm that'll get you a 2 approximation factor. However, in reality, no one uses polynomial time approximation algorithms. And the reason is that you can often do a heuristic that comes without any proof that may not be guaranteed to give you something better than a 2 approximation, but will give you something better than 2 approximation almost always. And most of the time, people just want exact solutions or global minima. They would say, well, how can you get global minima? This is clearly exponential time. Well, industrial problems are not living in the asymptotic regime, right? So say I want to solve a portfolio optimization problem that's going to be integer minimization, NP hard, size is probably 500. At 500, you can imagine solving integer minimization in a few hours. And in fact, with the correct setup, you can imagine solving it in a minute. And you will often see that it gets solved in a minute. So an exponential scaling is not always a killer. So you can have a quantum algorithm that takes exponential time, and this can still be useful. And in fact, this is what you need if you actually want to convince classical folks that you have an algorithm that's faster than their algorithm. Second, if you restrict yourself to polynomial time, you can prove lots of theoretical obstructions. So I'm going to go on to talk about QAOA in a second. There is a whole sequence of papers that show, well, QAOA viewed as a polynomial time approximation algorithm in a long list of settings, including, say, any constant depth setting for max cut, will do worse than the best classical approximation algorithm. So there's no point even looking at it. However, you could consider quantum speedups for exponential time exact algorithms. In fact, you could use QAOA as an exponential time exact solver and get better scaling than what people know how to do classically for some interesting problems. And I will go on to talk about this later today. We can try to find new evidence for the power of known heuristics, right? There's a perception that heuristics are interesting in the regime where you don't have provable guarantees. However, the vast majority of classical algorithms are actually just simulated annealing and taboo search and genetic algorithms and a variety of local meta heuristics for which we have no provable guarantees outside of very limited cases. However, these are very powerful, and there's a lot to be gained if you can understand the mechanisms by which these algorithms work, even if you cannot give guarantees end to end, right? And for known heuristics, there are several advantages. First, you can benchmark at non-trivial scale on near-term hardware. You probably cannot see any advantage over a classical algorithm, but you can benchmark them. It is important to study parameter setting to avoid the variational issues that I described earlier. So you never want to take QAOA and then use the quantum hardware in a loop to train all of its parameters. At algorithmic scale, this is very unlikely to work. You run into all these issues, you can't get the gradients and so on. But we argue that this is not necessarily a massive problem, right? Because the way you, say, use simulated annealing to solve a spin glass problem is not to parameterize your temperature schedule and then train all these parameters repeatedly in a loop until you get the best possible performance. You use some sort of combination of domain knowledge, benchmarks on smaller problems to get a good temperature schedule, and you assume that this schedule works, right? So we need to do enough studies to convince ourselves that this phenomenon, which we call parameter transfer, happens also for QAOA. There's a clear connection with adiabatic quantum computing, which is a very heavily studied subject in both physics and early quantum computer science. And we can leverage this to understand some mechanisms. And there have been some clear evidences that QAOA used in this setting does offer scaling advantage or for a classically intractable problem. If I have time to go into the details of one of our papers, I will talk about this. The third opportunity is to find new mechanisms for optimization, taking inspiration from quantum dynamics, right? So rather than starting with a classical system and looking for parts you could do faster using quantum algorithms, just start with a thing that is quantum and has no classical analog and find a way to analyze it and find a way to benchmark it. So one example, and this is getting more and more popular, is counter-diabatic driving. As many of you know, adiabatic computation guarantees the global optimum. So if you can do adiabatic evolution, you have an exact solver. However, the evolution time is going to get very, very long. And there are some well-known constructions that show, due to some many-body localization issues, adiabatic computing for certain combinatorial optimization problems can be slower than brute force search. However, that does not mean that quantum dynamics is slower than brute force search. And you can leverage many techniques that are typically termed shortcuts to adiabaticity to mitigate the diabatic transitions. And a popular example is counter-diabatic driving or local counter-diabatic driving, where you add a term to your time-evolving Hamiltonian that is specifically tailored to reduce the diabatic transitions out of the ground state. There is no clear theoretical analysis of this yet. However, it has been very fruitful. We ourselves have done some work that shows that counter-diabatic driving does help for some problems we're interested in. And additionally, there is some work by Jonathan Wirtz et al. That shows that the QAOA optimal parameters actually resemble adiabatic plus counter-diabatic corrections more than they resemble just the adiabatic schedules themselves. Opportunity 4, and more than opportunity, I think this is there's something to note, which is, if you're interested in optimization problems that we see in finance, these problems are going to be highly constrained, right? So there's budget, there's risk tolerance requirements, and like a typical example of financial optimization problem is going to have, say, at least the same number of constraints as the number of variables. A lot of like quantum dynamics, which so I've been talking up so far, the limitation is that it's not clear how to handle constraints. And people think that you can always add a penalty, and this helps you understand handle constraints. However, in classical optimization, it's well known that you can't do anything useful or at an industrial scale by just adding a penalty, and you need to be a lot cleverer than that. So there are a number of things you could do. You could try to use constraint preserving dynamics. So if the constraint set has a particular structure, you could just make sure that your dynamics never takes you outside. I think this is the best if you can do it. And there are some other suggestions, like a couple of things we have worked on are using quantum xenodynamics to repeatedly project the dynamics into the constraint set, or to use what is called constrained Hamiltonian optimization, which uses like some forms of non-abelian dynamics to explore the constraint set very quickly. We need to think about how to integrate fault tolerance. As I described, our main aim is to run things on early fault-tolerant quantum computers, and in order to do this, we need to start thinking about architectures and how these are going to translate onto these machines. A common example is QRAM, right? So often in quantum algorithms, we will assume the availability of oracles that are data dependent and use those to prove certain speedups for machine learning or linear regression or so on. But it turns out that, and I think the reason why this is caught on in the theoretical community is that if you look at it just as sort of an abstract construction, it doesn't seem that different from an abstract quantum circuit, and the asymptotics are not that bad. However, once you start looking at the cost of error correcting a QRAM system, you quickly start to realize why experimentalists get really nervous every time you say the word QRAM. And so any algorithm that we construct has to be cognizant of these things. And also, we should think about, if you're going to run an algorithm on hardware, early fault tolerance probably means that we can't run everything fault tolerantly. But is there a useful way to run a subset of operations fault tolerantly and still get something better you would get than with just physical operations? And then finally, and perhaps this doesn't a lot to do with quantum computing, is you could look at quantum and spiral algorithms. And as a group whose main job is to look very carefully at classical computational processes and then think about whether a quantum algorithm can do better, the burden of proof is on us to say that a quantum algorithm can do better. So oftentimes you're forced to look at classical algorithms more carefully than someone without that burden of proof would have. And like often this search will reveal something you could do classically that is better than what people were doing before. And this is faster than your quantum algorithm. But this does not have to be a sad story if you're just interested in better algorithms. It is a very sad story if the thing you started with is a completely useless thing, is just constructed for the purpose of demonstrating quantum speedups. However, if you start with a useful thing, you've made the world a better place, although perhaps not in the way you originally intended. Okay, so I'm going to go into the details of one work that we have done that covers a number of these themes, although not all of them. And here, the goal was to evaluate the potential of the QAOA. And this is the work I've been referring to several times during this talk, where we try to establish that there exists some problem where QAOA as an exact solver gives you the potential for an asymptotic speedup. So we studied what is called the low autocorrelation binary sequences problem. Now, if you're not interested in signal processing, I imagine that none of you has heard of this problem, and this problem has no importance in finance. So the obvious question is, why are you studying a problem that no one has heard of, right? And the reason is that there are very stringent conditions that a problem has to satisfy if you want to make claims like a quantum algorithm is going to solve this problem faster using simply benchmarking, right? Because at best, even with a lot of effort, you're going to benchmark up to the low tens for quantum algorithms. How can you make any claims whatsoever about separation from classical algorithms? The number of problems. First, and we've discussed many of these problems already. First, there's this worst case versus random separation. So what if you find that something that classical algorithms are slow at, but they're actually fast at all the relevant things? Second, classical algorithms are really, really good at small problems. Asymptotics typically kick in much, much later. So, and finally, it could be that you just made up a problem, right? And the only reason why you're beating classical solvers is that no classical person has ever cared about this problem. If they did, they would beat you next week. So this problem, the low autocorrelation binary sequences, I argue, gets around a number of these. First, while it is not a very well-known problem and is not important in finance, this is very popular in the signal processing community. And the binary sequences with these properties have many useful applications. So you can find 60 to 70 papers starting from the 80s that have looked at the problem of finding approximate or globally optimal solutions to exactly this problem. So this is very heavily studied. Second, there is just one problem at every problem size. So when we call this the labs problem, I'll just call it labs from now on. If I say solve labs at size 72, that means solve one specific problem. There are no problem parameters. So there is no worst case versus real case separation. There's only one case. And the cost function here, which I won't bore you too much with, it's kind of what it sounds like, right? So the autocorrelation is you take every index and then you compute its correlation with every other index, right? So these are the SI plus K terms. And then you compute the sum of the squares of these correlations. And this is so you want to make the total autocorrelation as small as possible. And the labs problem is, given a length n, find a sequence that minimizes this energy. Why is this interesting? Classical solvers scale extremely poorly. So your exact branch and bound solver scales as 1.73 to the n. For comparison, your exact solver for independent set scales as 1.02 to the n. So at a problem of a size 100, you have no hope of ever in 50 years of running the branch and bound solver, where you can easily solve a maximum independent set problem. Even with heuristics, such as taboo search, you can go only up to 1.34 to the n. And as I said, this is heavily studied. Like, these numbers come after decades of effort and optimization. And another thing that is very important to us is that below n equals 40, you should see the scaling that your asymptotic says you will see. So I can tell you that for branch and bound, if you plot the performance of the best classical algorithm from, say, 10 to 50, and you plot it on a log plot, you see a straight line with that slope. So you already see the scaling. And it's the same for heuristics, but maybe you have to start at around 26 or so. Below that, heuristics are relatively flat, but then you clearly hit this exponential wall. So I make the claim that this problem actually gives you a regime between 26 to 40, where if you find out how well a well-optimized QAOA would do, you can actually make a claim about asymptotics because you're already seeing the asymptotics for classical algorithms. And then finally, one point is that labs does not have a structure that is easily exploitable by local solvers. So there is a clear reason why this problem is hard. This plot we have below shows you the correlation of Hamming distance and And as you can see, for max cut, right, it's pretty well correlated. For labs, you have this spike, what's called a golf course landscape, which means that your Hamming distance tells you almost nothing about your objective. In particular, for near the global minimum, you have things that are many flips away that have nearly the same objective. And this is what leads to vanishing gaps, both for classical and quantum algorithms. All right, and here's a plot of the best that classical algorithms know how to do for this problem. I don't know if you can see the difference between black and gray on the screen from where you're sitting, but the gray dots are exact solvers, right? So these are global optima. Sorry, the black dots, so small sizes. The gray dots are where exact solvers no longer work, but you can get something with heuristics. The black line, the solid black line, is a trivial solution. So for the labs problem, you can construct some explicit sequences that give you, say, 6. So running optimization for a year of compute time and getting something worse than 6 is no good. So that's why the graph cuts off. And this dotted line is what we conjecture the actual solution should be like. So you can see that the gap is quickly increasing from the best that classical solvers can achieve. So in addition to what I told you before about the asymptotic scaling, this is additional evidence that this is just a hard problem to solve. Less than 200 qubits, if you can do QAOA properly, and this is, of course, without error correction, like it's 200 logical qubits, should be sufficient to tackle classically intractable instances if you can do better. So what we do is we perform exact simulation of QAOA with up to 40 qubits. To connect with what I said before, I should note that this is not an approximation algorithm. Instead, we are optimizing the QAOA for overlap with the exact solution. We're doing this at small sizes, conjecturing that this is the right schedule, using this schedule at larger sizes. So the idea is to run the QAOA and then just measure it and sort everything you see, and take, of course, do quantum minimum finding at the end if you wanted an additional quadratic speed up over whatever your random sampling would give you. So we performed the exact simulation, and this simulation is at supercomputing scale. We use up to 1,000 GPUs per simulation on the Polaris supercomputer. We observed that QAOA by itself scales much better than the branch and bound solver. Interestingly, not only does it scale better than a branch and bound solver, it scales better than the best quantum algorithm for branch and bound, which you could never imagine running or simulating. And then QAOA combined with quantum minimum finding also scales better than the state-of-the-art heuristics, which in this case is mimetic to boot. So we believe that this is the first strong evidence that QAOA provides an algorithmic speedup. For strong evidence because there was an earlier work by Ashley Montanaro and Sami Boulabani where they showed something similar for SAT solvers. However, those experiments were in the regime where SAT solver asymptotics don't yet kick in. So you could potentially question that on those terms. But that was also as an exact solver. And to lead to this, some interesting things that come out of it is first, we did a large demonstration of QAOA on continuum strapped ion processors. We believe this is the largest hardware demonstration of QAOA up to date. And to make this work, we actually use a novel error detection scheme. So this work is older than the recent explosion of work on fault tolerance. And I'm not sure that, we still use a lot of T-gates. But just using 2 extra ancillas and a custom error detection scheme, we were able to bring the performance to a regime where you can actually see the P equals 1 QAOA using the parameters that we actually derive from simulation, working on an actual quantum computer. So this is of interest, but this is not meant to demonstrate that you can run the algorithm today. We developed what we think is the fastest QAOA simulator that exists up to date. This is a supercomputing scale simulator, so it is written to run on GPUs and with additional optimizations to work on the Polaris supercomputer. The central idea here is that when you're optimizing something like QAOA, you don't need to do everything as gates. In fact, like half of the operations in the circuit, which are just cost rotations, you can pre-compute the cost, pay with space instead of time, and just use those as, insert them using what's called the fast Welsh-Hadamard transform as your circuit is proceeding. And this shows much better performance than state-of-the-art state vector and tensor network simulators for this problem. And I will note that going up to 40 here is a challenge because we need state vector simulation, Like I said, we're using it in exact solver mode. So we need to compute what the overlap with the exact solution is. So it does not suffice just to measure an expectation value. And finally, there are some interesting, I think, mechanism questions that we were also able to answer as part of this effort. Two of these that I will highlight is one natural question that you have in QAOA is, what should be your starting state if you want the heuristic to work well? If you were using the adiabatic algorithm, then the answer is obvious, right? You take whichever Hamiltonian you can do easily, or whichever Hamiltonian is cost independent, and you start in the ground state of that Hamiltonian. So in this case, in QAOA, you call this the mixer, right? So the cost independent drive. However, like the QAOA is clearly very different from the adiabatic algorithm. If you're running QAOA with p equals 2, you're obviously nowhere near Trotter regime, so you're not even approximating adiabatic or any quantum dynamics. So you can ask the same question, like, does it make sense to start in the ground state of the mixer? And we show that alignment between the initial state and the mixer Hamiltonian does indeed improve QAOA performance, even at very small depth. I think even at p equals 1, this holds. And it's actually smooth, so you get better and better fidelity with the initial mixer ground state. You do better and better. There is not yet a good theoretical explanation for this. If someone has a conjecture, I would love to hear it. And I think this is an interesting thing for the community to look at. And this we were actually able to validate at a 32-qubit scale on Quantinuum's H1 device, performing the largest hardware demonstration of portfolio optimization with QAOA. Another interesting aspect when it comes to QAOA mechanisms is parameter setting for QAOA relies on the notion of parameter transfer. How many minutes do I have? A couple of minutes? Yeah, I'll close with this. Right, so we need to be able to use parameters that conjecture from small sizes, and we need to use them at bigger sizes. This is easier if you're working with unweighted problems, where you only have one way for the problem to be different, which is problem structure. However, if you're working with non-integer weights or weighted problems, then it can get, you clearly don't expect that if I give you a max cut and just like double the edge weights on all the edges, that you can use the same parameters. So you would like to analytically be able to transfer the parameters. And here we actually derive an analytically optimal transfer scheme. So if you give me optimal max cut parameters, then we have provable optimal weighted max cut parameters. And this allows us to do exactly the operation that we're looking at. And interestingly, these parameter schemes also work for portfolio optimization without proof. So let me skip past everything else. And just let you know, here's our quantum computing team here. Actually, this is not even the whole team. We are growing very rapidly, so this is missing a few people who joined this. And we're still looking for candidates who are interested in doing the kind of work I've been describing today. If you're interested, please do reach out. You can find out more about our open positions there. We do not require any prior familiarity with finance or financial use cases. I'm evidence of this, as I have none of either. And here's where you find out more about us and about quantum computing for finance. Thank you.
Thank you. Thank you. Excellent talk. We have time for questions. So you mentioned, I think the coverage of the algorithms was excellent. You mentioned a little bit on hardware. So I would like to ask, so what hardware you would follow in terms of testing the algorithms you described? So you mentioned, I think, Query, Quantinuum. What else you're looking at following?
Right, so we are an algorithms team, like I said, so we don't have like any specific inclinations when it comes to hardware. You may have seen that a lot of our demonstrations are on Quantinuum hardware. This is partially informed by what we currently use hardware for, which is for benchmarking and proof of concept demonstrations. So fidelity is more important to us than anything else. So we end up doing experiments largely on the highest fidelity. However, we try to be, every time a new hardware paper comes out, we look into what it can offer. And I think a lot of directions are very interesting.
All right, thank you. All right, then thank the speaker again. And we have our next talk by Professor Gerhard Klimek. while we're setting up, I will introduce our speaker. Professor Gerhard Klimek is the Elmore Chaired Professor of Electrical and Computer Engineering at Purdue University. And he leads 2 research centers in Purdue's Discovery Park. He is also Vice President for Academic Information Technology and Deputy Chief Information Officer. So previously he worked at the Central Research Laboratory of Texas Instruments and NASA JPL Caltech. His research interest is in computational nanoelectronics, high performance computing, and data analysis. So, and with this, I would like to join me to welcome our speaker.
I want to tell you a very different story from what you might have heard in all the other talks today. It's about making other people that are different than you successful. And I joined back on my second tour of duty Purdue about 20 years and 6 months ago. And we had created, Mark Lundstrom had created NanoHub. And it was a portal, like many other portals that existed, that make people like Mark successful, like a computational scientist sharing something else with a computational scientist. But the real power of portals is to enable other people that are different than the creators of a portal to make them successful, to really propagate your science into other areas. And that was the goal. And so I arrived literally 20 years ago, and around this time, I started to lay out what a user experience should look like. It should be real tools with real user interfaces running inside a browser. And it should be enabled for other researchers and educators to use the tools that I built prior at TI and at NASA, and other people to enable others to share their tools. So we created a cloud before a cloud was a thing. We created apps before the iPhone created apps, and we wrapped apps around scientific tools where you don't have to read the 200 or 300 page manual to make a tool worthwhile. So I'm going to tell you a story where you can go from theory, and I don't know why these animations work, but let's see. Yeah. So where you can go from theory that you can scribble on boards to computational science to have global impact. And here's an animation of NanoHub users. And as you can see, the world doesn't sleep, maybe starting at 3 a.m. But people are interested in nanotechnology, and these are NanoHub users. And I'll talk about how we translate that towards Chips Hub and to a Quantum Hub. So here's an annual view of NanoHub users. So wherever there's a civilization that can light up the night sky, there seems to be interested in high tech, in nanotechnology and simulation tools and lectures. So what were the challenges? What were the fundamental obstacles we had to overcome? People had a deep belief that you cannot use simplified, easy access tools for research. People felt that is impossible. Also, they felt you can't really introduce full-fledged research tools in education. And there was a fundamental question on how do you share results, how do you make computational science reproducible and publish data. So those were the questions, and the bottom line of what I want to tell you is we changed those perceptions. People now believe in my field that indeed you can use other people's research tools. We created new tools. We can prove to them people are using NanoHub in education, and I'll show you a lot of numbers. And we created a new type of publication that is now literally listed in the Web of Science that didn't exist before. So those are three fundamental changes in belief and in thinking, and that's what you call a paradigm shift, when you change people's expectations. And now I want to translate that into Chips Hub and Quantum Hub, and it's all about community building, ease of use. That's the key question. You have to think differently than serving yourself or people like yourself. How can I make my stuff useful for others? And it's in that ease of use. So here, NanoHub in a nutshell, there's 170 tools, 170 courses online. We have about a total of 15 million visitors that utilize this material. We have over 700 tools and apps on NanoHub. These are full-fledged, real scientific tools and apps. And we've served over 250,000 people that would have never, ever used those kind of tools before. And I'll give you analysis that I find pretty cool at the end. We serve 43% of all US technical universities. We serve 56% of all technical minority serving institutions. We are getting out and we have impact in schools that normally would be underserved or not enabled to use these tools. All right, so what was the challenge in research? People thought you have to build your own tools in order to do research in the area of nano. They're not chemists where tools were established already at the time 20 years ago. They also felt no experimentalist will ever touch this because they always need to have their hands held in order to use these kind of tools. No experimentalist will ever touch these tools. And by the way, you can never provide the compute that is needed for your vision that you present. So that was a firm belief. And what I did about 15 years ago, I showed them a social network chart, not with 2,700 dots, but with 200 dots. Each dot is a paper, and the lines between the dots are common authors. So these authors actually form a social network around NanoHub and the usage of NanoHub. And when I showed the first chart, actually in Berg 15 years ago, you know what the first response of my peer reviews were? Okay, you can do research, but it can't be good research. It is so deeply in people's mind that if something is not possible and you try to prove them wrong, they find other reasons why they want to reject you. So we started tracking secondary citations to these papers. And right now we're at something like 84,000. If you translate that in an H index, that's pretty high for a virtual person like a hub that exists for 20 years. So indeed, you can enable and empower people to do research. The next question, 71% of these papers have nothing to do at all with us. And if I ever talked with you and showed you NanoHub and gave you some guidance, you're one of us. So it's very conservative. There's papers where there's a bona fide experimentalist. We actually go through the papers and figure out, is this person a theory person or an experimentalist? So real papers with experimentalists, papers with experimental data. And what is really cool, there's now papers in the education literature that explain and analyze how this kind of site can be used for education. That's kind of these dots you see here. These are the education papers. These are cyber infrastructure papers. Red ones are nanoscale papers. So these dot colors mean something. So we analyze this stuff and try to connect to these authors. All right, so you can do it, research. It's about building a community that grows slowly. And then the next one was, you can never do this for education. We knew some people use it in their classes. And the next question is, it was a completely, or is a completely open site. Anybody can log in. We don't require that you come from a specific university and with a specific law. It's completely open, you just have to register. And if you look at registration data, it's kind of sporadic of what's in there. So how do you know that people are in classes if nobody tells you that you're in the class? So that's a reasonable challenge. So the way we do that is we develop analytics, which are now sort of commonplace, but at the time they were novel. So what we do is we look at people behavior. So on the horizontal axis, you see time. Each dot is a person with a particular action or use of a tool on a particular day. So on the top row, you see a group of people that uses a yellow tool. Then there's a group of people that use an arithmetic pattern, the orange tool. There's a spring break, and there's one outlier. There's people that use tools multiple times, different tools in a rhythmic pattern. We can actually measure classroom size by people behavior. And therefore, and then we can follow up by point checking with some faculty members. Did you teach that class? How big was the class? We can't ask for FERPA information, right? But we can track down that there's classes. And today, we're about half of the people that run simulations are in formal classrooms. That's 11,000 people each year. So overall, 100,000 students used tools they would never, ever have touched. A completely different group, different than me, a computational scientist that runs on 200,000 cores at Oak Ridge or something, right? Very different people. And 16% of these users in total are at MSIs. All right. And then faculty members, we go after them, try to keep them on board because they're user multipliers. They bring in a class for 30 people. Next semester, they come back again. So we hold special workshops for faculty members to keep them engaged. All right. The next thing is people, my peer reviewer said, you can't do both. You can't do education and research. You have to really decide, what are you doing? And they said at one point, they give us homework assignments every night, every site visit at 6 p.m. They give us 10 questions, and then they say by 8 a.m. we need an answer, and you report back to the panel. That's how engineering research centers are run. So one time they said, you have 121 tools on NanoHub. Which ones are research? Which ones are education? I'm like, I'm not the author. How would I know, right? So we guessed something, how complicated the tool looked and whatnot, right? But what we really have now is a way of developing a metric. We can measure how many people use a tool, where each dot is now a tool in education, like how many classes, how many students. And on the vertical axis, we can measure independent users that come to study, that publish, or that just study by themselves, right? I can rank them there. And then I actually sit on 20 years worth of data. I can have a tool be born in the origin, and I don't know how that tool will be used, right? And then I can measure whether that tool shows up in a classroom or not. So early on, we had these web forms that were terrible user experience. I hated them. And this is when we created the cloud, where we started to see way more tools that are much more usable. The user numbers and the tools grew significantly. And you can see how the dots start to migrate from research use or individual use into systematic education use. So the assumption that you can have to decide you're either research or education is total bogus, which of course we knew, but we couldn't prove it. So now we actually have analytics to show that. And what's really cool, people talk about translational work, right, all the time. Well, this is a translational graph, right? How we translate tools from research and educational use into classroom use. And sometimes actually the dots come from education use and are getting adopted in research. So it's not just one way. All right. So the answer is we do both. And the last thing I want to highlight on achievements, and then I'm going to give you some examples, are how can you change how tools and data are published? So in 2016, the Web of Science approached us as the first gateway and said, would you be interested in listing your tools and your digital assets in the Web of Science? So we worked with them, and they probe us every other day. They look at our inventory of tools, and they translate that into a listing in the Web of Science. So we became a publisher of tools, and those can be cited, and they are referenced in the Web of Science. Not just tools, compact models, and we have our data fair, which is findable, accessible, interoperable, and reusable, which is a big deal these days on actually sharing your data. And then we can couple this data to AI systems to actually explore. So it's about building community, and I want to highlight now let me just summarize. Those three things, we changed what people thought. So again, I want to reiterate, it's a paradigm shift. So now I want to look at ease of use. So one of the early industrial tools, that is actually a design tool that came from Bell Labs. That tool designed transistors that really worked. And in order to use this kind of tool, you have to speak Padre. It's its own language, right? And not everybody speaks Padre, and there's a manual that's about 200 or 300 pages. That's what you need to learn in order to use this tool. All right, we have about 500 users per year now that are willing to learn Padre, right? And we just recently had the full-fledged Silvaco tool set, commercial tool set that sells for like $100,000 a seat if you're on commercial side. We have that running for free for education in NanoHub. And within a year, we have over 1,000, actually now it's 1,600 users. So graphical user interfaces are important rather than the old scripted stuff. But we can do better still. What we did early on, we built apps. So Padre can simulate transistors, for example. But it's hard to configure the tool. But you can make a family of devices that are transistor, that might be a PMOS, an NMOS, a double gate transistor. And anyone can modify 20 parameters or 30 parameters on this particular class of devices. If each parameter just had 10 variations, that's a huge design space. And you don't have to speak Padre, but you can explore a huge design space without being an expert in Padre. Yet, the space is huge. So real work can be done, and you make it easy. So we did that for MOSFETs, for multi-gate FETs, for MOS capacitors, PN junctions, BJTs, and a general diffusion model. We can generate 17 times more users on these apps than on this specific tool set. So I can reach way more people. The interesting thing is, if I look at the number of jobs they run, once you're an expert, you tend to run 4 times more jobs, which is exactly what you want. You teach people about the concept of what can be done, maybe they get their answers easy, and then they want to jump into the full research side, and they run more jobs, which is the transition of what you want to achieve from, say, novice intro user to expert that wants to speak Padre. All right. So let me highlight something that you can do with a tool like this that you will never, ever see in a textbook, at least not the traditional textbook. And it's the simple, stupid PN junction, right? Everybody has done this if you're an electrical engineer. And here's a page from Pierre's book that we use for teaching here. And what you see are equations that are derived in 1965, right? Beautiful, and you can explain exactly one part of the IV curve. And so you can explain this one slope right here on how the current goes up exponentially when you ramp up a voltage. Now, in this book, in Pierre, you see this sketch that, well, here's the ideal thing I know how to calculate, and here are all these other things that are really happening. And when it comes to explaining those, the math vanishes and a lot of prose appears. People waving their arms, yeah, you can imagine there's these effects, and if I just knew how to calculate that, then we would be good, right? Now, what could you do with a real tool? So here is a real tool. That's our PN junction lab. And under the hood, it ran a Padre simulation. And I'm just visualizing a result of here. This is the one thing you can calculate. And you can clearly see as you ramp up the voltage, you lower the barrier. And this is how the current goes, ramps up exponentially. Now, what happens up here? So up here, there's something that you will never see in a textbook, at least not calculated in this form. And what you see is really there's a resistive drop. The current is so large that it can't be sustained by these electrons that are in the structure. So Actually, students brought this up in my 606 class, showed it to me, and then said, well, let's look at this, right? Current is proportional to charge, to the mobility, and the gradient of the Fermi level. So here there's a gradient of the Fermi level because, well, you have to get the gradient in order to stay in the current. So what can you do to get rid of this gradient? You can put in more electrons, right? You can dump in, with doping, a factor of 100 more electrons. Very doable. You can go from 10 to the 15 to 10 to the 17, very feasible to do. And this is the IV you get. And indeed, you see that there's less of a resistive drop, right? Exactly what you want. But you also see down here, somehow the current got a factor of 2 smaller. You dump in 100 times more electrons, yet the current goes down by a factor of 2. Why is that? Because you reshape the barrier here. You have a depletion region that is very different, and you can visualize it and then understand it. Okay, so that's cool, but what if I wanted to make the device carry even more current? So what you can do is you can make the device shorter, right? I can make my barrier shorter, and you see the current go up significantly. This is exactly what we do in modern transistors. We make them shorter to get more current out and have more efficient transistors. So on this simple little PN junction, I can explain how transistors turn on, how they scale with different doping, and how you can make them shorter and have different current flows on a simple PN junction. And anybody can do it. Any teacher can do that, right? All right. Now, as I mentioned, this came out of student discussions, and I actually, in my 606 class, I replaced all of the exams by projects where they design a quantum dot photodetector or they design a nanowire transistor. And this is the feedback I get from people that are the non-standard students that really embrace more interactive embedded learning rather than the textbook and deriving equations. All right, so let's talk about fair data. All of these tools have their fair data shared, and you can feed that into a database. Now we have a database browser where we can look at old data. We sit on some millions of simulation runs that we store. And Alejandro Strachan, my partner in crime and NanoHub, is using that for teaching data science and usage in his material science classes. He designs experiments where he can predict which experiments would be the most advantageous to move forward from, given that the data that you have on old experiments. And basically what we do is we have these complicated tools, either in material science or in devices, and we abstract them and parameterize them, right? We have working input deck, working classes of devices, we give it parameters, which is this huge design space which can then be explored by AI. Now, you might think we are crazy in doing this kind of stuff, but that is exactly how industry works too. If you look at industry where they design circuits and systems, there's one person in a team of 20 that will design a flow. This is a rough design of a circuit. The other 19 will basically optimize around parameters through scripts. They optimize the original design to really home in on a structure. So industry does that already. It's just we don't have access to this stuff. But this is the common practice. So they have their own results database that they optimize, and they do that in the architecture side. Packaging and systems is a bit more complicated. So the plan for us now is to actually use industry strength tools to really do this not just for nanoscience here, materials and devices, to do this also for circuits and systems, and really scan that to a different class of users in a different user scenario. All right, so that being said, we hold workshops and to enable faculty and others to participate. There's large attendances. We have partners in Scale and in MEST that actually share their content for workforce development on NanoHub. So we get new content in to feed the monster so people can eat in this monster. And this is where we stand right now on NanoHub. So these are the numbers. And I want to show you next something that I think is cool. the analytics and the market space for expanding into what's called EDA, electronic design automation. So consider the Carnegie classification of universities. You can download it from various sites. There's about 3,600 in there. If you take out medical, legal, religious, art, cosmetic, all these universities that are not technical in our class, you end up with 2,082 universities in the US that have some .edu. Okay? And those are 151 R1s. Those are high research university like Purdue, Stanford. There's 150 of those. Then there's R2 classification that have medium-sized research, and R3s that have research, but it's not highly established. They don't get a lot of research grants. And then there's about 1,600 community colleges and non-research universities. Okay, and you'll see those in gray dots. All right, so let's look at the future of semiconductor device design, circuit design. So people believe that you must be able to use these type of tools. When students go to industry, that is the tool experience they will have. If you ever used Photoshop, you remember that the menu, pull-down menu with a pull-down menu and the pull-down menu and the little gray box that you click, and tomorrow you will have forgotten how you got there in order to do something to an image. I see some nods, yes. This is how good these tools are. They're not user-friendly, they're user-hostile. It takes literally years to go into the depth of a tool, and it's very hard for people that learn Cadence to go to Synopsys, for example, and vice versa. But either way, you need to train students on this, and there's a big challenge. We have a shortage of about 40,000 semiconductor engineers that are supposedly doing this. So I've been working with some of these vendors, well, actually all of these. I have commitments to have their software running in ChipSub. Two of them shared their academic license with us, like who they have licenses with, the universities, right? So you see mostly red dots. In fact, 82% of the 150 R1s are in these two ovals. So these vendors principally serve the high-end universities, and a few greens and a few blues. And their growth is incredibly hard. They can't grow much more. And the reason is, it's actually hard to get the licensing done. It's hard for some universities to pay for the licenses, even if it's 4,000 or 5,000 bucks. Some people just can't afford it. Some university can't afford it. And they don't have the ways of actually have hardware that is always running, always available for students to use or designers to use. They don't have the IT staff to install this. I know software, trust me. I have a hard time installing this stuff. It's incredibly painful. It's not like out of box and you plop in your CD or download it, no. It takes a week or 2 weeks of an expert to actually install this stuff. And a normal university out of the 1,600 doesn't have that kind of IT staff. And mostly, many of the universities don't have faculty that could actually embrace this technology and teach it. So you have to have material that teaches the faculty to bring them on board to create those. And the interesting, so basically I would conclude the rich universities can do this, but not the normal universities. Now, the interesting thing is that NanoHub does exactly that for many other tools. In fact, for 700 tools. So let's look what this NanoHub universe looks like. So these are 889 universities that have used NanoHub, where they have at least one user at that university. And you can see we completely encircle, except for some 8 universities, we encircle all of that customer base. So there's strong overlap. There's a good reason to believe that universities that change their curriculum to use NanoHub would be willing to change their curriculum to include EDA. So that's our opportunity. What's also striking is that there's a lack of diversity. So if we serve 210 MSIs, these vendors serve some as well, but we have a much broader scope. And There's also, outside of NanoHub, there's a whole lot of MSIs, but the honest answer is we really don't know what the technical expertise at those universities on the right are. We know on the left, we have some 900 universities that are technically savvy enough and have interest to go on NanoHub and to use metamaterials, photonics, device technology, right? On the right, we just don't know yet. But interestingly enough, there's only red ones out here, meaning we've really captured virtually all of the R1s already that are on Nano. All right. So that's where these numbers come from. I'm going to wrap up now. So we actually have NanoHub, chipshub.org up and running. This is how it looks like. We have tools. We have apps for learning. We have textbooks and free courses. And we have impact stories, like similar stuff that I've been talking about today. So if I go into the tools, so I mentioned Silvaco, there's some other commercial tools, and we just turned on, we had Bell Labs tools, but in Silvaco, but we just turned on Cadence and Synopsys tools for Purdue users. So these are full-fledged tools that sell literally for $1 million a seat to industry. And they're running for free inside Chip. And on the app side, I mentioned to you that we have apps. We actually have an accumulation of apps where this is a semiconductor course, this might be a TCAD course, this might be Introduction to Quantum Mechanics, with apps that make it easy for a faculty member to find all this stuff. We have a virtual lab, and we're working with Dassault to actually have a digital twin of our lab that sits out there at Berkeley that will run inside ChipSub. Free textbooks and classes, so those are actually strong drivers inside NanoHub and ChipSub, and there's a group of free books. And this Supriya Datta, he just got elected to Academy of Sciences yesterday, announced, right? And he's already a member of Academy of Engineering, so you can kind of imagine that might be good material. And so with that, I'll conclude the ChipSub piece and want to show you that we are starting to have a quantum hub that does similar things to NanoHub, where you look at industry tools, educational material, courses, textbooks, partners. So this is sort of the aspirational list here of what to be done. And you can go there. It's actually quantumhub.org, or you can go into nanohub/groups quantum hub. And why would you do that? You could create apps in your Jupyter Notebook and educate users on your own research innovation. You can have quantum games running in there. You can share your course material and other resources. You can link or host your seminar. And hopefully whatever we record here, we will put on Quantum Hub as well and make available. And why would you do that? First of all, you could reproduce your own theoretical work. Most of you cannot. my computational theoretical work, if you ran something on some machine and unless you share that code with other people, they cannot duplicate it. In material science, it takes a half a year to duplicate a DFT-based paper, if you can ever succeed. It's a huge flaw. We're not talking about equations and that you can, we're talking about computational. So, fair enough. You can reproduce your simulation and modeling work. This stuff will be referenced in the Web of Science. It's another publication you can do. And you can effectively transition research software to a very large audience, and we give you the analytics to measure your impact. So I'm going to highlight this, and I'm going to make a fool of myself, I guess. This is what I have on my NanoHub member page. This is the number of NanoHub users that use my tools. So roughly 1,000 per month, up to 103,000 by now, and 50,000 are in classes. This is why I came back to Purdue, to make my tools useful for others. I have some 480 lectures, tutorials, animations, over 1 million users. Okay? And I know everybody worries about publications. I've published 2, but sometimes I wonder where the real impact is. Is it in the papers that people cite, or is it in the people that you touch and change their line of thinking? So, and that leads you to have global impact like this. So talk to Thomas Roth if you need more information on Quantum Hub. And this is the summary of the talk. So thank you very much.
Professor Klimek, thank you for the great, amazing opportunities and resources for research and education for faculties across multiple universities. We have questions?
Well, I would, it's rather comments. I would like to put some of the things in some perspective. So a large number of citations was used as justification of the impact here. I'm sure the impact is enormous, but I would also like to point out that a paper called Electrochemically Induced Nuclear Fusion of Deuterium by Fleischmann and Mons has several thousand citations. So to me, thousands of citations means lots of derivative work in a fashionable field. You pointed out that some of those existing tools have really large entrance threshold for people to use it. I'm not sure it's a bad thing. There is lots of good work, there's even more of noise. The point is that the higher is the technical competence of specific group, the more likely they are to use this tool with high threshold, and the less is the capability of the group, the more likely they are to use a user-friendly tool.
Yeah,
so
I heard these arguments before, and I have two answers to that. In the late 80s, the first SPICE simulation engines came out. It was one of the first open source tools. And people brought forward these arguments. Unless you understand the quality and capabilities of a specific linear solver that calculates AX equal B and gets you the X, unless you know that, you shall never use this tool and design a circuit. And that's bogus today. Yes, it is. And the second argument is, yes, we have about 40,000 deaths in car accidents in the United States. Okay? I don't think we're going to outlaw cars and roads anytime soon because some people do crazy stuff and get into accidents and misuse their cars. That's why you get a driver's license, and still people do idiotic stuff. Let them do idiotic stuff and let the figure out what is idiotic and what is good. But you should not prevent other people to even start to drive a car. Maybe they start a bicycle with training wheels, but give them those things. Sure, of course. I think the exam in the US is pretty weak, but okay. Right. My point is, Evgeny, you want to enable as many people as you can to enable to do their work and let them grow up. And not everybody starts being a Formula One race car driver. You've got to enable to give them training wheels. And yes, there will be fatalities in the figurative sense. And there will be bad papers, absolutely. There's no doubt. But there will be diversity of thought and diversity of capability. And I'm all for that kind of diversity. I mean, my Nemo code has 500,000 to 1 million lines of code. It runs on a supercomputer that most people have no access to. I can let students design nanowire transistors with that tool without having to install this frickin' thing, and they get results. And they're good results. Yeah, and sometimes they're bad, and let them fall and figure out what's bad. You need to learn how tools fail. I give them 5 tools, and I show them how they all fail at some point. That's part of the educational training. It's fine. Failure is an option. It's a good option to learn. That's my take.
I have another question. So you mentioned about workshops for faculties to get on board and learn about the opportunities. Could you add a little bit more information, especially for new faculties, how they could introduce these opportunities into their classes and education?
Yes, so on this course called Abacus, which is equivalent to my semiconductor device course here at Purdue, what we have is we call them recitation sessions for faculty. So we have an email letter that goes out, and last fall I did it again for the third time, and we have like 100 to 150 faculty members dial in at night, and you demo to them what these tools can do. And they're like, oh, I didn't know you can do this, right? They don't have time to explore that by themselves, right? And the students may not deliver that to them. So we have like a series of 8 workshops where I walk them through 7 tools, and then the associated material and animations and homework assignments. So it's a recitation for faculty. Going forward with Chips Up, we want to have literally teacher workshops for a week where you walk them through this tool set, because it's like learning Photoshop with a drop down, with a little click. So that's what we're going to have to do to really onboard teachers as well. And then on the data science piece with Jupyter Notebooks, so there's Ali has run these, and there's people every time at least, and then we record them and post them on NanoHub so you can learn by yourself. So the hard part is reaching the faculty members that could be potentially interested, right? So we had a secretary actually plow through literally all of the MSIs and look at the ECE department, which faculty member might teach devices, which one does photonics or E&M, put them on a list, and then try to market to them. Like literally doing marketing and offering, and it takes 7 times to get somebody hooked on something, right? So yeah, it's all the work that nobody wants to do.
Thank you so much. Thank you for the lecture. And the speaker again. Thank the speaker again. I think with this we conclude our morning session. We will have now 1 hour break for lunch and reconvene at 1 p.m. And with this also I would like to ask you to thank all the speakers in the morning session again. Thank you.
Testing 1, 2, 3. All right, if we can have people find their seats, we're going to get started with the afternoon. So our first talk this afternoon is going to be presented by Professor Joel Moore. Professor Joel Moore received his PhD from MIT in 2001 and joined Berkeley and Lawrence Berkeley National Lab in 2002. After a postdoc at Bell Lab Lucent Technologies, he was promoted to tenure in 2007 and is currently the Chern-Simons Professor of Mathematical Physics. His work is primarily on the theory of correlated and topological states of electrons in solid with applications to their transport, optical and quantum coherent properties. Areas of his scientific contributions include the theory of topological phases and their electromagnetic responses, the role of quantum entanglement and understanding quantum matter analytically and computationally, and the nature of quantum coherent quantum dynamics in many body systems. He has been an NSF career and Fulbright guarantee, and then selected a member of the NAS, a fellow of the APS, and Simon Investigator. He has more than 150 scientific publications with a total of more than 200,000 citations, including a recent book on topological phases of matter, co-author with Roderick Meissner. He's the former chair of the Science Advisory Board of the Kavli Institute of Theoretical Physics and has chaired and co-chaired reports for Department of Energy and the National Science Foundation. Without further ado, Professor Moore.
Thanks very much for the kind introduction. It's great to be back at Purdue and to see so many friends. It's great to be part of this excellent school. It is a school, and I have tried to put in some material that doesn't assume you already know everything. I certainly don't know everything about some of the things I'm going to talk about, because I want to try to talk about a problem at the boundary of condensed matter physics or quantum matter, what I do, and what people in quantum information are thinking about. Because it will turn out that a fairly simple quantum matter problem that actually grew out of an experiment in QSC at the beginning around 2021 is now of great interest to Google, for example, and is being simulated on their quantum computer. So I want to sketch a little bit, in general terms, what are we trying to do in quantum matter? But the main focus of the talk is going to be using this one problem, which is just a chain of qubits, if you like, coupled in almost the simplest possible way, maybe the second simplest possible way, because the simplest would be boring. A chain of qubits already does something very interesting that we only understood starting in 2019. And right now, studying that with materials, with atoms, or with quantum computer made of superconducting qubits, those are all competitive and are contributing to different parts of the puzzle. So that's where I want to go. This is work with a fairly large number of people. I'll try to thank them along the way. So if you like, the problem I'm going to talk about, you could motivate as sometimes in condensed matter, we get excited when we make a new particle. A great success of particle physics is you spend billions of dollars to break apart matter. We still don't understand quantum gravity that well. But all the other forces, we understand, these are the key particles that explain all the other forces. And they're, a reasonable number. You've got quarks and gluons and photon and Higgs boson and so on, but they're not all that many. And there are a lot of interesting kinds of particles that people hoped would exist, like Val fermions or anyons or whatever, that are not in the standard model, but that appear as excitations in solids. So one reason why we study, even if we're just interested in very basic physics, why we study quantum matter is that sometimes, the electron and the interactions between them produce some new kind of quasi-particle. Another reason, which is more like what we'll talk about, is a new kind of fluid. So for example, a superconductor is a new kind of electron fluid that no one guessed beforehand and really required about 50 years of understanding of quantum mechanics before it was explained by BCS. And both these particle and fluid aspects appear in the very simple problem, at least simple to write down problem I want to talk about. So I'm going to talk mostly about a new kind of fluid in the Heisenberg spin chain. Famously, the ground state of that was solved by a graduate student in 1931. The surprise, I guess, is that there were things we understood a lot. We didn't understand the dynamics until 2019. And it turns out that once theorists kind of made guesses about the dynamics, there were different ways you could look for that experimentally, and it seems to have been pretty successful. There are still a few open questions that I probably won't get to too much in this talk. I think I'll mostly talk about positive results, which is typical. And then I wanted to talk a little bit about, two other things I'll touch on along the way. So one-dimensional systems are much easier theoretically and computationally than higher dimensions, especially if you have some kind of translation invariance no disorder. A lot of QSC is interested in higher dimensions, and I'll try to explain why, and why there's some very exciting spin physics on the triangular lattice. In fact, I think what is the current best candidate for a quantum spin liquid is actually on the triangular lattice. That is where Anderson said we should look, but it's not quite the spin liquid he was talking about, and it's also not the same place on the triangular lattice. So I'll try to explain that. And then finally, I do want to touch at various points along the way, just why do computer scientists care about these spin problems? Why are both Google and IBM, for example, on the superconducting qubit side, working on the same kinds of Hamiltonians that people like me work on? And a big reason for that is, even though the materials I'll talk about are translation invariant, meaning all the couplings are the same and short-ranged, once you allow them to vary, you get to some very interesting questions in computer science. In fact, most of the most interesting complexity classes in computer science you can understand in terms of spin models. So, okay, when I say spin model, I think most people here know what a spin is. So the neat thing about it, or I'll give you a couple of neat things about it just to remind you if you crept in here from, say, classical computer science. So spin behaves in some ways like a vector. You could think of the electron as having a tiny magnetic moment attached to it, but it also behaves like a two-level quantum system. And of course, a qubit, that's the idea that by superposing the upspin and the downspin, I can make any state on the Bloch sphere. So those superpositions are, first of all, how I get from a two-level system to thinking about it as a vector, but also how I go from a classical two-level system to a quantum two-level system. So even one spin is a little bit interesting. Now, if you wanted to couple two spins, the most boring way would be a ferromagnetic coupling, and then the ground state is very simple. It's what we'd call a product state. So if I gave you this ferromagnetic product of two spins, and I asked you, okay, this is my pure state of two quantum spins, what's the wave function of spin A? You could say, well, it's up. That would get you a few points on the final. It's correct. It's not that hard. Suppose the coupling between the two spins is antiferromagnet. Then we know that in quantum mechanics, product states are a basis, but we can superpose them to make other states. And in particular, the singlet, the ground state of the antiferromagnetic interaction, that is an entangled state. And if I asked you, this is a pure quantum state, this is the best description we have in quantum mechanics for the two spins. If I asked you, what's the wave function for spin A? That's kind of a mean question, because at least if you're an undergrad or something, because there's no answer. The best you can do is write down a density matrix. It's not a pure state. Even though it's a pure state for the whole system, it's not a pure state if I just look at one piece. That's entanglement, one of the deep properties of quantum mechanics. So if you like quantum magnetism, things like antiferromagnetic interactions between spins, the reason why they get interesting is that this two-spin solution doesn't generalize very well. When you've got many spins, you can't put every bond in a singlet at the same time. That's related to something called entanglement monogamy. You can't be in a singlet with multiple people at the same time. So that kind of motivated why you might get a spin liquid. You might get kind of fluctuations of which singlet bond you're locked into. So that's, spin. Now computing, why might you care about spin? So very briefly, and here I should say, I'm going to show one or two slides from Veer Mulchandani, a faculty member at Rice. He was my student, so hopefully at some point I taught him a few things, and now he taught me a few things. I thought I would show his slide. The basic idea of maybe the most important classical computational complexity distinction is that there are problems where, at the moment at least, it's very hard to find the answer on a classical computer, but it's very easy to check the answer if you give it to me. You can rapidly check the answer. So rapidly check is NP, rapidly solve is P. And we don't know, but we suspect that those are different classes, that NP is a superset of P. But as an example, if you're asked just to find the ground state of the classical Ising model, which would be trivial if all the couplings were the same, if those couplings vary and are all-to-all, so in other words, if I don't have locality and I don't have translation invariance and the other things that materials sometimes have, then that actually becomes a very hard problem. In fact, It's a hard enough problem. It's one of the original problems that the great Berkeley computer scientist Richard Karp showed was NP complete, which means if you had a machine that would find the ground states of this problem for all couplings, you would have a very, very powerful computer, much more powerful than anything we have now. And in fact, that's kind of the spirit of the original D-wave machine idea. So I'm going to talk about other spin models and maybe come back at the end to the question of how do different spin models give you different levels of computational power? Because I find this a very nice way to think about all the complexity classes, or at least some of the complexity classes the computer scientists talk about. You can just put it in solid state language and say, this is like finding the ground state of this kind of spin model. All right, so now back to spin models from a condensed matter point of view. So how does spin behave in most materials, especially at high temperature? The answer is we often have an approximate conservation of one component of the spin, like maybe the total spin along the z direction is conserved. And then once you have a conserved quantity in physics, the most common way that it behaves is diffusion. So I think you've probably seen this diffusion equation before. I think you might have seen the solution. It's as though each particle does a random walk. And if you start with all the particles at one point, they kind of spread out. And to be precise, they spread out like a Gaussian. If I now want to convert that to spin language, and let's talk about quantum spins, but the idea is not all that quantum mechanical, we just would say that the total magnetization is now the conservation law. And therefore, the way that spin spreads out is kind of diffusive. And this is what many measurements like nuclear magnetic resonance or neutron scattering at high temperature tend to measure. You see a Gaussian spread of the spin correlator. And the dynamical exponent, this is a very useful concept to kind of analyze classical and quantum dynamics. Right. Z is how many powers of space are equivalent to a power of time.
There are three things.
So for example, in the Gaussian, we know that it's not like the particles have a velocity. That would be what we call ballistic, where space is linear in time.
Service rule, there's the
now x squared is like
rule,
t, or x is like square root of t.
And the first one can be created by anyone by clicking the button. The second one can be created by the admin.
But life is not always as simple as diffusion.
And the third one is only created when the admin creates a notebook.
I'm actually going to, I think, skip this over. But let me say that a lot of what you measure in solids is actually fundamentally about diffusion and about this kind of relaxation. So this here, just to explain why I had this is a famous formula due to Einstein about classical diffusion. That actually is an example of one of the deepest principles in normal statistical physics. Basically, what Einstein said is the diffusion constant of heavy particles in a fluid of light particles. If you put more heavy particles in one region, there's a diffusive constant or diffusive equation that tends to restore equilibrium. But you can calculate that diffusion constant just by watching one particle jiggle around at equilibrium. If you know the history, Brown saw these heavy particles moving around, and he thought, my gosh, the heavy particles are alive. They're not actually alive, they're just fluctuating at non-zero temperature. But the equilibrium dynamical fluctuations, if you integrate over those, you get the diffusion constant. Where it gets kind of interesting, and of course there are known cases where this fails, but this is the fluctuation dissipation relation or part of linear response theory. How a system gets back to equilibrium doesn't care whether it fluctuated away or you pushed it away. So anyway, a famous example that is not diffusion and doesn't relax in the same way is something like air or water. And I'm not going to go through fluid mechanics very much, except to point out that there are only three equations, and these describe, hurricanes, droplets of water, biological systems, whatever. Why are there only three equations in standard hydrodynamics? Because the point is going to be that the spin chain has a much more interesting kind of integrable hydrodynamics. So these three equations, the first one basically came from conservation of particles. In a fluid, two particles bounce off each other, two particles come out. Momentum is conserved, energy is conserved. Those are the three equations. Now, where it gets kind of interesting is that the chain of qubits, whose ground state was found by Hans Bethe when he was 25 or so, at least when Jz is equal to Jxx. So this is a chain of qubits written in spin notation. It has been known for a long time that this has many, actually an infinite number of conservation laws. In other words, I can write down, and I might have a slide on it, not just spin and energy, but many other things. And there are a couple other examples. These are known as integrable systems, and they're quite fascinating mathematically. There are a few systems essentially only in 1D, where even though particles interact, there's still an infinite number of conservation laws. In fact, people knew that, but they only knew half of them until about 2011. So just so you don't think I'm lying to you, this is the beginning of those infinite lists of old conservation laws. The notation, if I write a bunch of indices, I'm sorry if you're in the back, there are Pauli matrices with a bunch of indices. That means the product of Paulis on some, local string of locations. Anyway, they're infinite charges and infinite currents and all that. Those are interesting, and they're enough to completely determine things like the free energy at any finite temperature. That was done in the 70s, what's called the thermodynamic beta ansatz. The surprise that comes from thinking about spin dynamics of the chain is that there's actually a whole another infinite set of conservation laws that are hard to write down. You have to generate them on a computer. So there's something fundamental about integrability of the Heisenberg chain, which is kind of the simplest integrable problem, or the original integrable problem, I should say, not the simplest. Anyway, so it was realized in 2011 that there was a bit of a problem, and that's why there were a lot of puzzles about dynamics. And what's happened in recent years, if you like, is kind of the continuation of the impact of that realization. And just, I don't want to get too much in the details of that, but let me show you that the hydrodynamics I'm going to talk about, once you realize what you were missing, works very well. So this is a comparison of how, if I took my chain of qubits and I heated up the middle. So I made the middle of the chain, the horizontal axis just moving along the chain. I made the middle of the chain hot, and the ends of the chain I kept cold, and I watched the energy spread. So T equal to 0, energy is still at the middle, it spreads out. DMRG is a fancy microscopic calculation. Hydrodynamics are the solutions of the kind of equation I'll write down, and you can see that they agree very well. So there's something right about this kind of hydrodynamics with an infinite number of conservation laws, and that hydrodynamics is actually really simple in hindsight. And it was worked out first, I think, in classical systems. The surprise is that it maybe works so well in quantum systems, at least in this class of integrable problems. And the idea is, you might have seen the Boltzmann equation at some point. It's sort of where the fluid equations come from. The Boltzmann equation is an equation, it's like the simplest one you could guess for the one particle distribution function, which is how many particles are there at a certain point of space-time with a certain momentum. And normally, when you look up the Boltzmann equation in textbooks, you'd say there's a left side, which is how the particles stream around, and there's a right side, which is collisions. And it turns out that integral models don't have any true collisions. Even if you bring a bunch of particles together, they interact with each other. The momenta coming out are the same as the momenta coming in. The way they interact with each other is a lot simpler. The velocity of one particle at a particular point in space-time depends, in a really complicated way, but it's just some integral, over how many other particles there are with other momenta at that point in space-time. It's a bit like you're walking through a crowd, you know where you want to go, you know the talk you want to go to or the concert or whatever. There are a lot of people in the way. They slow you down, but you don't lose your momentum. So that's the way particles move in integrable models. And now we come to maybe the more recent stuff, which led to an actual experimental test. So the hardest case, going back, when I say Heisenberg, what I mean is the particular case where Jz is equal to Jxx, because it was kind of known that if Jxx was much smaller than Jz, if it was Ising-like or easy axis, I would get diffusion. If Jz was much smaller than Jxx, in particular if Jz is equal to 0, there's a very beautiful and not very complicated solution of this chain called the Jordan-Wigner transformation, and that proves that the spins are actually ballistic. So we know there's a ballistic regime and a diffusive regime, and the proposal was in 2019 that actually the Heisenberg point is kind of a dynamical critical point in between, with z equal to 3/2 and related to something famous in soft matter physics. And rather than talking about it in detail, I have a movie and then some experiments. But if you want to know what this Kardar-Parisi-Zhang is, the same Parisi who recently won a Nobel Prize, you could take diffusion and you could add kind of the leading order nonlinearity. So in other words, left-hand side is diffusion, right-hand side is the first nonlinear term you might write down, at least in an inversion symmetric system, plus some noise. And it turns out that that's enough. That nonlinearity changes you from diffusion to something where the scaling is different. And this was known in a lot of classical systems. It's a surprise it happens in this quantum spin chain. It doesn't happen in the simplest classical spin chain. And what this tells you is that there's something very simple you could measure. And in fact, now this is what's been measured with electron spins, atoms, and with gates in a quantum computer, it says that the Heisenberg chain should have a very special kind of dynamics, even at very high temperature, as long as you don't melt your crystal, if you like, or have to worry too much about phonons or something. There's ballistic regime, means you spread or your spatial motion is linear in time. That's the red curve. Diffusion is the green curve. And what you should look for is something halfway in between, more or less. So, and again, to be precise, that's only happening at one point, but it does happen at high temperature. So that wasn't originally our idea. We were so surprised by it that we wanted to reproduce it and understand when it happens and at what temperatures and so on. And the answer is if you wait long enough, it happens at all non-zero temperatures for models that are both integrable and isotropic in a sense. And I think that conjecture still holds, and parts of it have been proven. All right, so here's the movie. This will date me. This is what video games were like when I was in high school. So particles are more or less, I mean, the particles in Tetris have different shapes, but they fall down from the sky and they stick. And if you were to look at this interface, so the velocity of the interface is constant, but if you were to look at things like the width of the interface region or the correlations across the interface, you would realize quickly they're not Gaussian, they're not exponents like 1 and 1/2, they're exponents like 1/3 and 2/3. And there are a lot of classical problems that behave like this. That's why this KPZ is one of the most important classical dynamical universality classes. So now we're going to try and measure that, but just to kind of state again, the way hydrodynamics works on the ballistic side, there's a very simple picture which you can already see with classical solitons. This is a picture in the nonlinear Schrödinger equation that two solitons are happily moving along with the velocity. They hit each other. They fall apart like you expect in a nonlinear equation, but they have been displaced from the trajectories they were on. I think that work of L and Kamchatnov that I showed is probably the first along those lines. If you want, there's a kind of hydrodynamics where instead of 3 equations, you'd have an infinite number, but we can just write that one generalized hydrodynamics or Bethe-Boltzmann equation and solve that. So, sorry for skipping a slide or two, but I want to come to the experiment. So this potassium copper fluoride is a 3-dimensional crystal, big chunks of it. You can pick it up, you can do neutron scattering on it, and it's got chains of spins inside. And those spins are more or less one-dimensional, in that the coupling between the chains is about 20 times smaller than the coupling along a chain. And people had previously studied this compound back around mid-2000s as a very good example that there's a new particle in Bethe's solution of this 1D Heisenberg model, the so-called spin-on. So we basically called them up and said, look, please redo your old experiment, but less well. Instead of going to low temperature, go to high temperature. Normally you tell experimentalists, go to low temperature and they get kind of grumpy, they need a fancy fridge. If you tell them, please redo your experiment at room temperature, they're relatively happy. You have to look at lower energy. That's the one challenge. So before, people mapped out the kind of spin-on dispersion relation. Again, spin-on is one of these emergent particles at low temperature and high frequency. Now go to low frequency and high temperature. So you're kind of looking down here. And what you get, at least if you integrate over a window of frequencies, is a scaling with momentum that is more or less KPZ. At least it's a better fit to KPZ than either diffusion or hydrodynamics. I'll show one slide of data in a second. I don't want to spend too much time because I want to tell you the other kinds of experiment. But just again, so that you don't think I'm crazy, because I do see some of my condensed matter theory friends in the audience, the low temperature limit of the Heisenberg chain is an example of something that we call a Luttinger liquid, or a Tomonaga-Luttinger liquid. It is normally described, it's thought of as kind of free bosons, which would be ballistic. And it has spin charge separation and other neat things. If you're interested in quantum many-body physics, you might Google this sometime. However, the problem is that free theory, while it's okay for thermodynamics, it sort of ignores dangerous, irrelevant dynamical operators that act to degrade the free currents of the free boson model. That's where KPZ comes from. But essentially, you have to wait a longer and longer time to see the onset of KPZ, which is this T to the minus 2/3 power law in the autocorrelator. You have to wait longer as you go to low temperature. And I'll come back because temperature will be an important part at the end as far as where the frontier is. All right, so you measure neutrons. That gives you something that you can compare to your one-dimensional simulation. I'll talk about classical simulations, even though other people have now done nice quantum simulations it works pretty well. You fit laws. The full data set is here. This is from Nature Physics 2021. You get power laws that certainly, have big error bars because it's only over 1 decade that you can measure in momenta effectively, but they are much more consistent with KPZ than either diffusion or ballistic behavior. However, after we did this, a group in Munich, Manuel Bloch and Johanna Zeiher, did a really nice quantum gas microscope experiment that is able to add a lot to the story. In fact, in some ways, it's much more tunable because when you take that big crystal, you can't really control how the chains are coupled, and that gives you a limit on over what temperature this will apply. They can build, if you like, tubes of atoms. It's only about 50 atoms in each tube, or chains of atoms, but they can control how those chains are coupled. And they can confirm, for example, that one chain, decoupled, has KPZ behavior, and coupled chains, when it's more two-dimensional, do not. So I think this is an example. I would probably call this a quantum emulator rather than a full-on quantum computer, but it is a quantum emulator that is contributing to our understanding of this quantum matter problem. And then finally, more recently, and just a couple of weeks ago, Google Quantum AI published a paper on dynamics of magnetization at infinite temperature in a Heisenberg spin chain, using of order 100 qubits. So it's the same problem. And let me now try to start talking a little bit about where quantum computers are starting to at least be competitive. I don't know if we're ready to declare quantum advantage for science yet, but quantum computers of various kinds, both atoms and superconducting qubits, for general purpose problems may be a ways away. For the kind of problems that I care about, which is quantum matter, they're beginning to contribute a bit. This problem of one-dimensional spin chain at very high temperature is kind of well suited because you don't need to cool. You're just doing dynamics on random initial states. And they were able to point out effectively that some of the behavior, in fact, all the behavior of two spin correlators seems to be KPZ. If you measure higher spin correlators, which you couldn't do with neutron scattering, they seem not to be KPZ. You have a question or just stretching? So, let me try to explain why did Google and IBM care about this kind of thing. And maybe that will give you a sense of where, if you want to do quantum matter with quantum computers, what are some hard things we want to start doing? So just to come back with why Google and IBM care, I said the Ising model is NP complete in the sense that if you could find a ground state, not of the simplest Ising model with constant interactions, the ground state of the Ising model with general interactions is NP complete. If you want to make your life even harder, the ground state of the Heisenberg model with random interactions is QMA complete. That's like the equivalent for a quantum computer of NP complete. It's probably impossible even with quantum computers. Transverse field Ising model is somewhere in between. It's like quantum Monte Carlo-ish. That's stochastic Merlin-Arthur, if you're curious. So computer scientists have these inclusions that basically the Ising model is easier than the transverse field Ising model. Simplest example of a quantum phase transition. This is effectively what D-Wave was building in the middle, or is building. And the right side is random Heisenberg model, or general Heisenberg model. If you could solve that, or even demonstrate that these three classes are actually different, that would be a big deal. So if the ground state is so hard, that kind of implies that getting to very low temperature is also very hard, and that's kind of where a frontier is that I'll come back. But let me maybe wrap up or start wrapping up with some recent work also in QSC about where the real scientific frontiers are. If you like, I think this one-dimensional quantum matter problem is very interesting, and seeing KPZ is very surprising, and there's still leftover questions like the 4-point correlators. But where maybe the big game is, if you take that same Heisenberg model and you go above 1D, then we know that there can be very exotic physics, theoretically. Finding good experimental examples is hard. So as an example of what's hard, if you take this simple Heisenberg model and put it on this lattice, so-called Kagame lattice, and I mean put it on every nearest neighbor bond, constant value, we don't know what the ground state is. Friends of mine fight about what the ground state is in a genteel way, but this is pretty much realized. There's a material discovered by Herbert Smith and called Herbert Smithite that has these in sort of planes. It's pretty well described by this Kagame material, and we suspect that the ground state is quite interesting, but we can't prove it. What I want to talk about is a slightly different approach to finding these states of spins, so-called spin liquids. Basically, it's kind of what Anderson was talking about, but closer to the Mott insulator transition. So let me maybe remind you of where this Hamiltonian comes from. If I start with electrons, the idea is if my repulsive interactions between electrons are strong enough that I've just got one electron on every site, that electron has a spin. That's an insulator because the electrons aren't moving, and that's a Mott insulator. So Mott insulators are typically antiferromagnets, but what the antiferromagnetism does depends a lot on the lattice. So, what we'd like to do with that, I think as you've already heard in this meeting, there are other systems that show one of the most profound bits of physics in nature, which is whatever you were told as an undergrad about all the particles being just bosons or fermions is not quite right. There are these anyons. Anyons might be useful for quantum computing. Leaving that aside, they're at least very interesting to physics, and now people try to build these on quantum computers, and we'd like to know, are magnetic Mott insulators actually building spin liquids with anyons, or even more exotic kinds of spin liquids? And here, I want to quickly take you through the story kind of where spin liquids come from, and then wrap up, because this is a problem where materials are contributing, and at some point, quantum computers may contribute, but for now, we're doing the best we can with classical theories and classical computers. So quickly, Anderson's original idea for where you'd get a resonating valence bond, sort of a fluctuating singlet spin liquid, was to take this famous Hubbard model, hopping of electrons, on-site interaction of electrons, and go to very large U. Turns out that when you have very large U, you get that Heisenberg model of the spins, but it orders like this. It's kind of 3 sublattice, but long-ranged conventional antiferromagnet. Now, what happens when U is not that large, if you like, when it's just barely on the Mott insulating side, we proposed, and I think other groups increasingly agree, that in this Hubbard model, you get a chiral spin liquid. It has a gap, but it's not the Anderson spin liquid. It's something else. It's actually more like a fractional quantum Hall state, the kind that Mike Manfra studies, but made out of spins. It's Kollmeier-Laughlin spin liquid, if you want to be precise. And understanding where that comes from, after we saw it numerically, in a later paper, let me try to do that rather than just take you through all the numerics. But just to kind of give you a bit of further reading if you're curious, there are many different kinds of spin liquids. They fall into at least 5 different classes by my reckoning. The one that Anderson proposed, we would now call Z2 spin liquid. There is a way to get it in the triangular lattice if you don't work with spins, but if you work with quantum dimers, which is kind of an idealization of a singlet. We think that there is a region of the Hubbard model that has this chiral spin liquid. What actually seems maybe to happen in some new triangular lattice compounds is something maybe even harder to define precisely, which is the gapless spin liquid. Roderick wrote a nice section on this, kind of a taxonomy of different kinds of spin liquids. So if you want to learn more, you can check out as far as I know, it's the only topological phases book with a bird and a snake on the cover. So it should be easy to find. All right, so as far as why spin liquids are hard and why people disagree, if you change the Hamiltonian only a tiny bit, you often get a different phase. This is just kind of a coarse level phase diagram of all the different things that happen on the triangular lattice for slightly different couplings. For the Hubbard model, the spin coupling that matters most is nearest neighbor antiferromagnetism J1. But the one that matters second most when you get close to the Mott transition is not longer range 2-spin. It's actually this 4-spin coupling, which is a bit non-intuitive. But trust me that in perturbation theory, this was known to be strong. And this is the one that actually drives the chiral spin liquid. However, I don't have a really great experimental candidate for that, at least that I'm prepared to tell you about. I think for new experiments, the hot thing in town is this ytterbium selenide family, where ytterbium is effectively spin half triangular lattice. And there's a debate based on neutrons of what those do. I think it's close to a phase transition to a quantum spin liquid, maybe, because I'm on the second paper here, but not everyone agrees, I suppose. There's another new compound out of Duke I won't talk about today. Anyway, just to kind of maybe mention a little bit about this QSC work. So this is the argument. If you want to read our PRL, this was led by Tessa Cook-Meyer, who's now postdoc at Santa Barbara, KITP. Basically, you can map this 4-spin term by writing it in terms of the scalar chirality and argue that this counterintuitive term drives the chirality. Once you have the chirality, it's natural to get the Kallmeier-Laughlin spin liquid. So for theorists in the audience, please ask me more if you're curious. But where we are in like the experimental world in this new ytterbium selenide family is probably something like this, where you can't really as easily as you can with atoms. You can just change the chemistry, and that takes you, from that 120-degree long-range ordered state I talked about to other possibilities, including possibly a spin liquid. So to kind of wrap up, because I'm getting close to time, where we are, I think dynamics in 1D is a great model problem. We thought we understood it. As of 2019, it was realized that we didn't understand it. There's still things we don't understand, but at least we can be pretty confident that the two spin correlators are in this dynamical universality class that is not exactly new, but it's new in a quantum system for these reasons. When we go to higher dimensions, so the way we model, compounds like what's here is this density matrix renormalization group numerics and very approximate analytical methods. With the numerics, just to kind of explain where classical computing is for quantum matter. So my favorite, there are special cases where we can do better, but for kind of general quantum matter with local interactions, I think the best general technique is matrix product states or tensor networks or DMRG or PEPs. Those are all kind of the same general idea. We basically, most of us doing those in higher dimensions do it by, you take your two-dimensional plane and kind of compactify it in a cylinder and study the cylinder, because we can't do the two-dimensional plane very well. PEPs is something for the two-dimensional plane, and there are problems where that can contribute. But what I think we do, and many people, is sort of cylinder DMRG. And that means that you have a fine size approximation because your cylinder is very short, maybe 6 spins around or 8 if you're lucky. You can only do sort of finite time, which means you have a lot of frequency uncertainty. But you can make plots that are at least a guide to experiment, but they're not accurate in a way that would impress a computer scientist. I'll put it that way. Or at least I think unbiased. That's the main selling point of DMRG compared to variational Monte Carlo or something. So I would say that, where we are with 1D, in 1D we can overlay data on calculations from DMRG, and the fit is good enough that I think the problem is in the experimental data rather than the DMRG, let's say. When you go to higher dimensions, or even more when you go to random systems, because those are computationally much more difficult, then maybe DMRG can provide kind of a rough guide to experiment, but we do need something new. So in other words, I would say when we go to higher dimensions, even the translation invariant problems, they're not provably hard. You can't really define it as a complexity problem in a computer science way, but they're hard in the sense that people from my field have been working on them for 40 years, and we suspect that there's not a really easy solution with classical computers. So they're empirically hard, or hard from the point of view of practical theoretical physics. But I think this is a category where, the emerging quantum hardware, like you heard about, I think that has a lot of potential to start to change how we understand quantum matter. And then finally, the part that I wanted to convey, these nice simple spin problems that we might care about for their own sake, I find them very useful to illustrate a lot of basic quantum information questions, like the different quantum computing complexity classes. And yet those spin problems are still relevant. In many of these atomic systems, for example, you could build those random versions and see just at what point does the hardness kick in. I've been interested in random spin chains for 20 years just because they're really fun and there were no experiments. And now all of a sudden there are experiments on random spin chains, and even a random spin chain in one dimension can actually be NP complete. So there has to be some point where the hardness becomes visible, and understanding that kind of classical and quantum hardness frontier with spin systems, that we'd like to go. So I think I have a couple of slides if you ask me the right question, but I think I'd better stop there. Thank you for your attention.
All right, we'll open the floor to questions. We've got a lot of them.
Thanks for the nice talk, Joel. I have a question about the first bullet. The question is this. At the very end of that bullet, you said that in the Google quantum computer, there was some trouble matching theoretical predictions from the hydrodynamic calculations with the higher order correlation functions. So in that context, first of all, do you have any ideas why? And the second is, when their idea of temperature, is it the same as our Boltzmann distribution temperature, or is it just some higher average energy?
Yeah, the second one, I'd say that what makes this tractable is it's infinite temperature in the sense that you're just picking a random initial condition and starting with it. So it's like Kubo formula temperature, if you want, where the temperature is only your initial condition weights, and there's no thermalization along the way. I think the random sampling is less of a problem, maybe I'll put it that way, than other things in the calculation. I think for the first question, yeah, I think actually the computer is right, and if you want, simple KPZ probably doesn't describe these higher point correlation functions. And the reason why we believe that is, I said that the classical Heisenberg chain is not KPZ, which is true, but you can cook up a kind of artificial classical chain with logarithmic interactions called the Ishimori chain. The Ishimori chain is like a theorist toy model, but it is in this KPZ universality class because it is integrable. And that also has this feature, and that's classical, so you can do a much bigger simulation, that also has this feature that two-pointer KPZ and multi-pointer. So I think at this point, the problem is, we know that multi-point are not KPZ, but we don't know what universality class they are. And some nice work on, trying to solve that. I think not solving that, but explaining what the issues are, is by like Sarang Gopalakrishnan and Raman Vassur. Have a nice article on it. But I think they would say, we have a picture for what might be going on, but not yet like a prediction for a number, the way you get out of KPZ.
It's more of a suggestion rather than question. There is a field dealing with somewhat similar issues, which was able to get quite far for a very simple reason that their experiments are at room temperatures using commercial devices. I'm talking about emergence of hydrodynamics in fiber optics. Basically, your equivalents are kind of a one-dimensional case. The equivalent of the site will be the photon frequency, and for 2 dimensions, the equivalent will be photon frequency and the mode number in a multi-mode fiber. They would also have nonlinear Schrödinger equation there because of refractive index dependence. Your time dimension will be their propagation distance. What you find, there's also the onset of hydrodynamics. You see kind of onset of statistical physics. You have in the limit of lossless propagation, which you can kind of get there if you put some Raman amplification in the fiber. You get integrability, and there is about 20 years of work there. And as I said, their experiments are a lot easier because especially if you go for a long time limit, which is challenging low temperature lab and very easy in a fiber, just take a spindle of long enough thing. When I was listening to your great talk, I found almost one-to-one mapping in many of the results there. There will be one group in 2005 to 2010 plus, and the other in a multimode fiber equivalent of your equivalent connection to your two-dimensional systems in about last 5 years. So I wonder if as a question, whether you know about this group of work and whether you were able to borrow some of their knowledge. And it's a suggestion if not.
Well, I would say that the field, I'm not sure everyone in the field totally acknowledges this, but I think effectively we did borrow work from that community because these people, this paper that I give a lot of credit is motivated in large part by the nonlinear Schrödinger equation and by what happens in optical fiber. Now, let me explain how the new stuff is harder, and it would be great to do an experiment. If you like, this is kind of the ballistic case, ballistic but not free. So the solitons interact and they do this. When you go to the Heisenberg point, that's like a critical strength of the interactions where they no longer do this, where it's actually going from hydrodynamical and ballistic to KPZ. So I think in the optical language, that would be like if you could crank up the interactions to something where you have kind of an effective like isotropy, a non-abelian symmetry. There should, anyway, I think the answer is the field has partly been influenced by the optical field and also reproduced without knowing it, the optical field. So I think I agree with the spirit of that comment. But I don't know, in the optical field, it's not as natural to get an SU2 symmetry. If you could tune to get the SU2 symmetry, which is kind of automatic for spins, then I agree that you should see KPZ in classical optics. Yeah.
Yeah, thank you, Joel, for a super nice talk. So I have two actually questions about two different parts of your talk. So one is this super diffusion. Is it actually really uniquely quantum effect? And if so, what is quantum about this, you know?
So I think no, but I would say that in the Heisenberg chain, it doesn't happen in the classical Heisenberg chain. It doesn't happen for spin 1, it only happens for spin half. So you could say in the Heisenberg chain, it depends on having spin half because otherwise they're not integrable in the same way. But I would say that
it's not clear, right? So that,
I would say that I would say that you can get KPZ. It's not clear. No, it's clear that you know, if you do this for classical Heisenberg, people have
yes, I understand. But whether it's uniquely quantum effect, I think it's not clear.
No, I think you can make a classical model. You can make this Ishimori chain, and that is super diffusive. The interaction in the Ishimori chain is that for two neighbors, now spin is a unit vector. The interaction is just log of 1 plus S1 dot S2. So you know, I don't know how to make a log in a solid. But that is KPZ in classical.
So the second question was about your spin liquid part. So my understanding is that, like in this kind of triangular lattices, for example, it is kind of clear that there should be no spin liquid, and it's kind of as opposed to, for example, like the stuff that things which we did. I guess we had this Kagame.
The point is,
you know, Kagame lattice where, you know, like our experiments, you know, clearly show that there is a spin liquid. Right? So.
Yeah, no, triangular lattice, if you go deep into the Mott limit, if U over T is infinite, there's no spin liquid, there's this order. If U over T is between 8 and 10, then there is a spin liquid. That's the claim. So it's, you know, in other words, you might have thought that the triangular lattice Hubbard model, the simplest thing would be that there are two phases. There's a metal and there's a Mott insulator with 3 sublattice order. But what I'm saying is, is that
it's not pure Heisenberg. Oh,
not pure Heisenberg. That's right. No,
so if you want kind of extension.
Exactly, not pure. So if you want the simplest model that will give it to you is J1, J4.
Yeah. Okay. Yes,
sorry, not pure Heisenberg. Yeah. Thank you for clarifying.
But like spin liquid, for example, in these other models like ours is much more stable.
Exactly.
Right?
No. Well, yes. Yep. I think that's well. Spin liquid, another model like in Kagame, for example. I think you can get it with just J1.
Hi, thanks for the talk. In this chiral spin liquid, do I understand correctly that the time reversal symmetry breaks spontaneously by the 4 spin interaction?
That's right.
Thanks.
That's right. So that's what we'd love to see experimentally. And I have hopes, but no paper I can point you to.
All right, time for, I guess we have 2 more questions. We'll get to them all.
Sorry, I just want something clarified. So if you see quantum, like let's say solitons in a Bose gas collide, and like following Crosby-Tyefsky, let's say, then is the manifestation a phase shift in the soliton phase? Is that
yeah, so people sometimes use the term soliton for any lump. When I would say soliton equation or soliton, you know, any lump that's stable, but soliton equations are when lumps come together and they kind of retain their identity. And the statement here is, if you want to understand the classical to quantum connection, classically, there is a delay in time because the solitons interact with each other. They didn't lose their identity, but they delayed each other. So you could ask, well, what does that become in quantum mechanics in these beta ansatz models? In one-dimensional quantum mechanics, a phase shift is sort of the key object. That could be from statistics or scattering. You can't tell them apart. But something Wigner taught us was that if you have a phase shift that depends on energy, which you do in these models when they're non-trivial, that semi-classically is just a time delay, this is the Wigner formula. So I guess I'd say if you have solitons that are true solitons and pass through each other and retain their identity, with a time delay, that would be like the classical version, and with an energy-dependent phase shift, that would be the quantum version.
Okay, yeah.
Hi, thank you for your talk. My question is, Ising or Heisenberg models have been used using their equivalents to solve optimization problems. And do you know if there is another way of using those models to solve other kinds of, let's call them quantum system simulations, such as chemistry or other applications?
I think I would defer to some experts in the audience who know more than I do. I think there are ways to start mapping interesting. Okay, so if you like, what Google did for the problem I talked about was a very direct mapping, more or less, where a qubit is spin. You could ask, if I had some more complicated, quantum chemistry or other problem, could I map that into what are the natural operations on different atomic lattices and so on? I think there's nice work on that coming out of QERA, for example. I can't really comment on if there's a universal strategy where if you were given a quantum chemistry problem, is there a clear best way to map that to like a natural quantum computing with spin problem? But I know a lot of people working on it. That's the most I can say.
All right, if you have any more questions, we'll save them for the panel. Let's thank Professor Joel Moore again as we transition to our next talk. All right, we're gonna go ahead with our first showcase today from QERA. So it's gonna be presented by Pedro Lopez. Pedro Lopez is a business developer at QERA Computing Incorporated with a PhD in theoretical physics. His research career through Brazil, USA, and Canada explores topics in quantum matter and topological physics. He is passionate about communicating quantum computing at all levels and helping customers and developers understand ideal entry point in this technology. So let's welcome Dr. Lopez.
Oh yeah. Do I have a voice? Yeah, looks like I do, right? I can hear myself. Shall we get started? Okay, let's go get started then. Thanks everyone for having me. And I think that I don't know if I tend to be lucky or positive looking at whenever I end up coming on stage, because I feel like it's always a good, I'm always coming in the right time. Right? So I think that what we're going to be doing now is a pretty good sum up of topics that came from Suzanne's talk and Misha's talk and also Gerard and Joe's talk right now. We are going to take a little bit of a pedagogical entry into neutral atom quantum computing. We're going to take a few steps back from all the exciting gate-based quantum computing stuff, but we're going to talk a little bit about the analog simulation capabilities that exist today right now that can address problems such as the ones that we were discussing. So there's going to be a little bit of the mindset of everyone that has been speaking today so far. I want to introduce you to our new learning platform. So we have a website. You can access it. It's qbook.quera.com. It has not been launched fully publicly yet, but I'm still collecting guinea pigs to use this to learn. But the idea is to start collecting information here about how to enable people to become expert users on quantum computing with neutral atoms in their mindset. So in particular, the content from today is mostly focused on this two-chapter introduction. This is a little bit longer, but we are going to make the short version of it. And we also have a little lightning blog post intro session if you don't have the patience to go through everything. But one thing that is cool is that you can take quizzes here. You can take quizzes and test your knowledge. And I am committed to correcting you later. And if you do well, you get certificates. So for being initiate in quantum computing with neutral atoms. So this is an invitation to everybody to try that after we are done with this conversation of today. But for now, we are gonna cover the content of this school. And so stop me whenever you need. I prefer to be stopped. And let's remain as engaged as possible. So also on that on this website, you can run all code that you need kind of instantaneously. You just need to log in. You don't need to install anything. But if you want to install anything, the suggestion is blockade with a Q and no U, as things go, which is the software that we use to program Aquila and do simulations, Aquila being our quantum computer. Can I get started? Okay, yes, so let's go. So by now, I think that no one in this audience can say you never heard about quantum computing. Right? So if you ever heard about neutral atom quantum computing, you raise your hand. And the question that I always like to ask people is, if you have heard about neutral atom quantum computing, who thinks that neutral atom is the coolest, right? The coolest modality to do neutral atom, to do quantum computing right now? And usually I get good correlation. So we're gonna skip that right now. But if you have not picked up the mindset yet, these are nice platforms. These atoms are neutral, so they're not ions. We could be calling them atoms, but people get confused. So we just emphasize the neutral part, right? So we don't torture the atoms. We keep the electrons. The limbs remain where they are. And this means that we can put lots of them together. These are kind of densely packed them. We don't have a nice, sexy golden, cryostats to show, so we stick to diagrams for now. But what we do is to hold these atoms with laser light. So laser light is not like lightsaber. Laser light has a waist, right? It's the focal point, and that gets sticky. Some people in biology use that to hold cells. We can use that to hold atoms and do calculations with them. And that's pretty cool. So as per conversations today so far, quantum computing, as I like to just make sure that we are all on the same page, it's not about computing faster. Quantum computing is about going from point A, the beginning of a calculation, to point B, the end of a calculation, through a new set of rules. So it's like changing the road. Sometimes the road leads to a shortcut. Sometimes the road leads to a better way to get to the other side. And the road for classical computing includes logic gates. For quantum includes quantum gates and all the probabilistic processes that go in. Now, even within quantum computing, there are different ways of doing calculations, right? So most of you who have been studying this field for a while might be used to what we call digital operations or gate-based quantum computing. That's what you do when you take the logic, right? So you have your set of qubits in which you want to operate, and you put that logic down into individual or 2-qubit gates, right? So discretized sets of operations that apply on each qubit in separate. And that's cool. It's universal. You can do any type of manipulation of information in the Hilbert space that you might want to do. The problem is that each of those gates is noisy, and it introduces errors to your calculation. There's another way of approaching quantum computing, and actually there's more than one other way. But here what we're talking about is analog quantum computing. So analog quantum computing, the way I see it, is not so different from the picture in the middle, right? The picture in the left is just the same, except that in a bunch of small boxes, we have one big box, right? So one big box is one many-body gate. Instead of 1 qubit or 2 qubit gates, you have a many-qubit gate, right? That you control continuously in time. And that's pretty cool because fewer gates, in some sense, you can expect fewer errors because you don't have to do precise manipulations individually on different qubits. Also, if you think about time evolution, right? So arguably one of the most important things to do with quantum computers is quantum dynamics. You don't get better than unitary evolution, right? That's literally what time evolution is. So this is actually quite efficient for any kind of quantum simulation that you want to do. The downside of this, of course, is that it's very hard to make universal. Right? So if you could make a box there that really does anything I want, I would be in great shape. I wouldn't even consider doing gate-based quantum computing. But I can't. So what do? We play with other things that are a part of this technology, like in the fact that I can move the atoms around and position them in different shapes to increase the flexibility of the platform. And there's plenty that you can do. To say the least, deep scientific discovery, and some people in this audience can argue that you can get quite famous by doing it, right? So we have done, we have seen characterizations of phase transitions in some of the largest ever controlled simulations that have been done. There have been controlled many-body scars, so quantum dynamics, this is quite interesting. I think that as far as I know the history, no one knew that this phenomenon existed until somebody ran this on the lab. So it's kind of a bona fide discovery from quantum computing, which is not so easy to find whenever, systems are so small that you can always simulate them. So this is really like a scientific discovery that was done by running experiments. Joe was just talking about quantum spin liquids, so there have been demonstrations, and also kind of recently the characterization of optimization problems, all using these devices. So of course I have to talk about my friends here, so you can see the Harvard symbol over there in every single one of them, but they are not the only people that are doing great stuff. There are groups all across the US and in Europe, France as well. And there's plenty more going on, right? So by no means what's interesting to do with analog computing has been exhausted. We are working on applications in high energy physics for like lattice gauge theory. We have been doing quantum machine learning. We are working new models for spin liquids. Some of these have been published already. And we're studying critical phases. Also, those are kind of relevant for the high energy community. So there's a pretty broad kind of fan of opportunity for studying at least physical problems and certainly beyond as well. So pause for appreciation that there's a lot to be done. And I hope that by the end of this talk, you'll be not only excited to try some of this by yourself, but also you'll be enabled, right, to know the tools that you need to, autonomously seek your favorite research topics. That's the motivation side. Questions? Okay. It's always funny to talk in the mic. My voice is loud. Anyway, okay, so let's get then into the details of the system. So for the purpose of this talk today, we are going to be stuck with rubidium, and with the forgiveness of any chemist in the audience, for the purpose of this talk, rubidium is in the first column of the periodic table, and if it's there, it's hydrogen, right? So for all that we will care today, it looks like hydrogen, feels like hydrogen, and in particular, it has one electron in the valence shell, like hydrogen. So that's where we are going to encode information. And we are going to use two different levels of rubidium. One of them is the ground state, and so for rubidium is the 5s. And any high energy, very, very high excitation orbital, and any of those is called a Rydberg state. So for these machines that we are operating at Quera, we use the principal quantum number equals 70, so 70. So that's pretty high, but they are not ionized when you use that state. And a fun fact about physics here is that the polarizability of a body is proportional to the volume of the body, and the effective volume of a quantum system, of an atom, kind of grows with this principal quantum number. So as we excite it to these Rydberg states, these guys become highly polarizable. When they become highly polarizable, if I put two of them side by side, they interact via van der Waals forces. Ta-da, you can entangle things. That's basically the story. So what does the QPU cycle looks like? And I think that it's actually important to appreciate all of this, because the day that you start to submit jobs and to try to do simulations, you start to realize that you are actually interacting with a physical system. And understanding what are the limitations and what are the capabilities really involves kind of being able to abstract or have some intimate understanding of what's going on there. But basically what happens is the following. Like you decide to do an experiment and you want to create a register. You want to create a quantum computer that's gonna have a shape. It doesn't need to be a brick wall. It doesn't need to be a square lattice. It could look like a penguin, could look like Boston, could look like whatever you want, almost. So you're gonna tell the computer what you want it to look like, and this computer is going to load a magneto-optical trap, a MOT. We like our TLAs in AMO, our three-letter acronyms. So the magneto-optical trap traps atoms using a magnetic field and optics. So it's gonna be a little gas, some like 100,000 atoms. It's gonna be cooled down, and it's gonna be held in place. And a CPU is gonna make a computation that is going to kind of figure out the Fourier transform of what you want to, of the shape that you want, and send to an active optical element that's called an SLM. It's a spatial light modulator. It modulates light in space. The trick about the three-letter acronyms is that all you have to do is to read them backwards, and it's always clear what they do, right? So it's a spatial light modulator. It modulates light in space. So it's gonna take your beam that's gonna come with a, like, let's say Gaussian, and it's gonna come back in a Fourier transform of whatever you are kind of displaying on this active mirror, this SLM. That's gonna look like, in this case, a square lattice in the center. That square lattice is gonna pierce the cloud of atoms. That is gonna be cool. And these atoms are gonna load stochastically. So some of them are gonna go in the right place. Some of them are not gonna go in the right place. Right? About 60% of them go in the right place. You may be happy, you may be unhappy. Probably you would be unhappy. I would be unhappy, right? Whenever I create a quantum computer, I want it to look like exactly what I want. So what do? You actually see that on the edges of this, there's this kind of separated rectangles. These are kind of reservoirs. They pick up more atoms, and these atoms are simply slided into place. I don't know if it's a little small. Perhaps for the people in the back, it's hard to see. But we are going to slide these extra atoms into place according to a sorting protocol, and that's what we call sorting, actually, which generates the figure in the middle. That is going to get your atoms, your register, about like 99.5% correct. This does mean that 0.5% of the times you're not going to get the register you want. You can see there are even some errors on this one, just so I can prove you that I'm honest. That's fine. You're going to have to run this many times because it's a quantum system anyway. So you throw away every 100 or so, you throw away one of the shots. And so we are down here in the sorting part. We are going to image again. And this image is going to say, okay, the atoms are in the right place. They're not in the right place. And then we're going to initialize the atoms. We're going to bring them to the ground state fully. And then we're going to do a calculation. So you see QC here in purple, 20 microseconds. So that's where the calculation actually is happening. And actually, for the user, you have 4 microseconds to do whatever you want to do with it. Usually, the coherence time is like more 6 to 8. So we cut it when you're deep inside this coherent regime. We image again, and whatever shines is basically going to be in the ground state. Whatever is not shining after the calculation is going to be in the excited state. That's your 0, 1. That's your computational basis. With the caveat that what shines is in the ground, and we call that 1, and whatever is excited is in the Rydberg, but we call it 0. So you have to kind of be a little, I didn't decide on that, okay? So there may be a little switch of what you expect to be 0 and 1. But the point is that you are measuring like a Rydberg excitation density, and or 1 minus that. And there you go. So that's going to be the end of your calculation. This is a measurement of a computational basis. Okay, you get 0 in one state and 1 in the other state. That's going to be a bit string. You don't need to worry about these images. This is something that we can see. What we send back to you is just a bit string that says 0, 0, 1, 1, 0, 0, and that's it. Any questions about how this goes? Come on. Sorry? No, no such a thing. We're not moving before one question. Come on, we need one question. Yes. So we're gonna get to the hardware constraints, but it is correct, right? So there are lasers that are holding these atoms, and something that is interesting is that most of the time nature doesn't want you to build quantum computers. This day here, nature did want you to build quantum computers. So whenever you hold these laser tweezers, either you have 0 atoms on it or you have 1 atom on it, right? So there's never a time where you pick up 2 atoms. If you had 2 atoms, they are gonna collide and fly away, which means that if you take 2 of those tweezers and put them too close to each other, the atoms collide and fly away and you lose both your atoms. So there are a few reasons why you don't want to put atoms too close to each other. But yes, it's true. So whenever you're trying to create your system, remember that you're not going to be able to do anything you want. There are going to be some constraints because this system is real. You are actually taking atoms and putting them in place on a 2D plane. Anything else? It's okay. I'll get back at you. Okay, I'll get back at you and start asking questions myself. So no worries. So this is a treat. This is a treat. This is a view of what we call the Q view. This is something that only we see at Quera, so users don't get access to this. And this is pretty cool. So what this is doing, I want to move. There's so many cursors. Yes, there we go. So what you're seeing here is real time, not right now, but real-time images of the atom. So every single dot there is 1 atom, rubidium atom. That's before ordering them, before sorting them. Here is post-sorting them. So you can kind of use your intuition to see that these guys are pretty much far from each other in comparison with the ones on the left. Right? So think of this as a register of like a 6 by 6, 36 individual qubits. They're just far from each other. They do not see each other. These atoms, they are going to interact by proximity. So as long as they're far, they do not talk. So I have a register with 36 qubits, regular qubits. No, nothing's logical here. And between the middle image and the right image, what you're seeing is that we are applying a 2-pi pulse around the x-axis. Right, so what a 2-pi pulse does here? Well, you get your atom, right? So shining is going to be north, dark is going to be south in the Bloch sphere, and the 2-pi pulse is going to, right, and it comes back up. Now, your eyes are not deceiving you, right? Like this is blinking. On the right, this is blinking. So if you ever heard that quantum computers are noisy, here's what noise looks like. Okay, this is what noise is. Right? Sometimes you ask the atom to go back up, and yeah, I'm happily back up. The guy on the top left, right, most of the time, sometimes it gets uncertain. Sometimes I tell you to go back and you say, no, I'm down. I didn't pick up the photon that I was supposed to pick, and the things didn't go as expected. So this is actually what noise looks like. I've done one. You next. And if you have ever seen this talk and have already answered this, already know the answer, you don't get to answer again. So I'm doing a gate. These are individual qubits. And I'm making them rotate again around the x-axis, but by a different angle. Anybody has a guess of by how much? Sorry? So we are between the middle figure and the right figure here. We are taking a bunch of qubits that are pointing up, and I'm rotating them around the x-axis by a given angle. What's that angle? 180. 180, the guys are up, and I want to push them down. Okay, you want half of that. So somebody's saying we are rotating in the Bloch sphere by pi over 2, 90 degrees. We happy with that? We're happy with that? I am pretty happy with that. Okay, so we are literally rotating these guys to the equator, so it's like a Hadamard gate. This, I think that we have to take a moment to look at this and appreciate. Okay, whenever I get emotional about this. Okay, so whenever on your notebook you wrote up plus down divided by square root of 2, this is up plus down divided by square root of 2. Okay, half of them are appearing shining, half-ish of them are going down, they're dark, and that's what quantum statistics looks like in real life. Okay, so I don't know, I love it. I'll let you do a little more. Questions so far? Yes. We don't get single site control. That's the trick, right? So I'm putting them far from each other, but there's a single laser here that is shining on top of everyone and telling to everyone, come on, everybody, let's do the thing, right? Rotate this by pi over 2. So the AODs are used to move the atoms in place, but after that, we don't use the AOD anymore. Not on Aquila, not on the analog computer. Once the atoms are in place, that is done, we do the thing, and then we measure, and then we restart, and then the AODs can come to play again. AODs are the acousto-optical deflector. It deflects optics by acoustics. That's what it does, right? So you use some acoustic signal, and it's able to deflect light and move it around. That's what we use to sort the atoms into place. Any more? Yes? Thank you for that as well. So the characteristic distance scale here is going to be in the micrometer range. Okay, so these guys might be maybe like above 10 micrometers from each other, probably. But this is a good point, right? So whenever you're programming on Blockade, this is the programming language that you have to program with units. Okay, so you're programming micrometers and you're programming radians per microsecond. Or megahertz. I prefer megahertz, and then I divide by 2 pi or something. So, but yes, so the scales for distance are going to be in the micrometer range, and the scale for energies are going to be in the megahertz range. So let's get to that. Again, you can always go back to qbook.quora.com, and you can either open the Lightning course or the introductory course. So you can actually run the notebooks for these calculations there as we go. So we are close to midway through chapter 1, actually. So what the actual computer looks like. So the computer here is, I'm creating a honeycomb lattice just so you remember that it does not need to look like a square lattice. You can do whatever you want. It doesn't need to look like a lattice for that matter. And these guys are going to live on a plane. Before anybody asks me, no, we're not doing 3D. It's generally accepted that it's not the best idea to try to make this into 3D, particularly if we are going to move to this dynamic shuttling regime, then kind of all notion of dimension goes away. But these guys, they're going to live in a 2D plane. So you see these red motifs. These are the lasers that are holding the atoms. Some of them are excited. That's the green bubbles over there. And there's this green field that is shining over everybody. So that's the laser that is really exciting everyone. So you can see that there is like a wide beam that's shining over atoms. And that's why we are going to have, remember the figure in the beginning with the big box, one box over all atoms. So that big box is being caused by one beam that applies on kind of light on everyone. Cool. So what the user do? User does two things. You control the geometry, and you can control the time dependence. So the geometry of where atoms go, and you can control the time dependence of like how much do you want in the intensity, phase, etc. of the green laser. Technically, it's not one laser; it's more. But for our purpose, that's it. And quantum computation again is just doing transformations of information between the beginning and the end of your time of interest. And for us, it all boils down to solving the Hamiltonian, solving the Schrödinger equation. Schrödinger equation is controlled by the Hamiltonian operator. So the time has arrived, right? We could not wait too long. We needed to look at the Hamiltonian. So this is the moment where we're going to do it. So this Hamiltonian has three terms that matter. And everything that you see of t, like function of time, is going to be something that you can control because you control time dependencies, as I mentioned. So the first term over there, omega, is what we call the Rabi amplitude. So that's the terminology. And you can see that its role, right? So it generates flips between ground and Rydberg and ground. So this is like an X gate. That's what generates things that will do like X bit flips. There is phi over there. It's a phase, so we call it a phase. I over there is the imaginary number. It's not the label I. I just refuse to call it J. The next term that you care about is delta. So delta, we have a name for it. We call it the detuning. Detuning is because it's like me playing the fiddle. Sometimes I'm out of tune. And you use that to basically shift the energy of the atoms. And if you want, it acts as like a weight in a cost function, right? That's going to say, okay, if your delta is positive, this means that exciting atoms to the Rydberg state, that n equals 1, is going to be a positive thing. It's going to be something that you like. You're going to bring that with many atoms excited down in the spectrum. So it's going to be a low energy state, right? If delta is negative, however, then you're going to disfavor states with many atoms excited. Right? So if you have many ones, then you would have something that has many times delta, and many times delta is going to probably push this guy high in energy. And finally, you have the final term. The final term is the van der Waals interaction. It's not a function of t, so you don't get to control it as a function of time, but you do get to control it because you control geometry. So this guy here is going to be a constant. Sometimes we call it C6. You'll see that in a moment, divided by the distance between 2 qubits to power 6. So whenever you decide what your register looks like, that's what you're deciding. You're deciding what this cost function is going to give you. The Vij. Questions of what everything does? Yes? They represent the different dots, yes. They are the labels of each atom. Well, I mean, micrometer range, right? Sometimes 5, sometimes 10, you decide. Yes, by position, by choosing where the tweezers go. Yep. To get dipole. So for that, you would need to have interactions between different Rydberg states. So this Rydberg state here is a 70s. So you would need to go from 70s to 70L. And then you can get dipole interaction because it's a sum rule thing. You need to, yeah. Yeah, and you need another laser beam. You need this kind of side bands to make you kind of excited. The distance between energy levels when you are so high is very small. It goes with 1 over n cubed. The distance. Yeah, I got this. Thank you. I can cheat. So you need like it's a much smaller kind of frequency range for you to be able to. So you have to operate differently. Kind of create some beatings. Yep. We good? We good. Cool. I'm just checking the time. I actually have no idea what's the time that I have to stop. I got until 45? I have until 3:10. Okay, we're going ultra fast. More questions. Yes. The Vij is a van der Waals. Van der Waals is the same thing that holds graphene. Graphene, makes graphite out of graphene. It's just an electrostatic kind of dipolar second-order interaction between neutral bodies. Yeah, let's do this for variety. It's given. Once we set up the lasers and calibrate everything, it's done. Yes. It's going to be about, so it's going to be 4 micrometers. The short answer is 4 micrometers. Yes, yes. Yeah. I know, but the radial is 4. So we got experts here. Yes. Yeah, no, every atom here is 1 qubit. It has 2 energy levels. The ground is the 5s. The excited is the 70s. Those are the 2 states for the qubit. Not here. Not here. Well, so if you were paying attention to Joe's talk, he was mentioning how transverse field Ising models are in a kind of a between the pure Ising and the full Heisenberg difficulties. So that's it. Okay, so this is like a transverse field Ising. It actually has a transverse and a longitudinal field. That's omega and delta. Okay, so anything that lies in that class. Sorry, in what sense? Yeah, I mean, we have been doing, again, machine learning with this system. We have been doing optimization problems with this kind of system as well. So it's not fixed to physics application, but we like the physics application as well.
It is still the Ising type.
It is the Ising type, absolutely. Yeah, yeah. I think that some folks are working on kind of generalizing this Hamiltonian, maybe pulsing, doing Floquet pulsing to engineer more complicated systems. But it all, at the end of the day, it all depends on the dynamic range. We say, like, how much omega do you get? How much delta do you get inside the coherence time of your system? Yep. So usually the coherence time for Aquila is between 6 and 8. So we characterize basically the Rabi oscillation decay rate. Okay, so you put these guys to oscillate, and then you see how it decays, right? And it's between 6 and 8 microseconds. We're going to give you 4 microseconds to do your calculation. Well, the question that you want is never the coherence time. It's something that is like large or small is always dimensionless. So you want to know what's omega tau, as we say. So it's what's the range or maximum range of Rabi oscillation frequency times the decay time. And that, I think that we're in about 15 to 16 Rabi oscillations within our coherence time, which if you think of a Rabi oscillation as 2x gates, right, one oscillation goes and comes back. So this would be like 30 to 30 something x gates within the, okay? It's very, I mean, it's an analog system. You don't think exactly the same. Yeah, Vahan. You're interacting with the system, right? Like you're holding them. It's like quantum computers, if you leave them alone, they're pretty good, right? The problem is that you want to actually interact with them. So, I mean, those are simplified answers, right? By all means. I think we can move on a little bit. So, we have 9 atoms, and I want to put them in a given shape. And I want to decide what that shape can be. So there are things you can do, there are things you cannot do. If you're just doing simulations, you can do whatever you want. But if you want, the moment you want to submit this to the quantum computer itself, there are going to be constraints. So first thing to be aware of is that there is an error to the positioning of the atom that in many cases doesn't matter, and I will explain why in just a second, but that's 0.1 micrometers. The second is the size of the playground here. Right? So the playground is 75 by 76 microns. We just a couple weeks ago released some new features. 76 went up to, I think it's 120 microns. So you actually can make much taller geometries. But the point is that you have to put your atoms, whatever you want, has to fit inside of this 75 micrometer region. There's a minimal distance radially between 2 atoms of 4 micrometers. And again, this comes from the diffraction limit of being able to separate the laser beams. It comes from the fact that if you put the atoms too close together, they interact so strongly that the approximation that leads to that Hamiltonian breaks down. It is related to the fact that if you put atoms too close together, as I was saying before, they collide and fly away. So there are many reasons why you don't want to put the atoms too close. We are giving you 4 micrometers minimal distance. And there's a constraint here, we call it the row constraint. So if you put an atom like at this level, 1 or 2, however many they are, the next atom has to be at least 4 micrometers higher. And again, as part of these features that we just launched, we can actually push this down to 2 micrometers. But the point is that imagine you put the next atom, for some reason you want at 4.5 but somehow you wanted this, the distance between this and the next one to be 6, even though this is okay. Since you put a 1 at 4.5, now the next one has to be 4 micrometers up. So the minimum distance you would get is 8. So you have to be a little careful with the type of geometry. Some people here have been playing with some funky lattices that has been literally, facing this to the utmost consequence. And you can talk to Arnab and Vahan about what they have been playing with. So these are the row constraints. And the reason why we have these row constraints at the end, if you rewind back and remember when we're assembling the QPU, you remember that we were sorting by sliding, right, these atoms from these kind of reservoir places. So that's the reason why we have this row constraint. So we are sliding these atoms to make sure that they fall in the right places. Any questions about geometry? Yeah.
Does that change like during runtime where you interact with atoms, you bring them closer
So this is going to be the absolute minimum through the calculation. So we're not moving while the calculation is happening. Okay, so this I set up in place and I shoot my lasers. And then they do what they do. But we don't move the atoms while the calculation is happening. To move the atoms while the calculation is happening, you actually need to store the information in the hyperfile, in the ground states, right? So the Rydberg state is actually very sensitive because it's so large, right? So it becomes highly polarizable. It interacts very easily. You don't want to move them. Okay. Cool. Let me take a moment to just briefly show you. We have this program, again, it's called Blockade. You can literally pip install Blockade on your laptop. It's quite easy to use. We have a Julia version and we have a Python version. The Julia version is pretty good for simulations. The Python version is pretty good for interacting with Aquila. And I just want to show you how simple it can be to use it. Now, last time I did this, Gerard told me that coding in front of people is like making them watch paint dry. But we will watch together, right? So if you want to just place atoms in any random way, it's very simple. You just create this thing that we call a list of locations, and very nicely you just give a bunch of coordinates. So it's basically the x and y coordinates in micrometers. In micrometers, don't forget, we are coding in micrometers here for every atom. And boom, you can dot show. So atom coordinates, what we were creating, dot show. And somehow this is not quite moving. So this is not impressive, right? If it doesn't change while I do this, it's not impressive. So we're going to try again. My screen is loading. No, it's not. Am I coming back even there? Yeah, no, this is definitely, oh, I see, I know what's happening. I know what's happening. This thing gets very confused when I have my, okay, I give up. I'm gonna log out and log in again. Because this is not obeying me. Ask me questions meanwhile, like what are you doing? Don't waste your time. I'm listening. No question? I thought we broke the ice, you know. I thought we were not shy anymore. How fast I can change the parameters in time. So I see what's happening here. It's the other computer that's stuck. So there is a maximum slope rate at which we can change, make those changes. So I think that is 0.5 micrometers, 0.05 micrometers is the minimum kind of time rate. This is really stuck, okay? So yeah, it's gonna crash. Yeah. Do you want to project your own screen? I can project my own screen. We'll have the dongle for you if you want. Yeah, I need a dongle. I'm still listening. So moments for questions. We were talking about how do we place atoms, right? So it's an amazing question. I have no idea what's. I never got that one. Okay, do you have any idea? No, right? Yeah, I will ask around and try to bring this to you before the end of the school. Thank you. Yes. How do you understand the word analog? There's a few different ways actually by which you can understand it in this context. So one of the PC laptop. All right, we got this. So I don't know if this is going to in any way affect people on Zoom. Hopefully not. So this is analog because we are not discretizing digital, operations. We are continuously doing transformations in the system. It's also analog because you kind of create a system that is an analog of another, right? So there are a few ways at which you can interpret. I tend to prefer the first one, but does it make sense? Why we call it analog? Kinda. Okie dokie. I think that we can see. Yeah. Cool. Thanks for asking. Meanwhile, so what happens if you want to do something that is not like an arbitrary thing? You actually want to create a lattice. We are sparing you the trouble of generating your own functions to create lattices. You just call a square, tells how many unit cells you want in each direction. You tell the lattice spacing. So if by any chance people are asking me, you wanted to do triangular lattice, no problem. We can do triangular. There is no prejudice. Triangular. And boom, triangular. And now you are going to choose your stuff. And just like that, you can do what you want. All right? So very simple, very easy going. But remember that if I put a lattice spacing of 2.2 micrometers here, blockade is not going to scream because it's just on your computer. But the moment you try to submit this to Aquila, Aquila is going to scream. Again, Aquila is our quantum computer. So you cannot do that. It's too small. Okay, so you have to remember to satisfy the hardware constraints. Good. Given that, we can continue. I'm going to try to open all I need again. So what comes next? With some hope? With some hope? Yes. Almost yes. Yes. No. Yes. Okay, we're alive. Cool. So we have gone through the geometric constraints. What happens with the dynamics? So we also have constraint on the dynamics, so we cannot do anything you want. There are three parameters that you have to control in time: omega, phi, and delta. And the first and most important thing is that we are going to be using piecewise linear functions on omega and delta, and piecewise constant on the phase phi. And so even if you try to do something that is smooth, whenever you try to submit the job, the system is gonna break it down into piecewise linear pieces. There is a maximum of 2.5 megahertz. I still prefer megahertz here. Whenever you submit something, you have to convert this to radians per microsecond. But I think that megahertz are kind of a better unit. So 2.5 megahertz for omega. The delta is -20 to +20 megahertz. So that's the dynamic range of Aquila, as we say. Phase phi, you can wind it at your will, roughly. And I said this a couple of times. I say it again: 4 microseconds for the amount of maximum kind of compute time. You can cut that short if you want to just study something up to 2.2 microseconds, then 2.4, then 2.6, and then see how things are evolving in time, you can do that. But the maximum is going to be 4 microseconds. And as far as programming the waveforms go, it's actually also quite simple. So all you have to do is call this piecewise linear function that is going to take durations and values. So durations are going to be kind of the duration of each little segment. So here what we're having, this is awfully small, right? And this is awfully small. Let's spare everyone's eyes. Here we go. Here we go. So durations, let's say the first segment, you want to go from -4 to -4. So that's where we are here, going from -4 to -4 in 0.2 microseconds, and so on and so forth, right? You keep going. So the durations will always have one fewer elements than the values, because values give you beginning and end. So when you add up, it's always like n durations, n plus 1 values, and that's it. So that's why you generate waveforms. But remembering that whenever you put this inside a Hamiltonian function, Blockade will interpret this, the y-axis, as in radians per microsecond. Okay? Cool. Cool. I don't wanna lose the excitement here. I know that the technical problems make us drowsy, so hopefully we'll stop with that now. We have gone through all of this. We are pros. We have just done that. So now things start to get interesting. What happens with the phenomenology? What happens if you want to do something with the system? Now we have given you the kind of the basics, right? The programming kind of paradigms. Now what happens if you want to do something with it? So the most important thing that you want to know in neutral atom quantum computing is the Rydberg blockade with CK, no Q. This goes as follows, right? So if you have two atoms, 4 states, right? So ground, Rydberg, Rydberg, ground. And you apply a detuning, a negative detuning here, so the energy is going up, just to split them a little bit. That Hamiltonian that we were looking at before is going to give you something that looks like this, right? So you have the ground states, the GG, so ground, ground. Any state that has one Rydberg is going to be delta above, because you had n times delta, right? So every time you have one Rydberg, you pay delta. So I have one Rydberg on the second qubit, or one Rydberg on the first qubit, you pay delta on each of them. RR is going to pay 2 delta because there's 2 Rydbergs. Right, so let's just remember I see question mark faces. So we're going to look at this again. We're talking about that delta over there, right? So if delta is negative, so forget that minus, becomes a plus. Every n that is equal to 1, every n that is equal to 1, so every n that is in a Rydberg state, every atom that is in a Rydberg state is going to cost me 1 delta. Why? Why? So is that a physical question, or is this like a...
Why adding 1 atom to 2 atoms is the same in energy as adding 23 atoms to 23rd atom to 22nd atom?
So in this case, delta is being generated by the same laser that applies omega. So it's all the atoms are under the influence of the same laser. No, there's no electrons here. It's just it's van der Waals interactions, right? So these things are like neutral bodies. There's absolutely no Coulomb anywhere. Sorry? Well, I mean, if you go deep inside, of course, the origin of that is a Coulomb interaction. But because this is enough to describe the phenomenology of the system. It's enough for the reasons that we were discussing, right? So you have a system of atoms that are neutral bodies that are either in the ground state and therefore too small to be polarizable, or too large, right? So if these atoms are too small, I cannot polarize them. They cannot mutually polarize each other. But when they are both excited, then they can self-polarize, and then you have these van der Waals interactions. Okay, maybe you're unhappy. So that's the point, right? So every guy that is excited to a Rydberg state is going to pay us delta. And besides all of that, if you have both atoms excited to the Rydberg, you also pay V because you have n times n, right? So 1 times 0 is 0, 0 times 1 is also 0, 0 times 0 is also 0, but 1 times 1 is 1, right? So whenever I have both atoms excited, I pay 1 delta for each atom plus a V, and that's the interaction term. Now, for a moment of a lot of you know, of tension here, right? What happens when I put these atoms close together? The interaction goes with the distance between them to power 6. Therefore, if I bring them together, ooh, right? I'll do again. It is ooh, right? So I'm exaggerating on the scales, but the point is that the state with two Rydberg excitations gets so large that I cannot access it via my omega or my delta for that matter once I start rotating. And there is a characteristic distance for that we call RB, the blockade radius. That's given by a constant, C6, it's just a constant, divided by, most of the times people like to look at only omega. Technically, the characteristic kind of a dynamic scale for the system is omega squared plus delta squared, square root of that. But either way, you can define this characteristic blockade distance according to the simple formula, which is achieved by just equating the energy with Vij for those two atoms and solving for the distance. So any two atoms that are closer than this RB and in the presence of both omega and delta are going to be kind of blockading each other. They cannot be excited at the same time because I just pushed away the state with RR. I only have GR or RG. That's the phenomenology of the blockade, Rydberg blockade. Are we okay with that? If we're okay with that, we're going to do an exercise. Okay, and that's how it goes. So imagine I have 9 atoms. Okay, I'm going to have 9 atoms, and forget the blue RB. Let's just focus on the red one, right? So RBA there. I'm going to imagine I'm playing with my omegas and deltas in a way that this atom 3 has a blockade radius around it, and for that matter, all of the other atoms also have the same blockade radius around it. And I'm going to play with my delta in a way that I will force excitations. I'm going to favor exciting as many atoms as possible. So let's imagine I'm going to paint these numbers dark, right? I'm going to make these things black, right? So if I excite 3, and I want to excite as many as possible, under the constraint that atoms that are within the blockade radius cannot be excited simultaneously, which numbers are excited together with 3? The red one, the red one. 2, 1, 7, and 9, why not 5? Well, if you look at the blockade radius, right, let me get closer here. Right, so this does not touch diagonally. Right, so if I put it here, it does not touch diagonally. So 3 is not blockading 5. It's going to blockade 2, 6, 8, and 2, 4, 6, and 8. But you cannot do 6 because 6 is blockaded by 3. So if 3 goes, who else goes? 1, 5, 7, 9. 1, 5, 7, 9. So this is what we call a checkerboard pattern. And it's part of the phase diagram of this kind of Rydberg square lattice. It has been fully characterized both in theory and well, fully is a strong word, but a wide range of this phase diagram has been characterized in theory and in experiment. And we are talking about this thing on the bottom, right? Let's say checkerboard. So in that phase, if you choose an RB that's here defined only by omega and delta inside of that region, the ground state of that Hamiltonian looks like this Z2, sometimes called Z2, sometimes called Néel, sometimes called checkerboard phase. But there is more. Like you can have this star phase. I still don't see a star there, but I'm pretty sure that people have a good reason to call it star. I think it's in the Fourier space, actually. Don't know, right? It's okay. One thing that is very interesting of this neutral atom system is also that you can find phases like this striated region here between those two quantum phases, where you see the checker pattern is not just dark and yellow, but you have something that is gray, bluish over there. So this means that while in this phase, the star and the checkerboard, you only have zeros and ones, you have a phase there where you have some atoms pointing up, sometimes atoms pointing down, and sometimes the atom is pointing in the middle. So this is really a bona fide quantum phase. You cannot get that on a classical system because you cannot point in the middle, right? And I think that is pretty cool. It's not a long-range entangled phase, but definitely it is a quantum phase. And to wrap this conversation, I want to show you how to generate this on blockade real quickly. So, of course, that's if I'm sharing my full screen, it doesn't allow me to show things that I want to show. I will try once again. Hopefully it's not going to crash. And show. Here we go. So I'm going to pick a lattice distance. This is really taking a toll on my speed here. So I'm going to take a lattice distance between two atoms here. That's going to be 7 micrometers. And I'm going to enforce a blockade radius that I want to be given by this quantity here, which is basically 8.44, which once I divide RB over A is about 8.19. That, as you can see over in this figure, right, it's about this 1.2. Right? So this is where we are with that RB. And then what I'm gonna do is to so pretty much define my omega max. So create a waveform that looks like this. That pretty much what's gonna do is say, look, I'm going to. I think that I have to tell a little story. So here I'm just using the same formulas that we looked above, and I'm packaging them inside a Hamiltonian. Right, the Hamiltonian that takes the atom positions, which is a square lattice 3 by 3, takes the detuning delta and the amplitude omega, and here is how we are choosing these things, right? So I'm choosing my delta in a way that I start kind of all the way there, right? So with a negative value, that's going to be pretty much forcing all my atoms to be in the ground state. I want everybody, the ground state to be 0, 0, 0, 0. And then I'm going to crank this delta up, moving along this line of 1.2 RB, and then try to pierce inside this checkerboard phase by changing the parameters slowly. So I'm ramping my delta. I don't want this here. Sure. So I'm ramping my delta, right? And stopping basically at a value that's kind of delta over omega of 2.6 or something like that, while keeping my omega fixed in a value that's corresponding to this 1.2 RB. So I can take that, and on blockade it's pretty fun. Once you have a program set up, all that you have to do is to choose the service. The services that are available right now are blockade or bracket, because you can access our systems on bracket. On blockade, you can run on a Python backend. That's what you're seeing over there. On bracket, you could run either on their Python emulator, or you can just .aquila, and boom, just like that, it goes to Aquila. So you have to add your ID and your credit card. And you choose the number of shots, so how many times you want to repeat this. But roughly speaking, all that you have to do in the end is to take this output, get the report, and show the report. And we have a little function here that tells you what happened. Let's make this a little smaller, right? And what do you have in the end? I don't have any place to write, right? So you have a wave function that's going to be like a sum over coefficients and bit strings. And one of them is going to have the highest probability. It's the one that's going to be appearing the most. It's going to correspond to a specific bit string that if I chose well my parameters and my adiabatic protocol, this was an adiabatic protocol, that will correspond to our state. And if I come here and I click and hopefully everything is all right, ta-da, right? Instantaneously, you can see what's the highest probability that you're gonna get, which is exactly the state that I guess we were agreeing that is supposed to be. So we are preparing a checkerboard phase. And this is something that, again, you can just choose the backend to Aquila, boom, it goes to Aquila, and you can see this happen in kind of a real experiment. It's interesting that you can also sort, look at this, the second one, right? Second one is the one that you wanted, right? So not too bad, right? But you have no guarantee, right? You can sample different structures, and the same way you can sample this phase of matter, you could sample optimization problems. You just change the square lattice to West Lafayette map, and where you put the next, what's the store that you have the most here? Panda, I don't know, Panda Express, right? Where you want to place them, and now you place Panda Express on the corners, but not too close from each other, right? And you can solve your optimization of where you place your stores. And again, you can sample there. The third most likely is also a pretty interesting one, and so forth. So all of this is at qbook.query.com. I will leave it showing here. So you can click on introduction. I'm going to click introduction just so that you see. Right, so there's 2 chapters, and you can literally go through them, and the content is there. You can read. You can answer some extra exercises that are good for you. You know, exercises like lattice. Like sometimes you don't want it, but it's good for you. And you can take the quizzes and really get good at this. Yes. Lattice is not good for you. Maybe not for the palate. I like lattice. Kale. we will use kale. All right. We can take some final questions and wrap up for the day. It is a valid checkerboard, and the question that I have to you is, if you think energetically, are these 2 checkerboards that generate or not? You pay more delta in one of them, right? So they're not the. If I had a 4x4, I would have two possibilities there as well. Would they be degenerate or not? They would. Very good, very good. If I had an odd number in the x and y of atoms in the x and y direction, but it was very, very large, let's say like 30 by 30. We don't have enough atoms for that, but let's say degenerate or not. Kind of, right? Kind of. That's your thermodynamic limit coming to be. Right? So yes, you have to be careful with your boundary conditions if your system is small. But this one is not a ground state here, so you have no guarantee to prepare it by the adiabatic theorem. Zero, zero, zero. Yeah, that was the ground state. Here you're just doing a simulation, right? So there's no environmental conditions. But if you put in the real quantum computer, certainly you're going to be exposed to all sorts of decoherence, which in the end, I think that the main source is black body radiation. Hopefully, I think that's the correct statement. That's what the Rydberg states are most sensitive to. Yes. In the beginning of the talk, so we were looking at, was it here? Oh, first, like here? One more, here. One more is this. Yeah. And is this maybe this one? That's Aquila. but it's more like the size of this thing here, right? Like it doesn't look like it's reduced. Battery is not included. The size is bigger than it looks, right? Like, so technically there is another box on the other side of Aquila that contains the lasers, and this is pretty much the optics and the cell that contains everything. Yeah, the vacuum is in this. Yeah. Yes, but we are not controlling. I mean, we control it runs on room temperature, right? So there's like maybe a degree variation in the environment, like in the environment that this is in, but we're not cooling it down. Other than HVAC, AC. There is some shooting, but I mean, there's an MRI machine that operates in the building next door, and we operate it. So it's not that, I mean, not that sensitive, but yes, it is true. And so there's some kind of UV, kind of, it's not sputtering, but treatment that you can do on the cells to reduce the amount of kind of electric charge and statics that is in there. So those are all things that matter for the quantum hardware, absolutely. Yeah. Yes, two here. Yeah.
But when you get to these really ice states really close, so like what happens when you get to a peak orbital?
It's not gonna do that because of it's a 2-photon transition technically, and it's tuned this very kind of narrowly to that 70s. So it's not so easy to go to the P, because maybe you could go to the D because it's a 2-photon, but you could not go to a P state. I don't think so. I don't. Okay. I've not done it, so I cannot say. But as far as I can tell, I think that the risk of preparing there is low, because we always kind of cool the atoms down to the ground state before the calculation goes. So I don't think that we usually that's a big source of decoherence for this of imprecision, let's say, for this system. Well, you can look in the news. Japan just bought one. Yeah, yeah. You can look in the news and can see the type of deal that has been done with Japan for the prices. Misha is nodding, so one way, yeah. Between those.
But there are other, it's not clear that that's the thing. But right now, like connecting different applications, no, well, it's not. Well, no, conic links, you can do it, similar to what we've done with time. I think it's an interesting idea. What's actually kind of the new development there is that it turns out that it's advantageous to connect large processes rather than small, because basically the requirement for quality of your welfares, for example, go down. When you have logical qubits, large logical qubits that connection, that is actually much easier than small minus photonics and moving atoms are, like in the long run, if you want to think about tens of millions of qubits, possibly this technique.
There are other problems before that, I guess that's the point. Yes? The interactions.
Yeah, so this is what I talked about in the morning today. Sorry, out of my place today. But so the way how we do it actually is literally interact with logical qubits, allowing users to move them if the flow, with the period of check. And then what we do, we basically do this parallel, these so-called transversal gate operations, super efficient.
But the point is, it's this machine.
Yeah, you cannot do that with the machine that we're discussing yet.
This is not yet possible.
Yeah. Yeah. Looking at that. I don't know how's timing. Yeah, we are good.
All right, let's thank Andrew again.
Thanks, everyone.
Hello, everyone. I think that it's time, well, I don't think, I know it's time for the panel. So if you're a panelist, now is a good time to come and be a panelist. And if you're in the audience, it's a good time to get ready to hear a most interesting discussion. So, all right, we'll get started in a moment.
Great job.
Okay, I guess we're just waiting. It should be recorded, I think. Okay, and yes, so
I can't say forbidden things then.
That's a good point. So I said we should just not record it and have a very interesting discussion. Well, but actually, Morris, if you could on the mic, that'd be great. Okay, so I think we've almost got everyone. So I guess we're just. Are we waiting on? So we're just waiting on one more. So I'll just stand here. That's probably more. Yeah, but the connectivity is better from the front. So. All right, everyone, welcome to our panel discussion with all of our esteemed speakers from today. I guess there's already been a lot of introduction, but I think the best place to start is if you could very briefly introduce yourself, who you're representing, which company you're representing, and then what you think that the most major work your company is doing or organization is doing.
Ryan Laffler, co-founder, president, and CTO of Quantum Corridor. We're building distributed networks for quantum communication.
Hi, I'm Pedro, as just speaking. As usual, my voice. I am the quantum advocate at Quantum Computing. So this means that I run our education program plus a lot of our government engagements. And I guess what we are doing the best is to translate technology from university into products for neutral quantum computing.
Hi everyone, I'm Shravnik, spoke earlier today. I'm a quantum algorithms researcher at JPMorgan Chase. As you know, JPMorgan Chase does many things, but what I do in particular is research in quantum algorithms.
I'm Suzanne Yellen, I'm at Harvard. My background is theoretical quantum optics and quantum machine learning, quantum information theory, and I'm working on all of them. And I guess our most important product is educating students.
So I'm Misha Lukin, and I'm a professor at Harvard, and also I'm a co-founder of Quora Computing. And so my group broadly works on quantum systems for quantum computing, quantum simulation, quantum networking, and quantum sensing. And also does a little bit of education.
So I guess as the first question, there's a big jump happening right now from the academic research end of things into more commercial space. So for everyone who's running more commercial endeavors, how do you see the next few years of going from these smaller scale systems to larger scale systems, and what are the major risks you see in terms of making that like a commercially viable option, and how is it a commercially viable option today?
Great. So we're kind of seen as the infrastructure guys in different groups that we're a part of. One of them that I can talk about is the Block, which is one of the tech hub designations that was given in 30 different tech hubs across the United States. And our charter is to assist with commercialization where it meets private industry. And so the thought process is that eventually quantum will become distributed. It won't become clustered. In the same way that supercompute and DWDM has transitioned and evolved over time. And so it's the concept of one quantum computer eventually needing to talk to another quantum computer in this race for 256 usable qubits, right? And so where we see ourselves in the evolution of this tech is assisting with technologies that are present today, such as post-quantum cryptography and QKD, and then eventually a transition to the holy grail, which is entanglement. And so we see the future as distributed, because if you look at even traditional supercompute as it is, eventually, well, you take it back to even desktop computers, nobody fully really realized where computers were going to go, right? Nobody fully understood what the internet would bring, but everybody understands now what communications means to a connected world.
So as of January this year, Quera has released our own roadmap that, it's our technology roadmap for the next 3 or so years. And I think that the way, at least I like to read that roadmap, is that our vision for the kind of short to mid-term future is really reach the kind of commercial and openly usable machines that are really kind of on the everyday past the limit of simulation. Aquila by itself has some gist of that, and we want to push that for gate-based machines as well, and to bring the to users the capacity to run programs that are kind of either, some people call it LISC, like logical intermediate scale. Other folks actually call it the true NISC, right? So real noisy, but really intermediate scale noisy machines, but that are really past the capacity of regular computers. And I think that reaching that moment is going to be really a mark for the whole industry, because that's where you can really start to test all your quantum heuristics and things like Giovanni was mentioning in a scale that is kind of quotidianly, like in everyday life, beyond the classical computing. And we will advance from there.
So I think I'm probably the least qualified to answer this, because my particular team is, of course, positioned as a user of quantum computing rather than people trying to build it. I can say that the quantum communication part of our larger group has started to make some like well-publicized deployments, and like JP Morgan has participated in like deployment of like certain QKD networks, I think in the United States as well as in Singapore. From an algorithms point of view, I think just a few years ago, like all hardware was like essentially a fantasy, so we could assume whatever we want. So as real hardware gets bigger and bigger, I think we need to take our algorithms and try to make them smaller so that we can meet in the middle and actually do something interesting sooner rather than later.
So I'm probably not qualified to talk about any kind of commercialization at all. What I have been seeing basically all the time in the last, 3 decades or so, there were always, let's say until perhaps 10 years ago, there were people who said, oh, wow, I mean, we are nearly there. It's 2 more years and we can do something commercial with that, etc. And it was always this kind of empty hopes, and it was all so slow, and it was everything which was found new was that it's really much more difficult than we ever thought. And I think since, I don't know, 2 years or so, perhaps a little longer, I think we are in the opposite regime. People are all saying, oh yeah, nothing useful will come out in the next 50 years anyway. I know we need to, in principle, prepare our infrastructure, but I mean, we have seen how this goes. And right now, I see the field evolving in huge jumps, and I think there are a lot of groups and a lot of companies, etc., at the brink, either already beyond or just at the brink of kind of really doing something useful. And I think that the progress will be counted in months and in years, and definitely not in decades anymore.
So I kind of, in my opinion, this the field now is at a kind of very special point in many respects, and it is, in fact, one of these aspects is that it is clear now that it is still the frontier of basic science, and so a lot of developments which will happen, in basic science and in academic labs. But at the same time, it's also very clear that industry will play a major role in two aspects. First, in engineering truly large-scale systems, and also in basically figuring out the first real industrial applications of quantum computers. So this the fact that the field is kind of struggling this interface is actually kind of a challenge, because usually, for example, you really do system engineering, you don't want to do science in parallel. So for many people, it's scary that we keep inventing things and kind of changing this kind of a slope of the progress. But I think it's also an opportunity. So that's why it's actually fun to work in this field. I do think that, the applications, at least kind of in the realm of say simulations, kind of quantum physics, but maybe also quantum chemistry, will likely start to emerge. And I think next, I would say 3 to 5 years will be a very special time for this reason. Yeah.
So I have one very short technical question, which is mostly for Ryan and people who are building the computers. So you mentioned that you want to build a quantum network infrastructure, but there are so many varieties of quantum computer. How do you propose to standardize interface? And so, for example, maybe Quera might have a comment also, and Professor Lukin, on how that could be accomplished, since they're so tied to hardware.
Thank you for the question. So we have different segments, we have different products that we're focusing on supporting. So the first foundational piece is that we have coherent optics, which is kind of the foundation for quantum comms. Anything supporting the BV84 protocol, whether it's post-quantum cryptography or QKD. We have our coherent wavelength, which is essentially a number of different separate wavelengths that are combined into one. And so with that, we can support what we hope to eventually be the instantaneous transfer of information, all states of information at once. And we support that by pushing QKD over the network. Of course, there's relative issues with that when it comes to degradation or attenuation. Something that, and then there's also the standard that's supported today, which is post-quantum cryptography on raw spectrum services or layer one. Where the industry will evolve is to support a different product set, which is essentially transmission of information through entanglement, full entanglement, which doesn't have the distance sensitive thresholds that the other two types of technology have. So we don't want to be in a tech race where we see, we're married to one solution, call it beta or VHS, right? And we die on the vine with that product set. So we want to kind of have lanes of the highway that support quantum transmissions and quantum comms, and support an environment of neutrality for that. And so that's our goal, is to support where this industry might be going.
So as networking goes, I think that we were discussing this earlier today with Misha. Some students were asking, right? This is important, evidently, for scaling up at some point, right? But not before the tens to 100,000 qubit level, as far as a neutral atom system goes. So I can't. How is it? I can't confirm nor deny that we are working on that right now. We hear of IonQ definitely caring for networking their systems, but again, if that happens, they're going to be networking many small few qubit systems. That's going to have the challenges of its own. And we hear also of other companies in the neutral atom space in France also starting to announce partnerships to start thinking about networking. But I don't think that we have any kind of public information about networking at the moment.
I can comment kind of from two perspectives. So first of my research group is doing work on quantum networks. And in fact, we have a new paper coming out, I think the next couple of weeks in Nature, which demonstrates for the first time a kind of a real kind of walled quantum network, basically connecting two quantum memory nodes distributed by the kind of deployed fiber in an urban environment, and it's actually, so the two nodes are actually on Harvard campus, but the fiber network kind of wanders around between Harvard and MIT, crosses Charles River 6 times, then passes by Quera building just by accident, and then comes back, So, but that being said, unless you specifically are interested in QKD, which actually is a little bit, a matter of, taste. So, for example, I think U.S. government is not necessarily interested in QKD, unless if you take QKD, apart. So it is true that, quantum networks eventually will play a role, but it is, very likely in that kind of setting that, quantum networks only will become relevant, once we have actually reasonable scale quantum computers, and, it is tempting to say that, you don't discriminate, you will be able to connect to any quantum computer imaginable, but it's not, unfortunately, it's not like this in practice, So certain types of qubits, for example, superconducting qubits, are much harder to connect to optical networks, as opposed to, for example, neutral atoms. So, that is true kind of on one hand. However, if you really are able to build, good interfaces, then connecting different types of quantum computers indeed is not, that hard. And the key ingredient for that is a frequency conversion technique, which you can do at a single photon level, and now can do it in actually quite high efficiency. In fact, this is one element which we used in our experiments, this urban network experiments. And I do think that, these capabilities not only provide a route to building, bigger and better quantum computers, but they also provide opportunities for novel applications of quantum computers. So in particular, one research direction is called blind quantum computing, and that's the idea that you can basically, submit a job through quantum network on a quantum computer, where basically, you are guaranteed that the person who is running quantum computer will not be able to find out what calculation you are doing. So that actually addresses a very important problem in computing, which basically, is one of the reasons why not all jobs now are outsourced to like Google or Amazon Cloud, or Microsoft Cloud, because, sometimes you want to actually do things which you really do not want to reveal to others, right? And, like it actually turns out that classically it is, of course, in principle possible. The way how you do it, you basically encrypt this computation, and, send it, but actually working with encrypted classical, computers is actually, algorithms prove to be challenging. In fact, this is an active research topic in classical information processing, and there is a lot of work now being done, but nevertheless, despite of decades of research, the solution has not been found. So in a way, working with the quantum computer, offers, really immediate kind of direct advantage. In fact, for algorithms like this, even the path for useful quantum advantage can be shorter, provided that you, of course, build, everything already in place than for just, plain vanilla quantum computation. So, but, again, so these things will really start paying off once you have kind of quantum computers at scale, and you can connect them also in a way which is kind of parallel, right? So talking to one qubit at a time will not, do. So, yeah, that's, I think that's both challenge and an opportunity.
Can you expand on this? You mentioned that
if we could, in principle, build the interfaces, we could connect them. But different technologies have very different repetition rates, right? So what is? Do you think that that's becoming a big problem? Would become a big problem?
Yeah, so what Pedro is referring to is that basically, like you can have different types of qubits, which can have different, for example, cycle times, and you would need to somehow synchronize them. Yes, but you would, you would need then to build like interfaces for these different computers, which would somehow respect that, And so, for example, you might need to use some kind of memory buffer, right? To store these qubits, this memory buffer, to be honest, might also be needed if you want, for example, to do computation with error-corrected qubits. And in fact, developing these kind of good buffers, again, while, keeping in mind you want to do things at scale, I think is a very active research topic. But, these are challenges, but also opportunities here.
Since we're on the topic of networking, and I have apparently Professor Lukin's group has done urban deployment already, and I assume Quera, despite not confirming or denying it, is involved in this. Is there anything you have a wish list for your colleague Ryan, who is seeking to develop these types of networks? Like, is there anything you could suggest to him to help him in becoming a useful provider of such infrastructure? Without confirming or denying anything, of course.
I mean, if it's about a wish list, I can say, like, let's put a computer in your network so that when we are ready with the interface, we can interface them, right?
At the end, you care about, the resources, basically a high rate of entangled bell pairs, right? They're the currency in quantum networking, right? You can provide some ways to do it, to distribute them, and maybe some ways to correct the losses, it's a high, kind of, at a high level, that's what this, then maybe memory buffers for some systems. These are the things which are, but, yeah, they are kind of generic, but of course, to make them useful for any given kind of platform, you would have to really work, with the users,
Perhaps if I may, this might be quite a bit down the line. Eventually, we might want to connect more than 2. And 3 is also fine. You can still do that. Let's assume 30. If you need all-to-all connection in 30, it's getting already a little painful. So the question is, how can you connect via different nodes if you don't have all-to-all connections?
So, there's different network topologies today in supercompute, and if you follow the patterns like mesh networks or frame relay, right? And there's, essentially even MPLS, it's an ancient concept, where you have tunneling that's pointed. There's things that we could do with end-to-end, A-end to Z-end networks with coherent optics. There's things that we could do with just raw transmission of light and devices on either end. But without being on the hardware side, I'm not going to speak to that. But there are certainly things that we can envision that would kind of mimic the concepts of traditional supercompute network on a quantum scale.
Right. Well, I guess we're sort of touching also on, I've always been curious because I've known the Quera story from very early on. Actually, Alex Kiesling and I went to undergrad together. And one question I've always had was, how is the transition from academia to industry done? And how is the relationship currently between industry and academia? Is it going both ways, as in the academia is learning from Quera techniques, and then is it going back and forth, or is it sort of one-way transmission from academia to industry?
So I feel like it's being a lot of cross-pollination. At least I would say so. It looks like Misha agrees. I have a conflict. But you can see that even on recent publications, the different teams sometimes end up publishing together, right? So there is a lot of cross-pollination. I think that.
President, could you give a specific example of a particular type of this?
Yeah, I guess.
Make it more concrete.
I guess this recent work on these 48 logical qubits that it used some devices that Quera built on Misha's lab. So very explicit, very concrete.
Yes.
And I think that I mentioned in the beginning of this, right? That it's all. I think that what we excel at doing is technology translation, right? So an experiment has become a product that is, reliable, stable, can be utilized, et cetera, et cetera, et cetera. And even though commercialization is still a tricky topic for quantum computing, because you have to understand the customers and the needs, so that everybody gets what they actually need and want. Mm-hmm. I think that this translation layer is very important right now. I don't know, Shivani, if you, on your experience, you're also in industry.
Well, not quite in the same way. I think, well, for me, the transition is, well, I barely noticed it. But I think from our point of view, I think the reason to have a quantum algorithms research group at, say, a bank or other industry is, well, partially to take people who know something about quantum algorithms and find out like whether you can just use them for something. But as I discussed today, maybe that is not quite the case yet. But I think the other direction is to identify what developments in algorithms would actually be useful, and potentially to guide the broader research community on what questions perhaps are very valuable to look at. And I think, at least speaking for myself, I've noticed, and I'm primarily, like, even within sort of algorithm space theorist, but like just speaking like in theory terms, there are very concrete like questions in theoretical computer science that are not really mainstream because they're difficult and there hasn't really been a reason to look at them. But I think with like sufficient use case backing, you can convince the community that here is this like completely abstract mathematical statement that is very important, and I promise you it is important, but you're super smart, so will you please solve it? So we're trying to get people on board.
Do you have also an example where like you feel like the works of JP Morgan influenced the service of hardware companies, or something that affected the hardware in any way? Just out of curiosity.
So when it comes to hardware companies, I think, like, as you know, right now we're at the point where we use hardware primarily for demonstrations of algorithms, right? So there'll be a paper that talks about an algorithm, and there'll be simulations and so on, and then there's a hardware section that runs, something. And initially, we were trying to do the to use the hardware off the shelf as much as possible, because of course in the long term that is the ideal way to do it. You would like to be able to develop algorithms without ever communicating with the hardware service providers. But I think for some larger experiments, like the work I talked about today, which is this big QAOA demonstration, that involved explicit collaborations with both the hardware providers as well as the providers of the classical supercomputing, which is Argonne National Lab. And just like classical supercomputing, it's very difficult to, just decide I'm going to do this on the supercomputer and sit down and write the code. It works very differently than programming for a regular system. So it's similar, I think, still for quantum hardware. I think, like, so far, I don't think we've done anything that would qualify as what people call co-design. But partially because I think it's too early even to say what the right co-design should be.
Kind of disagree.
Right.
Yes, I think it's. I think it's not early. That's now what will the next few years, the real progress, the real kind of breakthroughs will be made through co-design. I mean, it's like early computers. They were really optimized for some specific tasks, and you really need to think about, particularly if you would like to involve algorithms with deep circuits. I mean, the co-design, I think, is absolutely the key.
Yeah.
Perhaps I could add a few words. I think I agree with what you say there. What I meant was that we have not had yet a concrete application where we thought but I think the fault tolerance is a great place to start, right? And I think I touched on this very slightly. This also shows up with these QA demonstrations that like we have a path to fault tolerance, but we're not going to be like, I think I would like to think that fault tolerance means I can now do as many tickets as I want and run any service, and it's great. But in reality, it probably means that there's a hefty cost associated with each thing. So you have to think about things like partial fault tolerance, perhaps like some error detection, what codes fit what algorithms, and so on. And so there's a lot of potential there.
Maybe someone else can. So I think maybe others can elaborate, but for the example that I gave, for example, this complex sampling algorithm which we implemented. So if you would do it, in a kind of conventional way, like people, for example, talking about using surface code and using this T-gate, and it basically, this algorithm, it basically utilizes, close to 1,000, 2-qubit gate operations, to do it through this conventional kind of ways, is extremely hard, So, and basically here, what we found a very clever, very efficient error correcting code, which does not allow you to do general computation, but it allows you to do this specific computation, which is called so-called IQP sampling. So it's basically kind of a, it's a sampling algorithm where you sample from some kind of Gibbs distribution, but this Gibbs distribution basically given by polynomial, and what we can do using this algorithm, using this code and using specific operations which we have natively enabled, available, we can basically enable realizing, this polynomial and sampling through this kind of, and that's an example. But I mean, there are others. There are other cases which are. I mean, this is not practically useful what we have done, but I mean, there might be examples which are actually practically useful.
So Moti, in the morning after my talk, asked for drug design. Obviously, drug design right now is still very far away from a practical use of quantum computer, but we are actually having a fairly large collaboration with other scientists right now, but increasingly kind of industry collaboration comes in, where we are really starting from what is the problem that we can solve? What can you provide us? For example, what kind of knowledge of molecules do you and you and you have? How do you and you and you calculate that typically? What is your and your hardware, how to do that? And then you really go in circles and kind of try to optimize that altogether. And this is actually happening. It is not happening to the degree that we can say, oh, this drug came out of our work. This is still a little bit down the line.
I think that there are a couple things that are, I don't know, totally my opinion, right? But I also find that, so first of all, yes, there is also the side of co-design Susan is just mentioning. It's not just like theory on one side, hardware on the other side, but there is also the theory, the user, the application, the different domain specialists that get involved into this. But I also feel that not every hardware, if you are bringing the hardware into the scheme, is as amenable to co-design as others, right? Like any hardware that you have to, whenever you need to do an adjustment, you need to kind of put on CAD, design for half a year, send for production for another year, test, validate. The cycle is too slow, right? So I think that a big advantage of atomic base, and I am including ions here also, is that I think that the user has a kind of a software level access to the hardware capabilities to kind of change a little bit and to adjust things as needed. So there are some advantages in the technology that I think only now are also available. So I think that I agree with Misha. That's one of the reasons why now is a good time for thinking about this.
So what at the kind of level, what you would like to do is actually, I mean, you have some like very, special but very exotic, this, like resource, right? And you don't want to use this resource to solve, like, to do stuff which is not like kind of essential, What it means in practice, you'd like to basically outsource as much as possible of what you do to a classical processor, both in kind of formulating your problem, but also even in running your algorithm. You would like to, for example, do, push as much, for example, decoding for error correction as possible to a to a classical computer. Of course, it eventually might become hard, but basically that's kind of the idea, right? So that's, yeah.
So speaking of co-design, you mentioned that early computers had a lot of this co-design going on, but a lot of the reason for that was most of the computers were born as part of the military with very specific application that they were funded and then theoretically constructed for. Do you have any idea of any sort of problem that could be like that for quantum computing at the moment that can sustain it over the 10 years or so until it reaches this more like less co-design reliant stage?
I guess that Suzanne gave a good talk about about that. Maybe one.
I mean, as I just said, I think drug design is definitely one of them because there's a lot of money in the pharmaceutical industry, and tons of interest of all sides. For example, to cure cancer, right?
One should realize that these things are hard.
That's why he said over decades, right?
And in particular, the problems where quantum computers really excel are problems where you have strong correlations, right? I mean, that's why, for example, some early material simulations are already, I would say, bearing fruit now. But, there are cases, apparently, we are told that, in these molecular systems where strong correlations play a role, and some of them are, important,
Perhaps one thing, if I could add, I think there's a degree to which, say, if you look at chip design, where like some of this co-design sticks around even after the field has become extremely mature, when you're operating at the limits of what computation can currently do, right? Like you can go right now on Amazon and buy a graphics card that will tell you that it's specifically made for ray tracing, or if you're looking for like to do train LLM, like that is made to do attention computations. And that is because like these things are really difficult to do and people want to do them on unimaginable scales. So even to this day, I think the best solutions for attention computation, rather than being algorithmic, are actually just thinking very carefully about the chip design and how you do your caching and so on. So
in terms of communication systems, QKD is kind of disputed within the DoD DITCO ecosystem now. They view it as another point of compromise. But there is development underway with DARPA. And certainly in the financial industry, QKD is seen as an emerging security standard, right? So there's use cases now for those type of applications, and they'll be replacing other security authentication measures eventually on these systems. And so, what Sienna, for example, has poured hundreds of millions of dollars of R&D into QKD in general. Yes, it means quantum computers can talk to some degree. How much of that is actually functional, how much of that is useful is the question. But if you can couple the QKD for just the security portion of it, and then couple that with regular DWDM
that they will also feed back on the quantum computer. I think that that's how I see it.
I think, like, regardless of how powerful quantum computers would be, it still feels wasteful to use, decades of physics and engineering on running your note-taking app. So you should probably only do interesting things.
Yeah, I feel that way when I use an i7 to read PDFs.
I have to say, I mean, there's one very obvious application of quantum computation where exactly that is the case, where it's specialized. And that is where you have actually, rather than classical I/O, you have quantum I/O. That means you have to build your quantum computer a priori such that it takes certain quantum signals and it potentially spits out certain quantum signals that then connect to something else. That, I think, by its very definition, and I mean, what Misha mentioned before, quantum sensing is at the moment, the most obvious kind of direction of that. But I think I cannot even imagine any setup where this would not be custom built for whatever kind of quantum input or output you would get.
So I agree completely with everything what was said, and like there's no, but I should point out that, like, if you look like 20 years back, there was another example, where, it was exactly like this, in a classical processing, and that example was called GPU, so which was kind of in a corner of your chip and just, used by some very few people, and look what happened, right? So it's very hard to expect, anticipate all of these things, but that being said, certainly our current understanding is exactly what, quantum computer as a coprocessor, or maybe, for example, for distributed sensing applications, things like what Susanna has been mentioning. So, I mean, that's our understanding, but, who knows exactly, yeah.
Well, yeah, actually, I'll probably ask Morris, since I don't know what exactly the time limit is for this. So Morris, you'll have to cut me off when we're done.
I'll give you 2 more minutes.
Okay, we have 2 more minutes. So I guess I always want to ask this, for people who are developing all these algorithms, computer, what is something from other platforms, other than your own, that you really wish you had? And that you, like, for example, in our group, we work for photonics, we're always wishing that we had better, more efficient ways to do entanglement between multiple photons or have larger cross sections. But like, what would be something that you really wish you could get from another platform that you're like, oh, it would be so easy if I had that?
So today, we just are supporting coherent optics, RLS FlexGrid coherent optics that go to wave servers. But there's been something that's been resounding throughout this conference, really, which has been having quantum memory, a platform that has quantum memory, in trying to establish usable qubits across the network. So that's something that we've got to vet out and explore, and maybe have some conversations with some vendors here today that can help us with that.
I'm gonna try and get creative here. I could say speed, but what's the fun? So I think that classical computers have, and that I feel like we don't. We still program quantum computers as if we were programming classical computers with Boolean logic. Yeah. Right? We don't have a classical computer. You learn classes, methods, if statements, and loop statements and whatnot. You don't think of gates and XORs and ANDs and NANDs. So I think that one thing that would be quite interesting is what is that? What the hell?
We can come back to you if you'd like, Pedro.
It's a level of abstraction in the language. Yeah.
So maybe an angle from theoretical computer science, I think, is when you do classical computer science, you get very, very attached to the Church Turing thesis, all right, which allows you to treat essentially all abstractions as things you have, right? If you can write them down and like prove certain properties about them, you can go ahead and like build arbitrarily complicated structures on top of these properties, and whatever you have, it may not be something that you can immediately like code up and run like very efficiently, but it's going to be something useful, and someone else can figure that part out. I think perhaps in quantum computing, like partially because like merging also as a scientific and engineering field at the same time, this is less the case. Now, of course, like if you look at like computer science papers from like the 50s, it was very much the case in computer science as well. But sometimes it's nice to just be able to use whatever constructions you want, write down an algorithm, and be sure that someone can one day run that algorithm, which I'm not sure we're at, but it's also an exciting sort of opportunity to refine the way we do computer science, and it raises some interesting research questions as well.
I have to say, I mean, coming back to the question how you actually post it, what would you like from other platforms? I've been working with various platforms, but mostly actually, I have to say right now with the Rydberg array. And in particular, we are running right now experiments on Aquila. Definitely what we miss most is single qubit control. I'm perfectly happy with having mostly global control and being able to, in principle, multi-qubit, which you effectively have if you have a Hamiltonian. But a little bit of kind of separate kind of single qubit control would be really nice.
It's out, huh? Local detuning is out.
Yes, I know. This is we are jumping on it like crazy. I can tell you that.
Yes, maybe I kind of can shift gears a little bit. So what I think, one area where I'm quite envious, and that's related maybe mostly to classical computers, is a degree to which these devices are engineered. So I think we're nowhere near what can be done, and maybe some of the other approaches like superconducting qubits are a bit more engineered. They're still far behind where classical computers is, but I think here I see really kind of enormous potential. But again, what I said, the kind of most interesting thing is that we are sort of not quite done yet with science. And by kind of gaining scientific insights, we often can really circumvent decades of engineering, but I mean, sort of combining, nevertheless, while pursuing that, but combining them with kind of cutting edge engineering is really a future,
Yeah, I also would like to order my quantum computer on Amazon, but.
You literally can.
All right, Morris, I would have one more question if I can get away with it. So you have, in the audience, you have lots and lots of, young researchers that are always looking for interesting questions and topics. If you could make a recommendation, each of you, for a topic that you think would be good for any new student to go into and to really think about how to make an impact there, which topic would you suggest?
I would encourage delving into the concept of full entanglement, obviously.
Hardware, I think I've been a big fan of continuous reloading. I'm pretty curious about strategies that people are working on it, and I think it will make a big difference for neutral atoms. Theory, okay, I'm biased, right? I am a physicist, and so look, quantum dynamics. I mean, it looks like the earliest, the easiest entry points to do something. I mean, Suzanne was showing the graph from this paper earlier today, right? It seems like a place to be.
It's tough to think of one. I think one thing that is sort of very concrete, but I've just heard today, like maybe some counterexamples exist, is like if you have like these methods for getting, quantum heuristics, say QAOA or quantum annealing or whatever your favorite model is. I think two things are important there. Like one is you should not have to optimize parameters. And it seems that you don't have to in a lot of cases, but it's not clear that this is always the case. And it would be very nice if someone could give like an argument that you don't have to worry about it for your favorite combinatorial optimization problem, as long as you can go up to say n equals 20 or something. And the other is how to deal with constraints in a natural manner. So when you're dealing with unconstrained problems, these heuristics are very clean. Once you get to the constraint setting, classically, you're often left with branch and bound, which is completely different and doesn't have a good quantum analog, and like some very special tricks with penalties that usually don't work. So generically introducing constraints, we've tried in a few different ways, but I think it's still not quite solved.
So as I said before, quantum AI, quantum IO is one. The other one for me is error correction analog systems.
So I would maybe say that, at this point, like all of these things which have discussed, in this, sessions today in the talks and in this panel discussions are really, very exciting directions. So you can pick any one of them. The only thing what you should try to do is to become world's best expert in this, and also have fun with that, So, yeah.
Well, I think we should all thank our panelists for their time and for your insights. And I would especially like to thank you all for satisfying my personal curiosities.
All right, let's thank you to the panelists. We have one more talk left for today. If you are curious about Professor Chris Monroe's talk, that'll be happening. That's been rescheduled to tomorrow due to traveling conflicts. But tomorrow's talks has multiple photonic-based topics and optics-based topics. And right now we got an industry-related expert here. All right, so our final talk today, or our final demo today, I should say, is from a representative from Xanadu. It's going to be from Nathan Kilran. He's the co-CTO of Xanadu, responsible for the company's software division. He has a good fortune to work with many talented researchers, developers, and community builders to create foundations of the present and future quantum computing software stack and photonic-based quantum computing. Also, a logistics announcement. If you're staying at the Hilton Garden Inn and you prefer to have rides for transport to the venue tomorrow and Friday, there'll be shuttles coming in and out between 7:30 and kind of 8 o'clock window, maybe a little later as well based on need. So just so you know, you can hang around the lobby and there'll be multiple trips coming through. Also, if you weren't aware, the student and postdoc dinner is at Walk-On in the PMU tonight. Open to everyone here, and it's going to be starting at 6 to 8, so come through anytime. And they have our card info, so you just come and hang out and order foods and drinks.
Hi, everyone. Thanks to everyone who's stuck with it right to the end and even through the very fast classical computer here we had to get set up to show this talk today. So I know I'm the last speaker of the day, and so I'll try to keep it tight and try to focus on just the main points. I won't go through a coding demo or anything like that. Things can get bogged down when you get to that stage. I'll just give you the high-level overview. Try to tell a story, but not get too caught up with things that could just prevent us from going to dinner time. So as introduced maybe about 5 minutes ago, my name is Nathan. I'm the co-CTO of Xanadu, and one of the things that my team works on at Xanadu is Penny Lane, which is a quantum programming software development kit. So if you want to do research in quantum computing, we definitely encourage you to check it out. It's been under development for more than 5 years. It's quite popular. It's got maybe about 30% of people working on quantum computing research reporting that they're using it. And there's lots of features, both kind of standard features and more advanced features that I'll outline during this talk. And then I'll try to take a break in the middle if you have any questions, and then I'll get into some wider parts of the Penny Lane ecosystem to finish the talk. So I represent Xanadu, and if you haven't heard about Xanadu, we are a quantum computing company based in Toronto, founded in 2016. We've grown quite a bit. I joined as employee number 10 or so, and now we have about 200 employees, which is just kind of amazing to go through that journey. We're known for three main things. One is our hardware, photonic quantum computing hardware, for our software, in particular Penny Lane, and we do a lot of quantum algorithms research and development, especially in quantum chemistry and quantum machine learning. Today I'll just focus on that middle one, the quantum software that we work on and build at Xanadu. So Penny Lane is the where all of our software efforts are going these days, but it's a full ecosystem. It's not just one library. It's actually a bunch of different tools that can work together. So you have the kind of Python front end. This is for anyone who wants to write a quantum program. This is the first place of access you'll go. But if you want to run high performance simulations, you're going to need a simulator that's written in C++. And that's our Lightning suite of simulators. You can run on GPUs, you can run on CPUs, you can run on HPC centers. We also have a new part of the ecosystem we've been developing for the past year or two called Catalyst. And this is a quantum compilation or a hybrid quantum classical compilation tool. And this is what allows your code to run potentially 100 times faster just by taking a look at what the code is trying to do and either optimizing the quantum circuit or optimizing the classical parts around it. If you're lucky enough to have access to various quantum hardware or simulators from all the different vendors out there, you have plugins in the Penny Lane ecosystem that you can use to tap into those and run your program on pretty much on any one of those, including some of the more unique hardwares like neutral atoms we've heard a lot about today. And then even if you're not programming yourself and you're just kind of learning, or you're trying to understand certain ideas and you don't want to read deep into papers, we've got a ton of online resources available at pennylane.ai. It's not just documentation for the library, but it's actually got lots and lots of content and educational materials if you're interested in that kind of thing. So I'll start with Penny Lane itself. As I said, this is a Python software development kit. It's in Python, and pretty much everything's in Python these days. I know that the guys at Quera are doing a Julia library. Juliet's great, but I think Python is still the dominant one, and it's got a great scientific ecosystem that you can tap into. Penny Lane is open source. You can check out all the codes for the past 5 years on GitHub. There's over 170 people who've contributed to it. It's very modular. We try to make it so that it's not too restrictive and not trying to assume what you're trying to do with your particular use case, but in providing all the building blocks that you might need for different potential use cases. That's really what can empower better research, is if you don't assume too much about what the user is trying to do, but you just provide powerful components. And then one of the features of Penny Lane is that it's differentiable. So this actually came from Penny Lane's history. Originally, it was just a quantum machine learning library, and it's grown to a more multi-purpose general framework. But in quantum machine learning, the key thing you need is to be able to optimize and train your quantum circuits. And so you need to know, is there some parameter value that I can change such that I increase or decrease this cost function? And for that, you need the derivative your circuit in some sense. So PennyLane has this kind of as a first-class feature that's been built in from the start. One of its very unique features. As I mentioned, there's tons of plugins to connect throughout the entire ecosystem. So we had a few speakers from Quera today. You can connect to neutral atoms. You could do what we call pulse programming there on the neutral atom systems. You got trapped ions, you got superconducting qubits, photonics, a number of simulators, but also a number of classical scientific computing tools or machine learning libraries like TensorFlow, NumPy, PyTorch, or JAX. So it's designed in a way to integrate with these very naturally. Maybe speaking a bit more to our credentials, it's a very strong community. So we have about 13,000 posts on our discussion forum. So these are users asking questions like, hey, what's going on with my code? Is this a bug? How do I do this? That's quite a lot. That's over 5 years. 13,000 posts is quite a bit. And I just wanted to really emphasize that we do a lot of work to support the community to make sure that if you ask a question, we'll answer it. We try to help you. We use the library for sure. And we've been, over the last couple of years, really engaging with university partners, and we now have 50 plus partners, including Purdue. So what does a PennyLane program look like? Well, first thing you need to do, you got to be comfortable with Python. Assuming you're comfortable with Python, assuming you've installed Python and the standard kind of environment that comes with Python, you'll have to install PennyLane. It's just a one line from the terminal, pip install PennyLane, and then you can start writing your first PennyLane quantum program. I want to kind of call it out because it's a bit different from the other software libraries you may have seen for quantum programming. So first thing you might want to do is declare a device. This is where you want to actually run the quantum computation. It could be a simulator, and there's some built-in simulators. It could be a hardware device. It doesn't really matter. You just have to tell us which one you want to do it on, and we'll try to delegate the computation to that device. And then here's where we're kind of different. We treat a quantum computation as a function. So what is a function? It's just a mathematical object with inputs and outputs. And any quantum computation can be thought of in that way. There's some parameters coming in, there's some data coming in, and then there's some results being read out from the quantum circuit, either as an expectation value or as samples or as any number of quantities that you might post-process out of measurement results. So as long as you create a function that has inputs and outputs some sort of equivalent to what a quantum circuit outputs. And then inside that function, it's a Python function here. The body of the Python function can just be gates. You just kind of say, I'm going to do a Rx gate or RY gate. And these gates can be parameterized. They can act on different wires. So the wires are like the lines in a circuit diagram. That's this basic syntax. You treat it as a function. And why do we do that? Well, once you treat it as a function, it connects so much easier to all the rest of software. All the things you want to do with software, mathematics, scientific computing, if you treat it as a function, it really connects well together. Let's see if I can shut this off myself. There we go. So treating as a function really gives you the power to connect to NumPy, to PyTorch, to TensorFlow, to JAX, and just treat the quantum computation as a step in a larger hybrid computation. So you get the hybrid nature pretty much for free. You might want to take gradients of your function if you're doing a QML workflow. That's easy because I've already designed the thing as a function. So that's kind of the only kind of mental twist you need to make in your head to use PennyLane, is to treat quantum circuits as functions. Maybe just as an idealization, we call this function a Q node, and you have to kind of tell PennyLane that you're making this Q node around your Python function. But really, it's just something that can have inputs, and then the output should be classical. It should be read out from a quantum circuit, but it's finally a classical value that gets read out. So the inputs are two types. It could be data, or it could be parameters. So the data could be like the angles needed for a molecule, a chemistry problem, or something like that, some sort of hard data. Whereas the parameters are something that may be a bit more flexible. Maybe you want to keep a certain architecture of gates, but you're allowing the parameters of those gates to change. So those parameters are treated as kind of more abstract objects that can be tuned.
So each parameter will have its own Q node, or the entire layer will have one Q node?
The entire quantum circuit is treated as one Q geometry node, and you can put as many parameters or inputs into that as you want.
So then there cannot be any sharding.
Sharding.
Yeah, and no sharding because they cannot put some different layers on different networks. So there's no multiprocessing that can happen there.
You can do that. We can do batching, that's what we call it, and there it has to run the computation either on multiple simulations in different threads or in sequence. So yeah, sometimes you can't put it in at the same time. If you have multiple parameters you want to try, you have to run them sequentially or parallel. So we designed these things this way, as I said, to really empower quantum machine learning frameworks. So in quantum machine learning, you treat the circuit itself as a model, and that model can have some free parameters associated with it. You want to tune those parameters to minimize some cost function. If you look on the right-hand side here, basically any circuit is a unitary applied to some input state. Some unitary transformation, some Schrodinger dynamics that take one discrete step from state psi to state psi prime, but that unitary itself can be parameterized. And so you want to be able to compute the gradient of some cost function with respect to those parameters. Again, this is something that's built in as a kind of first-class citizen of Penny Lane. Any program you make, you can almost guarantee that it's going to be differentiable by default. Even if it's not really for QML, if it's for quantum chemistry or quantum algorithms development, anything you might want to think of, this is just a free feature that comes with it. As I said, the other thing that comes really nicely from the functional approach is hybrid computations. Hybrid computation, you just end up having functions that are classical, functions that are quantum, and you can connect them together. And they can be connected together kind of in an arbitrary data flow graph. It doesn't have to be a linear sequence of steps, but you can have things branching off in parallel. You can have converging, two nodes coming together to a singular node. The only notion is that we have this quantum node, and that's just kind of one of these nodes in this larger graph that has to be executed on a quantum circuit. But otherwise, just a sequence of steps, a bunch of composed functions in order to do a hybrid computation. And because we've built in the differentiability of the quantum nodes of the circuit, if you're using machine learning library, the whole end-to-end computation with all the classical processing, all the quantum processing can be trained. So as I mentioned, quantum chemistry is one of those newer application areas that we've expanded Penny Lane to be very useful for. So some of the kind of things you can do if you're interested in quantum chemistry, and I know there's some people here at Purdue who work in quantum chemistry, you can easily import chemistry data. You don't have to necessarily start from scratch. You can work with pre-existing data sets that we've built. There's different mapping available. So a quantum chemistry system is usually described in terms of creation and annihilation operators, fermionic operators, and you want to port those to live on qubits. And there's not just a one-to-one way to do this. There's different possible schemes to do this. We provide those schemes kind of for free. You don't have to do it yourself manually. So Jordan Wigner is a popular one, Bradley Kitaev. There's one called Bradley Kitaev Superfast as well that's available soon. These things are just out of the box in there for you. And then more advanced techniques like qubit tapering, or you might want to have a structure in your circuit that kind of obeys the fermionic symmetries, right? So particle number conservation. Well, that's a particular subset of gates that you can use there. And those gates are available also in Penny Lane. So basically anything you want to do in quantum chemistry on a quantum computer, you can do very easily. All the tools are available there. Plus it's fully differentiable. Maybe you're not interested in quantum chemistry, maybe you're not interested in quantum machine learning, but you're just doing general quantum algorithms work. Well, we also have algorithms toolkit. Some examples here, for instance, the quantum singular value transformation. This is kind of a unified framework. It's come out in the past couple of years to view a number of existing textbook algorithms as special cases of the same quantum singular value transformation, where you kind of embed a system into a unitary, and then you apply some transformation that applies a polynomial to the eigenvalues of that embedded matrix. That's what's shown by this like A and then PA here. There's a whole bunch of different subcomponents of that, and all those are available as well. One feature that's really upcoming, and I'm excited about this one, I've heard a couple people mention it today in the panel, is the ability to measure in the middle of a circuit. So in a quantum computing textbook model, measuring the middle of the circuit is not a problem. It's allowed. And you can even feed forward the result of the measurement process to later on apply some transformation to remaining qubits. This is a very important primitive in error correction, for instance, if you want to do syndrome measurements and corrections. But a lot of hardware initially did not have this feature, and now it's coming online that this hardware is providing this kind of features. So in Penny Lane, we want it to be best in class for mid-circuit measurements from the software side. So anything you can think of doing with mid-circuit measurements, you should be able to do easily and run on a simulator or run on hardware. So you might want to post-select, you might want to look at statistics, you might want to do very advanced conditional processing. So condition, if I get the measurement value 0 in the middle of the circuit here, I run some neural network, and then the neural network gives an output, and that tells me what the parameters of my gate downstream. So we have an example here where we're basically doing a measurement kind of somewhere in the middle of a circuit, and then kind of returning the result of the measurement, but also conditioning on the result of that measurement in the circuit. And then we're computing the gradient of that. And if you look here, we're computing the gradient of this circuit with respect to x and y. But the circuit ends up having a gradient of 0 because this first parameter x doesn't really influence the computation at all. So that's just kind of for free. This is another feature that we spent quite some time to develop. Maybe you've heard it called analog Hamiltonian simulation or pulse level control. We call it pulse program because we thought it sounds cool. But this is basically going down to bare metal in hardware, going down to like actually manipulating atoms or superconducting systems with electromagnetic fields. Gates are a nice abstraction, but what you're really doing is you're applying some sort of pulse from a waveform generator on hardware, and it's usually continuous. It's a time-dependent function. And if you can control this, you can actually typically do better in today's experiment because you're getting kind of the best control of the hardware possible. So what we did is we treated everything in terms of functions and operators. So an operator might be like the poly operators, poly x, poly y, poly z, but then they have time-dependent coefficients. And we can declare time-dependent coefficients. We have this kind of pulse function here. I don't know how easy it is to read, but it's just a function of some parameters p and some time t. And if you look at it, the parameters are just a amplitude, a frequency, and a phase of a sinusoid. And then t is just the time argument of the sinusoid. So your pulse, you can basically parameterize an arbitrary sinusoid. And then we attach that pulse to an operator. So now we have a time-dependent Hamiltonian h. And what you can do is you can evolve that h in time. You can simulate what the result of certain measurement results would be as you evolve this thing over time. Again, you can train this. You can train over the time parameter. You can train over the parameter values p, and you can run this on hardware. Maybe another more advanced feature that I think is pretty cool is you can actually parameterize gate you want. You don't have to break it down in terms of its constituent gates. There's this really nice way to parameterize an arbitrary sized unitary. Of course, if it gets too big, it's the whole point of quantum computation is that you're working in a very large space. So if your unitary is operating on many, many wires, on many, many qubits, you're going to run into memory problems. But if you want to do this on maybe 4 qubits, 8 qubits, 16 qubits, probably get away with it. And in some experiments we've done, we've actually shown that using this gate, rather than decomposing it, gives you a much more kind of natural way to evolve the system. Because when you decompose it, you end up introducing all these biases, all the other kind of intermediate gates that it decomposes to. And that can end up meaning you're taking this kind of zigzagging path to where you want to be when you can just take the path straight there. So this is also a native feature of the library. Just to summarize kind of key features very, very quickly, other ones I didn't get the chance to cover but are pretty cool. Visualization of circuits, manipulating operators, doing math on operators, and building Hamiltonians out of like basic building blocks with sums and products and so forth. Different kinds of measurement processes, whether you want to sample, you want to compute expectation values, you want to compute fidelities. We have a number of circuit templates that are available. You don't have to kind of design your own circuits if you don't want to. More advanced features, things like circuit cutting, also called circuit knitting, I've heard it called. More advanced simulators like Clifford simulators. You can do resource estimation. If you're a quantum algorithms researcher, you sometimes want to know if I have some error in this layer of my circuit, how does it affect my final result of my computation? How can I kind of trade that off? So you can do resource estimation. And new features, these are probably coming out in the next 2 releases. One of them is actually next week, and then 2 months after that, just kind of look ahead. Circuit debugging, network simulator, and noise models are some of the things we're working on. So at this point, I just wanted to take a pause in case there's any questions. And then after that, I'll just go into maybe the broader Penny Lane ecosystem. What do I mean by differentiable? Yeah. So you need to have a circuit that has a kind of real valued input somehow. So this input can be the amount of, how much you rotate a particular qubit, or how much you rotate a multi-qubits unitary. But there has to be some notion of a continuous parameter coming in. And then at your output, you have to have some notion of a continuous output. So a standard thing that's a continuous thing to look at coming out of a circuit is an expectation value. What is the average value of this operator measured at the end of the circuit? So if you have a continuous input and a continuous output, that's enough to kind of define differentiability of that circuit. It's if I tweak this input a little bit, how much does the output change? That's what's meant by differentiability. And there's a number of techniques available that allow us to actually compute these derivatives and these gradients accurately. So in simulators, we can use a bunch of advanced techniques for machine learning, this backprop algorithm, or something called the adjoint method. But if you're running on hardware, there's also techniques for computing derivatives on hardware, where you basically run the circuit with forward shifted and backward shifted angles and reconstruct what the derivative of the circuit would look like.
So basically, if you're doing that, so you must be storing the value of both the forward and the backward path somewhere as some concatenation of continuous stream between, for example, after every single multiple layer, so you have 5 layers. For every layer, you must be storing the value somewhere. Is it duplicating the value? Because are those values stored in the pipe as well?
So
the pipe will calculate the main gradient because they will have the gradient tape. For example, Jack will have the gradient tape, for example, right? So you cannot duplicate all the data every single time, because one thing will be stored in the qubit, and the other will be stored in the pipe.
Yeah. So it depends on whether you're going to run on hardware or you're going to run on simulator. If you're running on hardware, you just have to run it, but you have to run it for every parameter you have to run it 2 times. So if you have n parameters, you have 2n executions. If you're running on a simulator, there's some tricks you can play. So you can basically use the standard differentiation pipeline that PyTorch and JAX have, which is the backprop algorithm, but there's a more memory efficient version that is even better than the one they give you. What they would do is they would do the forward pass, they'd run through each step of the circuit and just treat it as matrix multiplications. And at every step, they would kind of cache a value. What was my kind of vector at this point? And then they would go to the next step and they would save that, and they would save the next one, they'd save the next one. You need this for the backprop algorithm because you have to kind of plug in to your chain rule. But if you're running a quantum circuit, you don't want to do this because your vector is a 2 to the n dimensional complex state vector, and it takes a lot of memory. What you do is you end up going through and you don't save any vectors, but because quantum computation is reversible, you get to the end and you just run backwards to recompute the values that you would have saved otherwise. So it's more efficient.
Basically it's a comparison between either you increase the amount of space you need or the time you need. Because if you're going to be the backward path for the quantum, and then it's completely reversible. You're at least reversing, you're at least doing this pass a couple of times, backward path.
So if you it's called the adjoint method. If you're using the adjoint method, no matter the depth of your circuit, you need 1 forward pass and 1 backwards pass, and that's it. So you can get away with computing everything you need on the fly as long as you're willing to go forward and then backward. It's a really neat trick. I can share some papers if you're interested. Yep. Yep. No, you can do it with hardware, but it can be expensive.
Yes, we are not sure about do you have an application.
Yeah, I would only use this technique on gates that are a few qubits. I would stop at like 4 qubits maybe. because even the classical processing requirements get quite big there. There's some classical processing that's needed to compute these things. But on hardware, you need to do a number of measurements to basically characterize this unitary, and it's exponentially scaling number of measurements needed for each qubit. So it can be expensive, yeah. Yeah, maybe the one in the back there. For sure, if you wanted to, you could. It would be expensive, and in simulators you can get away with it because we kind of simulate the state vector anyways. But you could if you wanted to. Yeah, the debugging I would say should only be run on simulators because it would get very expensive otherwise. It basically allows you to inspect the state of the simulator at every step and maybe to like say, what if I applied this gate, what would it look like? But yeah, if you're trying to do that on hardware, you would have to stop the circuit at every point, run full tomography, and then move to the next point, run full tomography. That's very expensive. But if you have a simulator, you've already paid your cost in memory to store a state vector, and you're just updating that single spot in memory. There's another question here.
So it's really tough. If you run it in the simulator, right, and if you're making sure that, let's say, the PyTorch also gets the same gradient, because at the end of the day, PyTorch will do the optimization. If I have an SGD, the update will be through that, right? So you will have to have, like, the code base has to be one-to-one matching with all the backward passes, or at least it has to have, so you're using a decorator, basically, right? Like on top of the main function call, this is the decorator. So it should match everything in the basic Python PyTorch call as well. So
yep.
There's any quantization that's happening, everything will be replicated one-to-one. Is that true? Like,
yep. I mean, the unit tests in the library are based on the fact that it should be the same answer either way.
And would they work the same way as in, for example, any kind of hooks and so like in backward hooks on the PyTorch call, would they work the same? Because I can't see, like, because in the quantum, if you don't have the memory space, if you're not replicating the memory somewhere, like if you're not keeping a copy of it, how are you going to calculate the gradient at the back end? That's my big worry for that. But maybe I can check later.
Yeah, I mean, the techniques that we use under the hoods, if you've already paid the cost of simulating a state vector, to compute gradients is only maybe twice that cost, no matter how many gates are in your circuit. Oh, I can show you some of the tricks of the trade afterwards. Any more questions? Great, thanks everyone for the questions. So I'm going to finish with a look at the rest of the ecosystem. So one thing I mentioned is PennyLane Lightning. This is a high performance simulator suite. So it's not just one simulator, but it's a few different simulators. So we have Lightning qubits. This is if you have a CPU and you just want to have code that is run as close to machine code as possible. It's compiled. We have Lightning GPU. This works nicely together with NVIDIA GPUs. And then we have Lightning Cocos. Cocos is a library that allows you to run on multiple different hardware. So if you happen to have an Intel CPU or an Intel GPU, I don't know how many people have these things, but they do make them. Or if you have NVIDIA GPUs, or if you have AMD GPUs. I think we're the only library that lets you run on AMD GPUs. So basically, try to make it so you can run on whatever hardware you happen to have available. When should you use it? Usually when you're getting into beefier calculations. So if you're running on CPU, maybe more than 10 qubits. If you're running on GPU, maybe more than 20 qubits. GPUs are not something that just works all the time. There's some cost to be paid to load data onto a GPU, so you should be careful about when you do it. But if you're running larger scale computations, you definitely want to use GPUs. If you happen to have multiple GPUs, if you happen to have access to a compute node with dozens or hundreds of GPUs, which we were lucky enough to do for some recent papers, then you can distribute over multiple GPUs. Again, you have to think carefully about it because distributing a very large vector over many GPUs can be inefficient. There's different ways you might want to distribute, but they're all available if you do happen to have those resources and you're willing to pay your vendor the costs of using those ones. So here we have a simulation that we basically ran up to 256 GPUs. Yeah, and if you're interested, this just show you can install on pretty much any kind of laptop or desktop or HPC system that you might have available. The other interesting part of the penny lane ecosystem is something we've been working on the last year and a half, 2 years. It's called Catalyst. It's a compilation stack. So this is kind of the middleware that happens between your program and the simulator. Try and give you as many gains as possible. So it's a quantum classical just-in-time compiler. What is a just-in-time compiler? Well, it's basically something that takes your code from Python and it moves it somewhere else, much closer to machine code. But it only does it when you tell it to do it. It doesn't pre-compile. Like a language like C++, you have to pre-compile things. You have to ahead of time compile. This allows you to play in Python, and then when you want to scale up, you can just add a decorator, and it can kind of compile on the fly for you. And every time you run that code, it should be much more efficient. You can also run on multiple different execution devices. Some interesting things. This is really an experimental stack we've been building. A lot of the technologies here are quite new and pioneering. You compile not just the classical part, you compile not just the quantum part, but you compile the whole workflow together. Again, in penny lane, we like to keep everything differentiable so you can train it. So this preserves the differentiability if you compile, and it can run on different simulator devices. Yeah, this kind of highlights again, if you're just working on prototyping, you probably don't care about speed too much, but there is a price to be paid. So in Python, it has this really user-friendly way to use it, but it's potentially 100 times, 1,000 times slower than equivalent C++ code or Rust code or something. So JIT is this trick that allows you to take Python code and convert it as if it was compiled, like those other libraries. And when you're trying to go from, okay, I have my idea, now I want to see how it works on more qubits, now I want to see how it works on a deeper circuit, now I want to see how it works with 1,000 optimizations, then you're going to start caring about how much you pay per circuit execution in terms of time. So just to hammer home, this is a paper from a few years ago showing the time taken to compile Shor's algorithm, not even to run Shor's algorithm, but just to compile it, to take a program description and to convert it down to like quantum machine code. What are all the gates that are going to happen there? And if you put a flat representation of a program, which is what most naive libraries would do, every time a layer is repeated, you kind of list out all the gates again and again and again and again, and you end up just this huge list of gates that need to be executed. But you got to recognize their structure, that there's potentially, if you're repeating layers, you can capture that in a for loop. And so you just need to have a small bodied for loop and repeat 1,000 times with changing inputs. And that's a much more compact description and much more easy to compile that program. So you end up with this dynamic representation of a program, you can end up with a constant compile time, whereas if you did use this representation, you would have end of the for scaling compile time, which in this paper they were saying would take 1,000 years to compile Shor's algorithm, which is obviously not gonna work. So how does Catalyst work? Well, you have to install it. It's just a Python package that's available. And really all you have to do is you take existing penny lane code and you just add another decorator. We love decorators. Everything's functional, so we have lots of decorators. You just tell it, it's kind of hard to read because it's gray here, but just QJIT, add QJIT, so quantum just-in-time compilation. So this circuit has 10,000 loops, and there's just some additional branching going on inside the loop. And if you don't compile it, execution takes 600 milliseconds. That's no problem, right? 600 milliseconds is fine. But if you're doing this many times, you start paying that cost. So you want to find ways to scale up and make this run faster. So running the exact same circuits 10,000 times, but we can do just-in-time compile, we get down to 6 milliseconds. So 100 times gain in terms of execution time. And all you do is add a decorator to your circuit, and it's just treating it to go through a different compilation pipeline. So yeah, there's a lot of stuff going on under the hood, but really, if you're a user and you're running code, you just add this QJIT decorator and it compiles it. And it can be much more fast than you would otherwise have it. It's a beta package, so there still might be some rough edges, and we'd love to hear from you if you find any. But that's the value proposition, is you just add this decorator and suddenly your code can be potentially 100 times faster. And you can compile different parts of your program. You don't have to compile it all, you compile separate parts. So you can compile the cost function calculation, which includes the quantum circuit execution. you can compile a whole optimization loop. So this is repeating 10,000 times potentially the same circuit over and over again. You can compile that whole optimization process as well. What's happening right now, if you're working on quantum hardware, when you do this loop, your Python code sends a job to hardware, gets a result, comes back, re-executes something in Python, sends it off again. It does this hundreds of times, thousands of times potentially. This is really inefficient. We need to rethink this. And this is the kind of framework we're putting together to allow you to skip all of that and to just ship the whole hybrid program to the vendor and have it run there. And all the for loop that's happening is no longer going over the internet. It's no longer going back to Python. It's just being executed locally in a runtime. Finally, just want to kind of call out the website. It's a great place to go if you're a researcher or if you're a learner in quantum. We have a few great resources there. We have data sets, we have lots of demonstrations, we have coding challenges, and we have an online textbook. So the data sets, really the idea here is if everyone's running the same experiments, we shouldn't be creating data from scratch. We should all be using the same data. Right? So if I see 100 papers all doing VQE on an H2 molecule, I hope people are not creating these H2 molecules all by themselves every time, because that's not really the purpose of people's papers, right? So why can't we share the same data? And if you have data, we'd love to hear from you. You can share your data with others. So you can see this kind of animation here. You can do things like select the molecule, you can select the basis sets, the angle, what's the separation of the bond. These kind of things are all available. You can kind of tweak different parameters to get different data sets. Demonstrations, we've been working on these for about 5 years. We have 120 plus different quantum computing demonstrations on the website. Starts from beginner stuff, more advanced stuff, implementations of key papers, showing some of the key features of Penny Lane that I talked about. It's a great resource, even if you're well familiar with the field. Just a reminder, hey, how does this work again? What does that concept mean? We'll have a demo, almost certainly. Coding challenges, this is if you want to kind of up your game, you want to get really good at quantum programming. We've got dozens of coding challenges that you can do. They're auto-graded. It runs through a submission system. It's kind of a way to challenge yourself. If you're just getting into the game, you don't want to do research, but you want to just get really good at understanding quantum algorithms. And finally, the code book. We're actually upgrading this, and it's releasing in 2 weeks. And this has a few dozen different chapters, I'll call them, their nodes. And yeah, it's basically based on the same coding challenge system, but it contains lots of pedagogical content around it. So if anyone here is TAing a class, for instance, this might be of interest. So yeah, that's it. I want to just finish by saying some ideas for what you could do next. You could check out the library for your research or for your education. If you're already using it, you can check out the website. If you're not using it, you can still use the website, because the website's got lots of materials that are relevant just for any researcher, even if you're not using the library. If you want to ask for features or report bugs or try to understand some of the things we're doing more, we're happy to help you on our discussion forum. Anything else that's not covered, you can also email me. This is my email, and I can put you in touch with anyone at Xanadu or on the Penny Lane team who might be able to help you with your questions. And maybe even as a reward for those who have stuck around to the end, I do have a bunch of stickers here that I can give out. I've got these cool quantum gate emoji stickers that you can put on your laptop so your laptop can look nice and full of stickers like mine. So yeah, I'm very much thankful to be here. Thanks to the organizers. Thanks to everyone for sticking around, and I'm happy to answer any more questions you might have. Why is it called Penny Lane? So it was named by our CEO, and he said the Beatles are his life. So he just liked naming things after Beatles songs. And our first software library that we made was called Strawberry Fields, and the second one we made was called Penny Lane. And if you know the Beatles, that was a single that they released. The A side was Strawberry Fields, and the B side was Penny Lane. Any other questions?
You have to basically through the Strawberry Field library, you're not really accessing the common hardware. reach out to them to get
Yeah, so for any hardware, not just Xanadu's, but any hardwares, you should hook up with the vendor to get credentials. And then there's a plugin available to basically tell PennyLane what your credentials are and send submissions to that hardware. And come get your stickers if you want some.